We're back. Sorry, we had lots of trouble in broadcasting it on YouTube, but it's working now. So it's the only problem because the whole room is waiting for your talk. Thank you very much for being here. We know that you've been sick and could not attend it in presence, but we're very glad that you could still make it, and we even know that you attended our talks yesterday online. So there is some. It makes sense to try to have it online. And thank you very much for being there. And you will have the floor very soon. I'll just show you that people are just watching, are just waiting for your talk. And so you see the audience, and you will see them when they'll be asking questions. So thank you very much for being here. Your talk is Intuition and Axiomatics, the case of non-Archimedean continuity. The floor is yours.
us nothing directly concerning the existence of limiting points or of the idea of convergence. Nevertheless, it enables us to demonstrate Bolzano's theorem, Bolzano-Weier's theorem, by virtue of which, for all sets of points situated upon a straight line between two definite points of the same line, there exists necessarily a point of condensation, that is to say, a limiting point. From a theoretical point of view, the value of this axiom is that it leads indirectly to the introduction of limiting points, and hence renders it possible to establish a one-to-one correspondence between the points of a segment and the system of real numbers. However, in what is to follow, no use will be made of the axiom of completeness. There is a huge literature on why Hilbert introduced this sort of meta-theoretical axiom to express continuity, but many explanations concern, for example, the role of Pythagorean subfields of the real numbers. But I want to recall Giovanni in 2013, who gives other reasons. One reason is that Hilbert wanted to build continuity step by step, and considered that neither Cantor's nor Dedekind postulate could be regarded as merely geometric. So both did the things in just one step, and neither was merely geometric. That was his point. So according to what we find here in Hilbert, we might have the impression that axiomatic needs, for example, the step-by-step procedure, prevails over intuition, because for a long time, Cantor's or Dedekind's point of view were considered as nearer to our Bolzano-Weier's intuition. It's interesting that this idea that you have a geometric and that you have descriptive axiom of continuity was well represented in Enriquez 1907, the articles Principia della Geometria that was published in the Encyclopedia. The difference that he traces between geometric axioms that talk about segments and descriptive axioms where the talk is about points. Dedekind's postulate was usually presented as a partition of points. So the story I would like to tell is something that goes from Dedekind to Hilbert and from Hilbert to Baldus. And it's a story that has a lot to do with Giuseppe Veronese and his idea of intuition. That is, let's recall it at the beginning and then discuss it at the end again. Intuition is, for Veronese, not something that is, like in Kant, only related to senses, only related to empirical experience, but and not, on the other hand, something like our intuition of space that is a priori and transcendental form. For Veronese, intuition was something really in between. So we have an intuition, an empirical intuition, but this empirical intuition evolves, changes in time, depending on the practices, the experiences that we make. He had this metaphor of the intuition of the painter, and by painting, like the geometer, he imagines or has an intuition of different dimensions, and so gets his intuition refined, to use the word by Klein. That is, the intuition changes according to the kind of abstract experiences we can make. So let's start with a bit of history and then come back to intuition later on. I will start with Stolz zur Geometrie der Alten, 1883. He was the first one who gave the name Archimedes' principle to that definition for it that we found in Euclid's book. And his comment at the beginning was, well, there are Dubois-Reymond functions, and the discovery was that this function can go to infinite in different degrees. So you can compare them even if they are infinite. And so he says these functions do not satisfy Archimedes' principle, but they can be compared. So the first conclusion he comes at is that this principle cannot hold for all quantities in general, but should apply only to some. And then discovering that whenever you assume Dedekind's axiom and other properties of quantities like trichotomy, uniqueness of sums, or property of sum and congruence, then you can claim that the Archimedes principle also holds. So Stolz starts at the beginning to think that, well, if the Archimedes principle is a consequence lamps of Dedekind, and it holds only for certain quantities but not for all of them, then it should be a feature of continuous quantity. And it was the first one to say it's a feature of the linear continuum. So what we found in Hilbert has his origins in what we find here in Stolz. In some sense, our intuition of continuity is influenced by axiomatic results, the relation between Dedekind and Archimedes, and exogeometrical results like Dubois-Remon's results on functions. But Veronese criticized Stolz, explaining that his results depend exactly on a sort of derivation that you can do from Dedekind. This derivation you can do because Archimedes' principle is part of, this is what he said, of the expression of Dedekind's postulate. And the idea that started coming up in this discussion between Veronese and Stolz was that Dedekind is actually a sort of composed postulate, a composed axiom that has two parts. One is Archimedes, and the other one is something else that should have to do with pure continuity. So we have the Archimedes axiom, which tells us that there is a specific order of a system, and the Dedekind principles that require this ordering to be gapless, to be continuous. So if you want to avoid gaps, you have to assume Dedekind. But you can have a sort of ordering already with the Archimedean axiom. And so, in general, everybody seems quite fond of Dedekind's definition and the idea that it really expresses continuity. So, Archimedes is now an ordering with gaps, and Dedekind is the order without gaps. And this is what we want from continuity. Veronese made a step further. He said the Archimedes principle is not contained only in Dedekind's formulation, but also in the Cantorian formulation of continuity. Here it is. Given on a straight line and sequence of segments A1, A2, AN, having the following properties, that each segment contains all following segments, and the length of the segment converges to 0, then there exists one and only one point internal to all the segments of the sequence. This is a geometrical presentation of Cantor's formulation of continuity. The problem, according to Veronese, is that when it assumes in point 2 that the length of the segment converges to 0, it is implicitly assuming Archimedes. And so Veronese presents a different postulate, claiming that any segment whose extremes, having always variable extremes in opposite directions, becomes indefinitely small, smaller than any possible segment, contains an element outside the range of the variability of the extremes. I will show you how this engender a huge discussion on the relation between Archimedes' principle and Cantor's continuity. And for example, Baldus in 1930 tried to give two versions of Cantor's. The first one, the metric, the usual version, and then he presented a sort of topologic, which is very near to Veronese's own presentation, where the idea is that you not require the convergence of the segments, but just that a sort of a segment such that it has a smaller length than any other segments you can imagine. And here I give you the standard representation of the Cantor-Dedekind continuum, the one we found also in Hilbert. So if Archimedes holds, there is no real difference between the two versions of the Cantor postulate, because the intervals converge to 0 anyway and become smaller than any given segment. The point is, what happens if we have a different intuitive representation of the continuum? So here we have a straight line. This is how the continuum was usually represented. Well, let's imagine what happens if we have this representation of continuity. This is an image that I take from Baldus in 1930. You find a similar image in Fano 1932, and a similar image also occurs in Veronese's own book. The idea is that you can imagine the linear lines. And then you have a direction going from left to right on any straight line. So you can imagine that a segment can have first extreme on one straight line, for example A, and a second, for example B, on the second straight line. So whenever you start dividing in segments into smaller segments, so A1, B1, A2, B2, A3, B3, A4, B4, what happens is that the intervals become smaller and smaller, but they never converge to zero because they are on two different straight lines. This means that Archimedes does not hold. And when Archimedes does not hold, you see that you need to split the condition in two cases. One case is in when it converges, if the segments are on the same straight line, and one case is where they belong to different straight lines. So you will have a gap whenever the segments belong to different straight lines. The point is that according to Veronese, this model corresponds to our intuitive linear continuum, and he gave many arguments to say that whenever we imagine a continuum, we do not know what happens. We cannot perceive by senses what happens at the infinite. So, in a sense, we have this possibility of always imagining something farther beyond any given set of things. So whenever you have a straight line, nothing prevents us from imagining something outside a straight line. So for him, this is really compatible with our intuition of continuity. So for the first time, we have that we can have a system that is non-Archimedean and continuous at the same time. It has gaps. So the notion of continuity is now separated from the notion of being gapless. This opposes Veronese to Dedekind. For Veronese, the geometric continuum is more general than the continuum of real numbers, which is a special case of it, one straight line and a system of straight lines. And the starting point for the construction of this geometric continuum is really our intuition. The intuition of continuity consists in the fact that given any interval of the straight line whose extremes are variable in opposite directions, the extremes form an interval that decreases continuously without the two extremes coming to coincide. The existence of a single element within the interval guaranteed by Dedekind's principle is a special case, which does not necessarily occur in a line that we perceive as continuous. For Veronese, every limit point of a Dedekind can itself be seen as a line containing infinitesimal segments with respect to the given line. He really takes the visibility to the infinite in a straight form. And Brouwer in 1907 showed that Dedekind's continuity is a special case of Veronese's continuity. So there was a lot of mixed work on the one hand on intuition and on the other hand on dependence and independence of actions in order to show these things. These are two different ways of understanding linear continuity. On the one hand, we have the existence of a limit for every partition of a set of segments. This is Dedekind's approach, which also contains Archimedean comparability. And then you have the possibility of comparing any two intervals, even when one always remains smaller than the other for every natural multiple, and the assumption that the limit exists in some cases only when the intervals converge to zero. So, what are the differences between these two ways of understanding line continuity? From the formal notion, we derive the usual principle of Archimedes, while in the latter case, we require a principle that has a similar function to Archimedes, but is based on a different notion of multiple. So Veronese will develop a system of hyperreal numbers, and then you can use these hyperreal numbers to multiply a quantity. And so multiplying an infinitesimal quantities by a hyperreal number, you can get an infinite quantities and so on. In the case of Veronese, continuity is composed not of a single axiom, but of two axioms. An Archimedean notion of comparability, which is enlarged, is non-Archimedean, but plays the same role of the Archimedean axiom, and the notion of continuity proper, the possibility of making an interval smaller and smaller, this divisibility. In the former case, the continuum in Dedekind's case is constructed from a discrete material, sets of points. In Veronese's case, from continuous material, set of segments. And he insists on that, insisting on recapturing Aristotle's idea of continuity, saying that an interval with variable extremes is a set of segments and not of points. He always avoids reducing segments to points. So in Dedekind's approach, linear quantities and numbers have the same kind of continuity. Real numbers are a possible representation of linear geometrical magnitudes. In Veronese's approach, they have completely different features. Real numbers are Dedekind continuous, and linear magnitudes are not. So we have a different intuition for numbers and for geometric magnitudes. And this is a key point in all discussion of how you can do geometry independently from numerical systems. Some words about Bertazzi 1890, Teoria delle grandezze. Bertazzi does not talk about intuition. He really presents a sort of formal, abstract, axiomatic study of ordered systems. He studies the properties of classes of magnitudes independently of numbers in a structural way, distinguishing several properties such as being one-directional, limited, proper, or isolated. And in particular, he considers how an ordered class can be divided into subclasses and distinguishes connected classes, which contain only links or sections, closed classes, which do not contain sections, but contain the limit of every section of the subclasses, and continuous classes, which are connected and closed, and thus contain only links. So he goes back to the standard idea that Archimedean classes contain no gaps and are called classes of the first species, while non-Archimedean classes are called classes of the second species. It answers to the introduction of numbers as a system that corresponds to a class of a given category. For example, the class of integer numbers is associated to all discrete classes, the class of fractional numbers to all rational classes, the class of real numbers to continuous classes. So you can see numerical systems are like the representative on an equivalence class of structures. Measurement is the mapping of any class of magnitudes of a certain kind into a class of numbers. So non-Archimedean classes also are mapped on a numerical system, hyperreal numbers, so they can also be measured. But they are not continuous. So what we have here is that continuity and measurement are separated one from the other. The point is that there is measurement in general, then measurement by real numbers, and continuity is the name for the measurement by real numbers. So the Archimedean principle does not express comparability or measurability anymore, because also non-Archimedean magnitudes are compared and measured. Hodder, 1901, first one who gave a complete axiomatization of measurable quantities. He also presents a model of non-Archimedean system, but he really sticks to Dedekind's theory of continuum, considering it as incompatible with Veronese. He did not know Veronese's results in detail. He did not. He was convinced that the two were incompatible, and that's why he thinks if the two are incompatible, we want the axiom of Archimedes, we want then the postulate of Dedekind for measurable magnitudes. So our intuition of measurable magnitudes, he claims, suggests that they are Dedekind continuous. But we see there was at the time a sort of lack of consensus on what intuition tells us about the continuity of linear quantities. My point would be that in many discussions about how we intuit the linear continuum, the axiomatic results played a huge role. Hilbert's approach has a point of contact and a fundamental difference from Veronese's. Both believe that continuity should be expressed by two axioms in two steps and not just in one. However, Hilbert explicitly associates Archimedes' axiom with continuity and thus completeness as a second element. This move, in particular, made it very difficult for a long time to imagine that a non-Archimedean system can be complete, since the axiom of completeness included Archimedes. So this sort of maximal axiom, meta-theoretical axiom that has been always praised so much, was not so fruitful in the case of investigating ordered magnitudes, like non-Archimedean ordered magnitudes. Because what you need to do is to provide a definition of continuity that does not presuppose Dedekind, and then provide a new completeness result. And this was done by Hahn in 1907. He assumed completeness for non-Archimedean system of quantities, assuming Veronese a generalized version of the Archimedes axiom. And Hahn follows Hilbert in providing two axioms, sort of generalized Archimedes and then completeness axiom. Hahn quotients a system of Archimedean quantities into Archimedean classes, of non-Archimedean quantities, into Archimedean classes for an equivalence relations. So any kind of Dedekind continuum, any kind of straight line, as in our image before, is a sort of equivalence relation class. These are the segments that have the same height, that are finite, one with respect to the other. And then we can have segments having different heights if they do not satisfy the Archimedean principle with respect to each other. And then he gives a principle of completeness, saying that it is not possible to expand the system without losing the property that each new quantity introduced belongs to one of the previously obtained equivalence classes. So now the Archimedean principle operates as a sort of means to postulate another structure into Dedekindian substructures, a completely different world, has nothing to do with continuity anymore, but rather with finitude. And I conclude by Bali 1907, which is a very interesting paper, I think, from Bhutan, who mentioned that in a review to Giovannini paper, saying that Valen took Veronese continuity as the property of pure continuity, or Einstetigkeit. And then he had, if you add Archimedes axiom, you have Dedekind continuity. But then, why should we add Archimedes axiom? We might be guided by other ideas, not that of measurability, but we might be guided by the idea of having a system that is closed under algebraic operations. So what he does is assuming Veronese continuity and then adding an element, I, as the square root of -1, that allows the closure of algebraic operations. So we have a mixed system. And here, the essential point is not that of having no gaps, because the system contains gaps, but that of being closed under algebraic operation. So we have some sort of new intuition emerging from a combination of geometrical and arithmetical objectives, continuity on the one hand and closure on the other. There are two ways to show that Archimedes axiom does not express continuity or full continuity. It expresses only the comparability between quantities of the same height, Veronese and Hahn. And so this strategy allows for the development of the idea of non-Archimedean continuity and considers Dedekind continuous systems as special cases of more general structures in which the field of reals is immersed. Or you can hold that it is a first step toward continuity, but is not sufficient to derive either Dedekind's axiom or Boltzmann's theorem. This strategy considers the Dedekind continuous case as the maximum possible expansion of a system of quantities on pain of losing its characteristic properties. Now, this was the historical presentation. Now, what I really want to say is how intuition at several steps modifies the axiomatic formulation of continuous systems, so the other way around. There were different procedures of completion and definition, a search for different things, one step or two steps procedures of axiomatization. I will mention the role of the starting intuition and the end intuition as a way to demarcate between legitimate and illegitimate theories. We had a variety of non-Archimedean systems, and the choice of the system often depended on some objective. What guides the construction of such different axiomatic formulation? We had a system also in Hilbert, I didn't mention that, but so many things. Different intuitions guide the axiomatic development. In Veronese, the point is express the intuition of continuity. In Bertazzi is to clarify the relation of order and to clarify how numerical systems are associated to system of quantities, so to clarify the idea of measurement. In Hilbert and partly also in Veronese, one important point is also really axiomatic, that is, show the independence of certain axiomatic assumptions. Hilbert's non-Archimedean model is a way to show that the Archimedes axiom is independent from the others. The same you have in Hulda, the same you have in Veronese. Then we mentioned Valen. Well, the main point is the closure of algebraic operations. So what guides the whole procedure are some sort of values or goals that have to do with our intuition. So my point would be that in this objective, there is an intuitive part that plays a role. One, for example, is the idea of completing the order from a gapful density that we have in rational numbers and expressed by Archimedes to a gapless continuum, the continuum of the real numbers, the Dedekind continuum. Or in the case of topology, we might say not all Cauchy sequences converge, we want to go to a convergence of all sequences. Or when we are in the case of algebraic operation, we have the non-closure of Veronese's number system, we want balanced number systems that are closed under certain algebraic operation. In other cases, we have a sort of process of definition of linear continuity, and we have a sort of incomparability, a sort of tendency to generalize certain kinds of comparability principles from Archimedes to generalize Archimedes. Or we have the problem of measurability. We want to discuss how and why real numbers can be associated to the points on a straight line, and which numbers really do the work and why. And then we have this idea of pure continuity, so abstracting something that does not belong to order only, but has to do with the traditional intuitive idea of infinite divisibility of linear segments. But we have also an axiomatic procedure that searches for different things. In one case, you have a search for definition and properties of ratios, numbers, sequences, functions. In other cases, what you're really looking for are structural or architectural relations. One clear example is Bertazzi, the other one is also Veronese. The point is to show what's the relation between a Dedekindian structure and a non-Archimedean structure. And you might do that also in the case of number system when you want to show how, in which sense you can say that real numbers complete or eliminate the gaps that you have in rational numbers, or a complex number eliminate the gaps that you have when you have some operations that are not closed, and so on. A huge point was the search for axiom dependence and independence. So what I'm interested in is how some, let's say, meta-theoretical practices typical of axiomatics induced changes on intuition, or on the contrary, the search for certain dependence and independence were guided by the fact that the axiom did not exactly correspond to our intuition of continuity. And again, all the discussion between pure geometry and analytic geometry, synthetic geometry and analytic geometry played a role. So all the discussion on how intuition should guide geometry and get rid of this sort of tendency to use numbers to represent as models, adequate models for representing geometrical quantities also played a role. And then we also had results from different domains, like Dubois-Ramon functions, so intuitions coming from analysis and from other aspects. that had nothing to do with geometry. And then what we can consider is how axiomatics had this strong interest for distinguishing between one-step or two-step procedures. So all this discussion that I tried to make between pure continuity, the Veronese's or Cantu's geometrical formulation, topological formulation, and the sort of metrical or Archimedean parts of continuity was a way to separate into two axioms. But was there some corresponding intuition to this separation or not? Veronese would say yes, other would say no. And then another interesting part is the role of the meta-theoretical axiom, really the role of something that goes beyond intuition, as it seems at some point, or rather sticking to the Archimedes principle was Hilbert's way to stick to intuition in the first step of the procedure. And again, when I discussed synthetic and analytic geometry, what I want to say is also that starting from segments, numbers, magnitudes that have to be measurable, as in Holder, or from functions, leads to different axiomatic formulations and also to a different number of axioms. So Veronese and Hilbert start from nice segments, Dedekind starts, let's say, from both, in a sense, from real numbers on the one hand and points on the one hand, and then he tries to associate the two. Holder starts from the idea that he wants to discuss measurable magnitudes, but that he discusses magnitudes in general, and then want to see how, and discusses numerical systems in general, and then try by a representation theorem to associate the two. And Valen actually starts from hypercomplex numbers. All his discussion starts from a number system, and he develops this hypercomplex number system with real coefficients and rational exponents. So he assumes the numbers from the beginning, both as coefficients and exponents, and in the idea that what he wants to build is a numerical system, which we can calculate upon. So again, we have intuition playing the role of starting the element, and this forces an axiomatic treatment that has an effect, a change of the intuitive content of the Archimedean axiom. Exactly, this axiom changed in time. Did it change meaning? Did it change in its relation to intuition? It was a property precious, Eudoxus Euclid at the beginning. It was a property of homogeneous but eventually incommensurable quantities later on, so forced to avoid incommensurable at some point when incommensurable magnitudes were accepted. You could say, well, it extremes homogeneity but not necessarily commensurability. It became so, in a sense, a sort of axiom expressing comparability, and this for some time was considered as a way to exclude infinite or infinitely small quantities. Assuming Archimedes was assumed that no infinitesimal segment exists, because an infinitesimal segment is a segment that remains smaller than any other segment for whatever multiple, integer multiple you can find. Then in Stolz and Hilbert, it became the champion of continuity, the axiom that really expresses the intuitive content continuity. In Bertazzi and Holder, it was a postulate concerning measurement and order in particular. In Hilbert, it was a preliminary way to continuity from 1900 onwards, and not all what leads to continuity, because you need the axiom of completeness to have the Bolzano-Varillas theorem proved. And in Veronese, it is a non-necessary ingredient of continuity unless in a generalized form. And for Hahn, it expresses the comparability of magnitudes of the same height. Finally, intuition played another role in all this discussion because, as I mentioned before, for Veronese, non-Archimedean continuity not only is intuitable, but is what we get from a deep analysis of our empirical linear continuum. Because what he says is that our empirical intuition is always related to a finite portion of space and not to the totality of space. and it is always combined with a sort of abstract intuition. So the idea is that empirical intuition and abstract or logical intuition, different names are used for that, cannot be separated. And I discussed the case of non-Archimedean geometry today, but the same kind of argument is presented by Veronese for hyperspatial geometry, so for geometry with more than 3 dimensions. And a huge discussion is centered on whether these theories are geometrical in nature, numerical or arithmetical in nature, or abstract theories. Veronese would go for the geometrical part, Bettazzi will go for the abstract theory, so it's an abstract theory of systems having special kinds of order, and the same probably would hold for Hahn. So the question I would like to conclude with is that what we have, this historical example might tell us that intuition may vary from one context to another, and by context, I use this in a very general way. It might have the type of objects one deals with, geometrical continuity, arithmetical continuity, measurable continuity, but might depend on the notions that are common knowledge at the time. Let's say, I did not mention here, but Aristotle's continuity, Bolzano of Aristotle's continuity, Cantor continuity, Dedekind continuity. But intuition may also vary from one axiomatic theory to another, depending on the type of axioms one deals with. Intuition might provide models for new axiomatic theories, non-Archimedean linear continuity, non-Archimedean hyperreal systems. If you go back to the image I showed before with the several parallel straight lines compared to the single straight lines, these are different intuitive models of the abstract axiomatic system. So what I'm trying to suggest with this example is, as part of a larger project on axiomatic, that the relation between axiomatic and intuition is very complex and goes in both directions, and formalization, as it plays a role in axiomatic, cannot be said to just eliminate intuition or, let's say, contain really the role of intuition. What I would like to say is that in these debates, in these controversies, in this discussion, there was a deep interaction between intuition and axiomatics all the time, a back and forth between the two. So I thank you for your attention, and here are some of the references I mentioned. So thank you very much.
Thank you very much, Paola, for this great talk. I mean, that was very much interesting, and I guess there will be questions from the audience. So we will now ask a few questions, but thank you very much. We really are pleased that you could make it, because that was very interesting for the whole workshop.
So questions? Yeah, Jessi.
During this time, was there any sort of rules that the mathematical community had set up in place to determine if an axiom was an axiom? Like, should it have certain characteristics or properties in order to be able to call it an axiom?
Yes and no. So there was no definite criteria. Rather than being called an axiom in general, the idea was, could it be called a geometrical axiom or an arithmetical axiom? There were a lot of criteria trying to show what could be a geometrical or a non-geometrical axiom. For example, with Hilbert, Poincaré, and Veronese, a discussion on that, yes. Another point was it needed as an axiom, or another principle should play the role of axiom instead? This was a huge discussion about the order of axioms, starting from Ramos up to I would say up to Pehanu, you find this idea. Bolzano is a good example of that, discussing whether one property or the other should come forth. And so more rather than on the evidence, which was not a criterion anymore, the truth or the evidence of a principle to be an axiom. The point was it just had to be non-demonstrative, but then there were other criteria like, is it the first one we want to take and then we want to demonstrate the others or not? And one point I made in another article was that even if apparently in hypothetical deductive system you stop considering that there are some truths that are more evident than others, still this search for an ideal right order of axioms still remained. So an example maybe is Hilbert as I presented it today. You have this sort of two-step procedure that appears to some as better than a one-step procedure. Why? It's not explicitly formulated as a criterion, but still you have this idea that you have to isolate the smallest components. You have to isolate pure continuity from the Archimedean property, but it's not expressed, of course, as a criterion.
Okay, other questions? Gerhard? Oh, you wanted to follow up? Okay.
Thank you very much, Paola. I'm very impressed about your analysis. Now, you say that intuition depends on objects and on context and so on. And in my lecture, I defend the thesis that intuition should be independent of objects, independent of context, and so on. I suppose, I have no idea now, but I suppose you use a different kind of intuition for your different examples. I don't know, I should examine this in detail, but this, so we should keep in discussion, and I would like to have your slides to prove it. It's very, very interesting talk. Thank you very much, and perhaps I have to revise my position.
No, thank you. It's true that that was one objection I was coping with, and you made it, I accept it, is there are different notions of intuition that I've been using in my talk. This is true. And the point is, I don't have, I'm very sorry I missed your talk, but I will ask your slides because on Monday I was really totally kaput. But what I would like to say is we have different efforts to clarify what intuition is at the time. So one point would be, I go for intuition, how it is presented at the time. You have Kant's intuition on the background, reaction to it, you have Helmholtz, you have Klein, you have Poincaré, you have Veronese. So one way would be go historically. Hilbert, so you just try to say you have a sort of notion of intuition that has to cope with the Kantian notion, has to react to it, and what's really clear that they want to have some sort of intuition that has to do with experience, but at the same time have some abstract component. It's very difficult how to account for that. And then I think there is a parallel but intersecting discussion, which is near to the problems of purity, where you have this analytic synthetic geometry discussion all the time. The two are intersecting, and Veronese is a good example of how the two intersect. I agree that they are not exactly the same thing. The notion of intuition that you have in the discussion of analytic and synthetic geometry is slightly different, because this is the one who has to do specifically with objects. Yet the two intersect all the time. That's maybe why I didn't clearly separate them, because my difficulty historically would be to say, what did they understand by intuition? It's not at all clear. What was clearer for me is how it was perfectly normal to admit this back and forth between intuition and formalizing efforts and axiomatics that later on was considered as wrong. So my point would be, a minor point would be at least to show that a certain idea, a certain way of proceeding of axiomatic as a static construction of certain theories does not work, because all the time you had this dynamics between some sort of, let's call it intuitive in the sense of pre-axiomatized, and effects that it has on the interpretation of the axioms at the end. So we have this sort of intuition as what comes before and what comes after. The two need not be the same thing. That would be my point. So the axiomatization is a process that changes the starting intuition into something else. I agree that starting intuition might be delicate to assume numbers, or because this is already theoretical. So I would get your point that I was following more the way people were expressing themselves than making a deep philosophical analysis. This is a delicate point. How you express intuition before the axiomatization, because it's already context dependent from previous theories. So it's true that somehow it was already theoretical determined. And this was what I did not really explore in detail, but the mention of Bolzano-Weier's stress at some point as a sort of reference. Everybody said the Bolzano-Weier's stress, the idea of Bolzano accumulation point, that was somehow what people had to account for. That was this sort of pre-theoretical and half intuitive, half theoretical notion they had to cope with.
Thank you very much.
Bruno?
Yes, thank you. I've got a question. So I'm sorry if I missed perhaps part of what you said at the very beginning of your talk. We again had a small problem I had to solve, and at that time my attention was not perfectly on your talk. But you haven't talked about the intuitionist conception of continuity. So Brouwer, of course, and the relation of his intuition of continuity and the way real numbers should be built, but also the relation between this notion of intuition and the notion of intuition he has for arithmetics, like the notion of 2et that would go from one number to the next one and things like that. So you left that aside, and also Weil's notion of continuity in Das Continuum. So before his intuitionist turn, but still a constructivist notion of continuity. I think you left them aside. Are you planning to also look at them in this, especially because these people are ones who claim that we should rely on intuition for starting doing geometry and mathematics in general?
Very quickly, exactly, that was, I think, the best paper that realized from the beginning Veronese's point, and Veronese's idea that you can have an intuition of continuity that is gapless. And I think this plays a big role in the kind of way you imagine that we are building up on some intuition, and that we are not forced in just one direction. So this construction is built upon intuition, but need not be forced in just one direction. This is, I think, the one important thing that is very clear in Brouwer's presentation 1907, and I think Wahlen and Brouwer are the two that really get things very clear from an axiomatic point of view, from the intuitive point of view at the same time. But it's true that I haven't worked specifically on that. So that's what, and while also they come a bit later, but it's true that they both played a role. It was a discussion that played a role especially in German-speaking countries at the time. So also the neo-Kantians, NATO, Burkhardt, all discussed these questions. So building a larger story for the part after 1907 to 30 and 40s is certainly important to understand how this notion of intuition evolved.
Thank you very much.
Any other questions? I may have like some kind of a really wide-ranging question. So I've recently seen that Solomon Pfefferman wrote a bunch of papers. I mean, I knew he worked on that, but on the continuum hypothesis. And he has defined the view that this is not, according to him, a definite problem. And when he did that, he actually like analyzed various notions of continuity from different authors in the same way as you presented it at some point during the presentations. And he used this to make the point that the notion of the continuum that we have in set theory is actually very different from the notion of continuum, or maybe the intuition of continuity we have in geometry or in analysis. I just wanted to know if you had a look at that, and if you see any connection with what you said, in particular, like a potential role for intuition, context dependence connected to this like big problem.
This is a huge problem whenever you discuss continuity, because it might have to do with many different notions. On the one hand, I would say they are quite different, like the notion of the continuity of a function cannot be identified with the notion of the continuity of linear continuum, so the continuum hypothesis, and the same is more something. But on the other hand, you might say, well, it's still about a concatenation of orders. I'm telling you how many levels you can have. So it's not completely different from... this, I think, is one of the problems, and this is why I try to attack the point from just one axiom, the Archimedes axiom.
Right.
Because it's easier to show this back and forth in one axiom rather than in one program. So rather than in the program of definitely giving an axiomatization of continuous what, I try to say how the Archimedes axiom changes in time, suggesting that apart from a general theory of something or a general program you might have specific axioms that, let's say, they are like objects leading their own life. You might not like the expression, but they are at least linguistic objects at some points. And whenever you mention them and you change their meaning, you are doing something. So it's a dig operation. The same might happen for continuity, but rather than sticking with adjectives, I just rather prefer to stick with axioms that always occur in a specific theory and whose meaning can be better determined. Anyway, I wouldn't say that there is no relation at all between the problem of the continuum hypothesis, which has to do with how many orders and what lies in between two different layers, and this kind of problem, for example, of Veronese's continuity, where you are trying to check what's the relation between Dedekindian continuity and others, so the hyperreal numbers, for example. But they are distinct problems anyway.
Okay, thank you. Any other questions? Okay, so if there is no other questions, then we close the session. Thank you very much, Paola, again.
Thank you.
Sorry for the problem. It worked perfectly well at when we tried at 9 in the morning, and then when we just launched it, like, don't understand anything. Really sorry about that, but it worked well.
Yeah, thank you very much, and we'll try to have a correct online broadcast so that you can go on following us in the next few hours. Thank you very much. Bye. So we're leaving Teams now because we have to go to other online solutions. Thank you. Thank you very much. Yes, I mean, we're already almost 20 minutes late, so if we could make it just a 5 minutes break, or is it better 10? 8? Shall we settle at 8 minutes? Great.
Talk. Yes.
This works.
We'll start again. So not to be too late.
Mhm.
So now we have the pleasure to listen to Tabea Rohr's talk. She's talking not about Kant's notion of Anschauung, but about Frege and Hilbert's reading of Kant's notion of Anschauung. So we're pleased to have her here today, and the floor is yours, Tabea.
Thank you very much for the invitation. So, yes, as my title suggests, I will talk about Frege and Hilbert and Anschauung. I will also start to talk a little bit about Kant on Anschauung. Just as a preliminary remark, I talk about Anschauung here all the time instead of using the English word intuition, because this word is a translation of two very different German words, namely Anschauung, which is like the philosophical term which probably originated with Kant, and then there is also a German word, Intuition, used in context like female intuition, which means something completely different. Second preliminary remark, so my talk is not like one paper, but it's like taken from different works. So what I will present about Frege is mainly also something you find in my book, Freges Begriff der Logik from 2020, which is based on my thesis. And the part about Hilbert in the 1890s is can also be found in my paper, The Frege-Hilbert Controversy in Context, which appeared this year in Synthese. In both, I kind of embed this notion of Anschauung and this discussion into like the development of 19th century geometry. I will widely omit like this part here because some of you already listened to talks I gave on this topic, and I wanted to present something else in order not to bore you too much. The very last part on Hilbert in the 1920s is something I'm just about to start thinking about, and I will show you why I think this is like interesting. Okay, so let's start with Anschauung in Kant. So luckily, Andy yesterday already talked about Anschauung in Kant. I just want to highlight again that when we talk about Anschauung in the context of mathematics in Kant, we have to always keep in mind that we're talking about pure intuition, reine Anschauung. This is important because reine Anschauung is very different from the Anschauung of concrete objects. Kant has like two forms of intuition, of Anschauung, space and time. And they are, how he formulates this, the condition of a possibility of appearance. So any object we perceive is spatial and is space in time. So we cannot think of an object without this being in space and time, but we can think of space and time without an object in it. And in mathematics, we do construction within space and time, which is possible before like having any kind of appearance. And this whole notion of pure intuition, reine Anschauung, in Kant is very important for his theoretical philosophy, because reine Anschauung is the concept needed to explain what synthetic a priori judgments are. Yeah, and I mean, this is like the important Kantian idea that there are not only like synthetic a posteriori judgments, empirical judgments, or on the other hand, analytic a priori logical judgment, but something else, a third kind of thing. Yes, and basically there are like 3 fields in which we find synthetic a priori judgments, which is like mathematics, pure natural science, and metaphysics. So mathematics is quite important for Kant to argue for the possibility of synthetic judgments a priori. So already in the introduction of his critique of pure reason, he presents an argument in favor for the synthetic a priori nature of mathematics and against the supposed analytic a priori nature. So here in my talk, I always have on my slides the German original and like the English. That's also the reason that I have like 51 pages. So don't be worried. So yeah, I will read out like the English ones because probably you don't all understand German, but in the discussion, if you like, we can go back to the original. So here in the introduction he writes, all mathematical judgments without exceptions are synthetic. We might indeed at first suppose that proposition 7 plus 5 equals 12 is a merely analytic proposition, which is something most people held at this time, like even empiricists, and follows by the principle of contradiction from the concept of sum of 7 and 5. But, and now he presents his own arguments against the thesis that mathematics is analytic. If we look more closely, we find that the concept of a sum 7 and 5 contains nothing save a union of the 2 numbers into 1, and in this no thought is being taken as to what single number may be which combines both. The concept of 12 is by no means already thought in merely thinking this union of 7 and 5, and I may analyze my concept of such a possible concept as long as I please. Still, I have never found the 12 in it. In this example, we see that Kant's notion of analytic statements is quite complex. So analytic statements are such statements which do not rest on Anschauung. This was not really the topic of a thing just quoted, so this comes when he positively speaks about the knowledge source of mathematics. But there are also like other things which define analytic statements, namely that they can be proven by the principle of contradiction, something he just mentioned, and then that they do not extend our knowledge. So that when we think 7 and 5, we should already, in a way, think 12 in order for such an equation to be analytic. And finally, that such statements have like the form SSP, a syllogistic form of the predicate term already included in the subject term. So much about Kant, you probably already knew. This is a reminder to talk about Frege. So Frege thinks that Kant has defined analytic judgments too narrowly, and as a result underestimated the value of analytic judgments. On the basis of his definition, Frege claims the division of judgment analytic and synthetic is not exhaustive. The reason for this is, according to Frege, that Kant had a too simple, naive view on how concepts are built from other concepts. So here he explains how concept building works according to Kant and why this is trivial. So if he writes, if we represent the concepts of extensions by figures or areas in a plane, like here, man and unmarried, then the concept defined by a simple list of characteristics corresponds to the area common to all the areas representing the defining characteristics. In this case, bachelor is defined as being a man and being unmarried, and this is like the area common to both men and unmarried, and so this is like the representation of the definition of a bachelor. It is enclosed by segments of the boundary lines, so here's a segment of a boundary line of unmarried, here a segment of a boundary line of man. With a definition like this, therefore, what we do is to use the lines already given in a new way for the purpose of demarcating an area. But what he does is more complex. The more fruitful type of definition, he says, is a matter of drawing boundary lines that were not previously given at all. So if you look, for example, on the definition of prime number, to take a more like rather simple example of like a complex definition, you do not have concepts of the same type in the definition like you have in the defined concepts. So prime number, just like bachelor, is a first order unary concept. But prime number, unlike bachelor in this definition, is not made out of first order unary concepts, but of concepts of different order and arity. So we have like the extension quantifier, which is a second order concept, like the factor relation, which is binary. So the whole image of like having circles and then taking the union area does not work at all. So because the things falling under concepts, the extensions of concepts like factor or existing are of a totally different kinds than the things falling under the concept of being a prime number. And from this, Frege concludes that we need a different definition of analytic statements in order to have like a division into analytic and synthetic judgments, which is complete. So he, like Kant, maintains that analytic statements do not rely on Anschauung, and that they can be proven by the principle of contradiction, so that they are logical. But he crosses out that they do not extend our knowledge, and that the predicate term is included in the subject term. So in Frege, unlike in Kant, we have analytic judgments which extend our knowledge, which is very important for Frege's logicism, because he wants arithmetic to be knowledge extending, but on the same time logical and thus analytic. So Frege has like the idea that we do need Anschauung in arithmetic because we can use logic, namely complex logic with complex conceptual formation, and thus can have like derivations of analytic judgments just from basic laws of logic. However, at the same time, Frege maintains that geometry does rely on Anschauung. In the paragraph following, we just quoted paragraph 88, namely paragraph 89. To do the math for you, he claims that I consider Kant did great service in drawing the distinction between analytic and synthetic judgments. In calling the truths of geometry synthetic and a priori, he revealed the true nature. And if we look at the paragraphs 10 to 14 in the foundations of arithmetic, we will see that Frege in fact presents arguments in favor for geometry being of a different epistemic nature than arithmetic, and, this is also important, than like empirical science. So there is something Kant-like thing which is like neither logical nor purely empirical. And that's what I want to look into. So here in paragraph 13, he presents like one argument in favor of like a certain non-logical and non-empirical nature of geometry based on the nature of geometrical objects. One geometrical point considered by itself cannot be distinguished in any way from any other, The same applies to lines and planes. Only when several points or lines or planes are included together in a single intuition do we distinguish them. So a point as such does not have any specific properties. You can just speak of like two different points if you have like one intuition, and then these are distinct. And from this, Frege infers that there is like a specific way of reasoning, which is specific for like geometry. In geometry, therefore, it is quite intelligible that general propositions should be derived from intuition. The points or lines or planes which we intuit are not really particular at all, which is what enables them to stand as representatives of their kind. So because geometrical objects have this weird nature that they are not really distinct, like at least with elementary objects, we can use like one construction to prove a general statement. And this is kind of an idea we also find in Kant, the Brief of Pure Reason, in a chapter called Transzendentale Methodenlehre. Here he contrasts philosophical reasoning to mathematical reasoning and the knowledge we gain thereby. So he claims philosophical knowledge considers the particular only in the universal, mathematical knowledge the universal in the particular. And that's really like the idea we just found in Frege. So we also give like the example of we are constructing like a figure in order to prove that the inner triangle sum is always 180 degrees. And then argues, okay, and now we can like infer like this like generally, whereas like in philosophical knowledge we argue logically, and we can start with a general statement and only infer something less general. But Frege differs from Kant insofar as he thinks that the same does not apply to arithmetic. So for him, arithmetic is more like philosophical knowledge. His argument is that numbers are different from points, lines, and planes because each number has its own particularities. And an example for this he gives like in paragraph 10 in quoting Leibniz. An even number can be divided into two equal parts, an odd number cannot. 3 and 6 are triangular numbers, 4 and 9 are squares, 8 is a cube, and so on. So these are like the particular properties he thinks about. To what extent a given particular number can represent all the others, and at what point its own special character comes into play, cannot be laid down generally at once. So you cannot, from like one equation, infer something about numbers in general. Thus, Frege, this indicates that arithmetic has a different epistemic nature. Must be like, must be derived from logic. In paragraph 14, when he goes on to present even like another argument for like the non-empirical, non-logical nature of geometry and the logical nature of arithmetic. He explains the wildest vision of delirium, the boldest invention of legend and poetry, where animals speaks and stars stand still, where men are turned to stone and trees turn into men, the drowning haul themselves up out of swamps by their own top knobs. All these remain so long as they remain intuitable, still subject to the axioms of geometry. So the idea is that unlike in the empirical science, we cannot kind of envision something, have like an intuition of something, even like imagining something which is not in accordance with geometrical axioms. So in a way, geometry is more general than like the empirical science. On the other hand, it's different from like true completely conceptual thinking, logical thinking, because for the purpose of conceptual thought, we can always assume the contrary of some one or other of the geometrical axioms. Yeah, keep in mind at this time. Alternative geometry like non-Euclidean or non-Archimedean geometries were developed, so Frege was well aware of that, without involving ourselves in any self-contradictions when we proceed to our deductions, despite the conflicts between our assumption and our intuition. The fact that this is possible shows that the axioms of geometry are independent of one another and of the primitive laws of logic, and consequently are synthetic. And he proceeds to argue that in arithmetic this is different. In arithmetic we cannot negate one arithmetical axiom, and thus this one is logical. So until this point, I think it's kind of persuasive, maybe. Frege had like a certain picture of like geometrical knowledge and pure intuition. But one big weakness, I think, of Frege is that he does not really provide a good explanation of solution of how we should deal with the fact that now, unlike in Kantian times, we have like different geometries, and it's not evident in a way which one is kind of the logic of our intuition and our space and so on. Yeah, sorry, this is like another slide that I just wanted to visualize like this hierarchy of logic and geometry, of which an alternative can be conceptualized, and physics, which always, even in their thinkable alternatives, relies on geometry axioms. Yeah, but to come back like to a point I just tried to make. So the only argument Frege presents in favor of like Euclidean geometry is purely dogmatic. So he says, okay, Euclidean geometry has maintained an undisputable reputation for more than 2,000 years. So yeah, we cannot consider it to be false, and thus we must consider non-Euclidean geometry to be a pseudoscience, the non-Euclidean axioms to be false, which is, yeah, not really a satisfying solution and not really philosophically deep in any way. So to conclude my part on Frege, so Frege has a wider notion of analyticity than Kant, but Anschauung remains crucial for the demarcation of geometry and arithmetic. And Frege has something like pure intuition in mind, at least, because he makes a difference between geometrical and empirical source of knowledge. In geometry, a general statement can be proven by string construction, while we cannot prove something general by just one single observation of empirical objects. However, Frege does not really present a good argument for like the Euclidean nature of our intuition. And he also doesn't even really use the distinction between Ding an sich and Ding der Erfahrung, thing itself, and thing of experiment, the thing we experience, yes. So, yeah, it is hard to see like what his solution is to the problem alternative geometries posed to like Kant's presentation. So his conviction that Euclidean geometry is a true science is kind of purely dogmatic. Yeah, and I think, and it's kind of what I argue in my latest paper, that Hilbert has a more satisfying way with dealing with his issues. Though Hilbert's philosophy, if you want to use that term, goes through like many changes. So even in the 1890s and then again in the 1920s. So in the very beginning of his career in the 1890s, he has more like a naive empirical point of view. And my Kant is not an empiricist. So here in a lecture, he claims that one needs nothing beyond purely logical thinking when I occupy myself with number theory or algebra. So it's like logicism. Though with logicism, yeah, it's just taken over from Dedekind. So he quotes Dedekind a lot. Hilbert does not exhibit any own logical research at this time of his career. With geometry, he claims it is totally different. I can just as little comprehend the properties of space from mere thinking as I can recognize the basic laws of mechanics, the law of gravity, or any other physical law. Space is not the product of my thinking, but is given to my senses. And yeah, so geometry, for instance, empirical science, and this is a common idea among mathematicians, something also Gauss claimed, who also had the idea that arithmetic is somehow analytic, but geometry is an empirical science because there are many alternative geometries, and Gauss had the idea that we experimentally could choose the geometry of outer space by just measuring like very big triangles in space, because there the difference to 180 degrees would be big, because like the bigger the triangle is in hyperbolic geometry, the bigger is the difference to 180 degrees. And in this way, we could prove, for example, that space is hyperbolic or is Euclidean. Yeah, and at this time of his writing, this seems something Hilbert shares, endorses. But this changes already some years later, after he came in touch with Hertz. So here in another lecture on geometry, he claims that no experiment can force us to acknowledge hyperbolic geometry, which is contrary to what Gauss claims. Rather, even if the angle sum of a triangle appears from experiments to be smaller than pi, it is always possible to get by with the usual Euclidean space, and then he kind of explains how, but very dense and incomprehensible in a way. Still, it would be simpler, more transparent, and would need fewer axioms if, under these circumstances, we were to postulate the hyperbolic nature of space. So an experiment cannot really force us to acknowledge this, but we can decide to use hyperbolic geometry because this is more transparent, needs fewer axioms, it's more convenient in a way. So what happened? So Hilbert read Hertz, Principles of Mechanics, and in several lectures he renders like his own axiomatic approach in using Hertzian vocabulary. So in this lecture, for example, he introduces this with like utilizing expression taken from Hertz in the introduction of the Principles of Mechanics. We could formulate our question as follows: which are the necessary and sufficient conditions to which one has to submit a system of things, so that every property of these things can be equated to a geometric effect and vice versa, so that as a result, these things are a complete picture of a geometric reality. So this is a very dense quote. But we see that there are for Hilbert kind of 3 layers. So we have like the necessary and sufficient conditions. And from the context we get that these are like the axioms. Then we have like the system of things which are submitted to these conditions. And these system of things are a picture of like the 3rd layer, geometrical reality. Yeah. So what does this mean? So the conditions are like the axiom, and the system is like a word he took from Dedekind, something which roughly means set. So Dedekind's notion was a bit different. So there are there's no difference between like a set with only one element and the element itself. but other than that, it's more or less like the same. And in the Foundation of Geometry, like the book from 1899, the Festschrift, Hilbert in the beginning introduces 3 systems of things, which are called point, lines, and planes. But from the text we get that this is not what he means by geometrical reality, but these formally introduced things are just a mere picture of the reality. And the word picture is taken from Hertz picture theory. The first mention here directly at the first page, we form ourselves pictures or symbols of our external objects, and the form which we give them is such that the necessary consequence of the pictures in thought are always the pictures of a necessary consequence in nature of a thing's pictures. So idea is just like pictures is kind of our theory, and if from our theory we can entail that if this and this happens and that happens, this has to be something which also is in accordance with our observations. So that our theory can be verified experimentally. And here in his further explanation, a kind of Kantian element enters. He writes that the pictures which we here speak of are our conception of things. The things themselves, they are in conformity in one important respect, namely in satisfying the above mentioned requirement. That's the requirement I mentioned. For our purpose, it is not necessary that they should be in conformity with the things in any other respect, whatever. So, and like Kantian is this in this way that, like, the things from which we form pictures are kind of like a Ding an sich, a thing in itself. So we don't really have to, or don't really can, like, understand this kind of object, but only have like, but only with our kind of theorizing about it, which is kind of similar to like Kant's thinking that we only the only thing that represents us is the thing in experience, which is kind of formed by our Anschauungsform and categories, constituted by them. Hertz considers like different theories of mechanics in his book. That's why it's called this way. And then he presents like different criteria by which these pictures, these theories can be evaluated, which is consistency, so that no contradictions appear. It's like a necessary condition. And then it is correctness, so what is in accordance with like our observations, so that we can really verify it experimentally. This is like the condition already expressed with this first introduction of Bild, which I was presented. But when Hertz claims that there still might be different theories, which all might be consistent and correct, and then we still need the criteria to choose one, and this criteria has like the umbrella term appropriateness, Zweckmäßigkeit, so things like simplicity, but Hertz claims that we have like no one objective criteria to decide what is the most appropriate one, and this might depend on a context. And in this light of this reading of Hertz, we may better understand Hilbert's remarks on the Gaussian experiment. So hyperbolic geometry and Euclidean geometry can this way be seen like two pictures of reality. But one, namely hyperbolic geometry, would in this context be the more appropriate one because it's simpler, more transparent, needs fewer accents, etc. So Hilbert at this time, so when it comes to arithmetic, he has like the more or less the same view like Frege, but less sophisticated because he exhibits no own logical work. But when it comes to geometry, it's kind of a better solution of how we should deal with the situation that we had like different geometries. So he kind of has a neo-Kantian position, which is Kantian insofar that the object of knowledge depends or is constituted by the subject of knowledge, we, himself as the one who have this knowledge, by our theory or as Kant, as Hertz says, or build. Neo-Kantian, different from Kant, is this insofar as this is kind of a flexible a priori. So this theory may change also under the impression of new empirical data. And this is something which happens in the late 1910s and early 1920s. So what happens, like the theory of relativity, which made it kind of necessary to adapt our geometry to this physical theory. One would think that Hilbert would pick this up and say, okay, this really highlights what I was right in my presentation of geometry, my Hertzian grasp on geometry. However, like in the 1920s, we find claims which more sound like naive beginning of 1890s Hilbert. So here in another lectures on physics, Hilbert claims Kant certainly overestimated the role and the scope of a priori. As Gauss already recognizes, the statement that the sum of angles equals 2 right angles can only be determined and refuted through experimentation. So this seems like a purely empiricist approach. So what happens? I'm not completely sure. So Leo Corey, in a paper already 20 years old, Axiomatic Empiricism and Anschauung in Hilbert's Conception of Geometry, also like looks on Hilbert's notion on geometry and how it changed throughout the years. And he claims, as part of all this, the subtle balance manifested in Hilbert's early writings between empirical and a priori intuition as possible sources of geometric knowledge was finally altered and unmistakably resolved in favor of experience. And I found it really unsatisfying because I think this naive empiricism is like, a less satisfying philosophical position than like this more subtle neo-Kantian Hertzian approach. And I wonder why Hilbert abandoned it, or I asked myself, if Hilbert abandoned it as much as some passages suggest. So among other things, I made a bit of reading in the Nachlass, so in the unpublished things we find, for example, in the archive in Göttingen. Sorry. Here, for example, we find a note on this book by Hans Reichenbach, Relativitätstheorie und Erkenntnis a priori. I think translation is more like self-explanatory, theory of relativity and knowledge a priori. This note looks like this. So he first takes some notes about what Reichenbach says on time, and then he comes to space and geometry. And when he sums up that there have been like 3 different ways of dealing with the question which geometry is kind of the right one. The first one is, here he says, no. He writes Kant. I don't know if you can see it. that is like that it is anschaulich, intuitively evident that Euclidean geometry is the one which is in accordance with reality. The second one, that since conceptually many geometries are possible, only experiments can decide which one is true. And the third one, that geometries are only schemas, so that it makes no sense to call geometry true or false. So like 2 would be like the Gaussian variation, and third is his own one in the later 1890s. And then he finished with like the general theory of relativity, claims that that Euclidean geometry is wrong for reality. So, and you see, like Euclidean geometry is for reality false. It's a sentence he really like highlights. And yeah, this is like the rest of a note. When he sums up like Reichenbach's theory that mathematical sentences are as such neither false or wrong, but we can use mathematics to express like physical statements, which are statements about reality and thus can be wrong or false in a way. And what we make a mapping of like the mathematical theory onto like physics, and then we can show if a physical theory is true or false, and like comes up with like contradictions, and yeah, this is a good theory of reality. And yeah, Reichenbach's claim is okay that now in the present situation, there's like only one mathematical theory which is appropriate in the context of theory and relativity, and this is hyperbolic geometry, and so far you can call it right, and also something like Schlick holds. So from this, it might be that Hilbert, I mean, at least he was interested still in this topic of the role of a priori, and that maybe this claim is to be read more as the statement that there's like that the debate is over, which geometry is the geometry which describes our reality for the moment, because there's only one solution which makes sense and order, and that this is like that our space is curved. Yeah, also like the same manuscript in the archive also contains this very short note on Hertz. So in a way, he kind of still thought about Hertz or even read him. Second, like context is like in this lecture where he claimed that Kant overestimated the role of a priori, and that the true geometry can be chosen empirically. He writes quite a lot about Poincaré, and in a very mean way. So Sunday night we had this discussion about Frege, and that he sometimes has this very polemic and mean writings. And when I first read this passage, I had the impression that this sounds just like Frege. So Poincaré, in a way, at least according to Hilbert's reading, claimed that we still can apply like Euclidean rhetoric to a theory of relativity. Maybe Gerhard Heinzmann can say more about this. And then he gets very polemic in saying, according to Poincaré's analogy, it would be as if someone slipped a pancake recipe between the axiom and then thereby to establish the importance of the art of cooking for logic. Conventionalism had led to utter confusion. The ultimate consequence of Poincaré's point of view is that there are not any laws of nature at all. Well, in the very same lecture, he also writes about, or teaches his position on arithmetic, and this is also interesting because it shows that he does not have like a logical empiricist view, because we a priori enters the stage of mathematics again, but now not in geometry, but in arithmetic. So like the first traces of his finitism he later presents, 1925. I believe mathematical knowledge ultimately relies on a kind of intuitive insight, anschauliche Einsicht, and that we even need a certain intuitive attitude, anschauliche Einstellung a priori, to construct number theory. And yeah, this is what later presents in Über das Unendliche, where he claims that, sorry, here the translation by Banasov and Putnam, that mathematics, especially arithmetic, never be grounded solely on logic. Consequently, Frege's and Dedekind's attempt to do so were doomed to failure. So we have seen, like in the 1890s, he just followed Dedekind. Now I think he's false. Reason is that a precondition for using logical deduction and carrying out logical operation is that something must be given in conception. Is the translation, I don't know, it's so good, Vorstellung. Certain extralogical concrete objects which are intuitive as directly experienced prior to all thinking. And for logical deduction, we need every aspect of the object, properties, and so on. So we must have like one Anschauung. We have to kind of be able to manipulate them by seeing them all at the same time, having an overview, having an intuitive grasp on them. I mean, Andy already summed up this finitist position of Hilbert yesterday. So his idea is we start with Zahlzeichen, number signs. And I think this shouldn't be necessarily a 1, but just a stroke. So 1 stroke for 1, 2 strokes for 2. Yeah, we can directly manipulate them and carry out like mathematical operations to put them together to make addition, for example. When we refer to them by like concrete number signs like 2 or 3 in Arabic numbers. Algebra is then introduced by introducing what it calls ideal elements, so different signs, and then we need to prove the consistency of this extended ideal theory, because we don't still have grasp on like this primitive like number signs and don't have an intuition of them. And this is kind of maybe one of the first time, maybe not, but unlike Frege, he really takes into account that in Kant we do not just find this idea of construction in the geometrical sense, that we really have like the object, the concrete object represented by our drawings, but that Kant also thought of construction in a more abstract way when it comes to arithmetic, especially algebra. So when we just introduce like notation to represent like magnitudes, but also operations, and then we exhibit in Anschauung our operations, we manipulate our signs, and this is for Kant also a kind of construction, something which needs Anschauung, something he calls symbolic construction, which is kind of different from geometry insofar as we do not construct the object itself, but have like more of a roundabout way of doing so. Yes. And I'm not sure how much like finitism is like really a completely Kantian project, but I think he really appreciates the idea that Anschauung does not necessarily mean some drawing of figures, but there's like this mechanical manipulation of operations, which was like, what is, I think until the present always like associated with something like non-intuitive, is for Kant also something intuitive. So it is intuitive because we do not reason conceptually, but we simply manipulate and therefore need science. So to sum up this part on Hilbert. Yep. So Hilbert in his later theory seems to think of geometry as an empirical science. However, I don't see that he completely rejects his former Kantian conception. So it might be that he rather thinks that the only geometry is correct and appropriate to pick up like this Hertzian terms of picture theory of outer space are in the context of Einstein's theory of relativity, or is in the context of Einstein's theory of relativity, the hyperbolic geometry. And Anschauung, especially pure Anschauung and a priori, enter the stage again in the context of arithmetic and his finitist approach. So now I'm at the end. Thank you very much for your attention.
Okay, thank you, thank you very much, Tabea, for this very stimulating talk. Questions, Gerard?
Yes, I'm very astonished about Hilbert's position, and as empiricist, was he not conscious as to measure something, you should have a solid body? That's it. I mean, this was Poincaré's argument against the empirical attitude that geometry is empirical science. If you measure something, you should make a movement, and then you should be sure that if you're making a movement, that the measure is invariant.
Yeah.
He must be conscious of this.
Yeah, he is conscious of a measurement, but he thinks that the Euclidean metric Poincaré uses is kind of inappropriate. But I'm not so sure whether this is a good criticism. Yeah. I mean, in curved space, we have to we have a different measurement than when we have a flat space. So, and he seems to think that Poincaré kind of uses Euclidean geometry or sneaks in Euclidean geometry by this metric. But yes, maybe he misunderstood him. Yes.
But you should presuppose something to measure.
Yeah, but he thinks you have to presuppose something else.
I cannot understand him. Okay.
Yeah, I mean, measurement.
There must be another argument. I'm very surprised about this. Can you understand it?
I mean, it's all very short, but I mean, the problem is that I don't know enough about Poincaré to really understand him. But Hilbert argues that we sneak in Euclidean geometry by using Euclidean metrics, by the way of measuring, which kind of presupposes Euclidean geometry, and that we shouldn't do so. But I can send you the pages. Maybe you have a good see a better argument on Hilbert, or can tell you that Hilbert is wrong.
Okay, Romain.
Yes, thank you very much. That was really interesting and insightful. I didn't know also about Hilbert's position in the end, that it was that empiricistic. But I have a question, because I had a hard time following your storyline on slide 17, 18. It's about paragraph 13, 14 of the Grundlagen.
Yes. Mm-hmm.
And you said something, and this is true. I mean, there's really a parallel way in which Frege treats the strange singularity or particularity of geometrical objects. So, in the one hand, they are singular, but not really determined and not distinct from each other. They don't have these Eigentümlichkeit that you have in numbers, which makes them somehow general. And it's pretty similar in Kant, in the Methodenlehre. So that's fine, but I think then what Frege also says in the same paragraph, and you quoted it, is that numbers are different in that they are really individuals with fully determined properties that that marks or that individuates every single one of this huge infinite series. So it's and then you could say, well, but Anschauung is something particular. So you have a particular object, and an Anschauung could be totally determinate. So in a certain sense, this determinacy or object individuality of natural numbers does not really speak for them being only or not accessible by Anschauung. So you could say, well, that's not, well, that's even a better object of Anschauung than these half singular, half general objects of geometry. And I think he's, you're right that he's dogmatic here about geometry, but his actual point is that arithmetical truths are analytic because you can show that they that you can conclude them from the primitive laws of logic, which are truth. And if you were able to do that with geometry, with geometrical axioms, then all the other considerations would be annihilated. Then it would also be analytic. And the thing is, you just can't do it with geometry. It's not something he shows. And he tries to show it for arithmetic that you can do it. So.
Yeah, the thing is that in the Grundlagen, he does not yet have like a deduction of arithmetic from logic laws. So what he do is to motivate a certain conviction, also to show that, maybe also prove to himself that the whole project is worth pursuing, I think. I mean, it took him many years. So you might have some other arguments in favor for this project to work out well. What you said about numbers, in a way it's correct, but I think one could say they are better objects insofar as in their B in particular, there would be good candidates for empirical objects. But he presents pages of pages showing that this solution, this million solution is bad. I mean, he's very polemic there in his Pfefferkuchen-Arithmetic. And I think this not being like really particular is something which is in his point of view, and I think maybe also in Kant, something particular for objects of pure intuition, which have like a kind of a weird objective status. Because they're purely constructed by ourselves. Did I answer all the questions? We had like many layers of.
Yeah, sorry.
Okay, yeah.
No, you answered everything. Thank you.
Okay.
Start the closest. Gemma.
Conveniently, my question's about the same slide. So I was just wondering what is meant by kind in this context. Is it kind as a point, line, or plane? Or is it something more specific about, say, classification of different kinds of points, lines, and planes?
Of that kind. Ihre ganzen Gattung. I rather think like here it's really point, line, and plane. I mean, point, line, and plane are something indistinguishable from each other, except from an intuition. I mean, it gets more complicated when you talk about triangles. I mean, when they can have different properties. So I would really like this.
So there being, in this case, three kinds.
Yes.
Okay.
Yes. But
Thank
he's
you.
not very explicit about this, but I've always thought that this is what he means.
Yeah, it's interesting just given his knowledge of projective geometry and duality, where the kind is interchangeable to some extent. I mean, that you can play with that. But maybe it's just, maybe I'm trying to read too much into a casual usage of it's not a text about geometry necessarily.
Yeah, I mean, it's a text about geometry, but not so concrete. I mean, he has like this very dark passage about projective geometry in paragraph 26. So he was, he was aware of it, but the more I'm thinking about it, the less clear it becomes. So I cannot really tell you what the role of projective geometry is in Cantu, is in Frege. So I mean, there in paragraph 26, he seems to say something that we can also have like kind of a conceptual grasp on what's going on in geometry, which is also important for him to say that like alternative geometries are possible, and so it shouldn't be possible to derive it directly from logic. But then you need like a kind of intuition, but how this works exactly in this kind of thought experiments where like two kinds of aliens in a way who both have like a projective intuition, and when they talk about points and lines, and the one means points and the other means lines, and so they cannot communicate to each other. And then he says something about like our conceptual grasp on geometry and intuition, but then it becomes kind of weird. So he thought about this kind of stuff, but I don't think that it plays a role in the notion of kind here, because he doesn't go back to this notion of kind at all, and especially not in paragraph 26.
Thank you.
Okay, Dirk.
Thank you, Tabea, for this very great and nuanced talk. I like it a lot. I have two questions. One is, you described the transition in Hilbert's notes from 1891 to 94 by emphasizing that he read Hertz in between. And I admit I haven't paid attention much to Hertz, because for me the transition is that he read Pasch, which is also discussed in the Maya Hallett thing. So I was wondering whether, you know, what you think, whether you think that Hertz was kind of more important, or that, or what the relation between these two influences is, basically.
Yeah, I mean, he mentions Hertz and I think also Pasch in the same lecture. Yeah, I just think like for this specific emphasis here, this non-empirical, a bit neo-Kantian approach, that there is something which comes from us, the way in which we constitute objects, that this is a Hertzian influence, this particular thing. But I mean, his whole presentation, this whole more axiomatic approach, is probably also influenced by Pasch. But yeah, I was trying to think about this Pasch-Hilbert relationship, but yeah, there is some things in Pasch which yeah, I still struggle with. So maybe you can explain it to me at some point. So I feel we will come with Pasch again, because I think you already like asked me about Pasch in two other talks, and I never had a really good answer. Yeah, but I just aware that he read Pasch, but to really like tackle down like the influence is yeah, something I didn't really achieve until now.
Okay.
Yeah.
Well, maybe we can figure that out together at some
Yeah.
point. But I had also a question about Hertz now, and on slide 31, you quoted him, where actually the German quotes is about innere Scheinbilder, and you just reduce that to pictures or a builder.
Yeah,
so I was wondering whether you think that the difference doesn't really matter, or if there's more behind that.
Yeah, I'm wondering. I thought I took this from the official translation, but maybe I omitted kind of a word. But the thing is that he uses innere Scheinbilder there, and then he never came back to Scheinbilder, but only talks about Bild. Yeah, and I think like a first approach to show in which direction it goes, namely that our pictures are not like real, like mirroring picture of the object, but something which is not the thing that is there, but something we have in which differs kind of the thing which is pictured. Yeah, but you're right. I should, yeah, go back to the translation and maybe. Yeah, insert here another word. Thanks.
Okay, Andy?
Thanks, Tabea. I wanted to come back to the subject that Romain was mentioning, the particularity of the numbers, because for Frege this is something that's quite striking, that he tells us that each individual number has so many individual properties of itself. The number 3 is prime. The number 4 is not prime, but there are each so many different properties. And I wonder then, do you think that for Frege, of course, he'll go on to tell us that numbers should be defined in an analytic way. That is, he'll give us a definition of number that's purely conceptual. But do you think that Frege thinks we can have Anschauung of individual numbers? I know that he doesn't think that it is necessary for the justification of propositions that we have Anschauung.
Mm-hmm.
But does he believe that it is even possible? And for that matter, does Kant believe that it's possible that we could have of a particular number to take it in its entirety with all of its infinite complexity in a single moment of presence? Is that something that's part of the Kantian or Fregean picture of Anschauung?
Yeah, with your first question, I'm not sure he doesn't really talk about it. I mean, in a way, his hierarchy is so that you would rather say, okay, here we need only logic and not Anschauung. So there is room for the interpretation that you have like an Anschauung of number. But if you would really say that you have an Anschauung of number, or more we have like an Anschauung of a good representation of number, I'm not so sure. Yeah, maybe I should carefully read like his first paragraph where he talks about Kant and his representation of points. I mean, with Kant, the whole thing is more subtle. I mean, Frege's representation of Kant is not really fair. When Kant talks about numbers in like this, when he talks about schemas, so that we have like a schema of a number, which is kind of our representation, but he does not really think. So he talks about we can take our fingers or points, and when Frege mocks him for like, okay, you cannot have like 1,500 fingers or so. But I think he misunderstands him. And when we look at what a schema is, when it's more like an algorithmic procedure of just adding another thing, and taking points or fingers is just one representation of this schema. And no, I don't think that Kant would say, okay, we look at like 4 points and then we see all the properties of 4 and 1 intuition, if this is what you asked. But we still have to make judgments. I mean, this is the point in arithmetic also being synthetic. The argument was that in considering 4, or in considering 2 plus 2, we're not just already considering 4, but something else has to be done. And this can be like, we have to do something, a construction, so that we like 2 points and two other points, and when we have like this relation between 2 and 4. And I also wanted to add, even though this was not your question, that I think like that the Fregean argument is somehow flawed in this way that, okay, he says we can only distinguish a point, for example, in putting it kind of in relationship to other points. And we can say, okay, this is this point, this is that point. But when we think about what special properties numbers have, their properties is that they have a certain relationship to other numbers. So we can only individuate numbers in putting them into relationship to other numbers. And this is kind of very similar to what's going on with points. Well, in a way, maybe slightly different, but because they are, there's like one sensible relation of ordering numbers, and you don't have the same kind of order structure of geometrical entities. But in a way, it's like the same. They only have properties in their relationship to other abstract entities. But I don't. Did I answer the questions you did actually asked?
I think so in a way. But what's interesting to me is that for Frege, the numbers themselves have, well, for anyone, numbers themselves have such variety. Mm-hmm. Each individual number, mm-hmm. and yet there is a sense in which that variety isn't accessible to us except through analysis. Mm-hmm. Except through somehow the conceptualization of this individuality. Mm-hmm. And that's interesting, right? Because you might have thought that in ordinary life, when we come to know someone, mm-hmm. we do so, we try to approach them as an individual, and we try to take in their individuality through the senses. And that any attempt to conceptualize that individual puts us at distance from that individual. But yet, somehow, with arithmetic, there's a suggestion that that this relationship is inverted, that a sensual relationship with the numbers fails to reveal their inner depths, but instead we need to conceptualize them, and that's interesting to me. And I think Frege is pointing us in that direction, because the development, he raises that in paragraph, is it 13? Yeah, and which is trying to lead us then by later in the Grundlagen that we need to think of we need to define each individual number in a analytic, in a conceptual way, without reference to intuition. And I think that's interesting for thinking about numbers at all, and also about what intuition is supposed to be.
I mean, Kant would say we don't need analysis, but also like synthesis. But in calculating, we synthesize like to
but
do something.
But we do more with numbers than just calculate. Yeah. So somehow for Kant, it's ignoring that numbers, they're here to put it in Kantian terms. They're worthy of respect in their own right, not just as things to be used for other purposes, but rather each individual number merits contemplation and knowledge of itself. But maybe Kant is not a mathematician, and maybe he never thought about the number 7 as something that needed its own life.
Yeah, but how do you contemplate, now I have it, about numbers without kind of putting them in relationship to other numbers? That means in the end something like calculating. I mean,
you're right.
You recognize the prime number nature of 7 when you kind of divide 7 by 6, 5, and so forth, or less numbers if you have like a better algorithm, and see that it cannot be divided by other numbers except 1 and 7, and then you recognize this nature. So I think what Kant wants to say, even he's not a mathematician and his conception of mathematics may have flaws, is what we have to do something, and this doing something for something synthetic.
Yeah, I think that point is well taken. It's just that I still might be interested in a particular graph, for instance, or a particular number, and want to know the properties of it. And while those properties are relational, as you said, with respect to other numbers, it's not that I lose my focus on that original number itself in thinking about its relational structure. And I have a sense that for Kant, this is not part of the picture. That no, I could never be interested in just one number. Why would that be? But we see mathematicians all the time being concerned with one particular graph or one particular function, and it seems that this is lost in the move towards generality here that comes in Kant. And interestingly, for Frege, who we think of as being logicist, and logicism being a move towards the general, gives us another way to think about particularity.
Yeah, I mean, that's also something I thought striking the first moment, when like he highlights the particularity in order to defend a very general approach. Yes.
Okay, do we still have enough time? Wait, is it a follow-up you want? Or is it Okay. Okay, so let's try to be just short question, short answer, so that you can close.
And I wanted to come back to your discussion about the fruitful definitions, right? Because I've been very interested in that passage also. And kind of rhetorically, you presented the view that Frege criticizes with these kind of Venn diagrams, right? And then his own view with a definition of prime in terms of quantifiers. But of course, you could also present married as, there exists a y such that x is, married to y and so on. So you could also put that into this kind of more different format. And you could also draw a Venn diagram with divisible by 1, divisible by itself and divisible by something other than 1 by itself, and then see that the prime numbers are a particular spot in there. So, but your discussion actually made me think that it's actually not about the definition, because in a sense what I just said is that you could, define them both in a similar way, but it's more about the analysis. Well, how do you analyze, or what you take as your basic, and maybe that's the thought that I had when listening to maybe Frege's discussion about definition is kind of it's not about the definitions. It's about kind of what you take to be the basis of your analysis.
Yeah, so I mean the context in which I also discuss this in my thesis, where the discussion is much longer, is the idea that Frege's logic is so fruitful in a way because you only need this, it's between 8 and 10, so it changes over time, basic concepts, and you can form this variety of concepts like being a prime number and all these mathematical concepts. So you can even potentially define an infinite amount of new concepts, because the Fregean concepts have different order and arity, and so they allow for much more combinations when if you think of the basic concepts of just being for example, all unary and first order, or also something else. And this discussion also pops up in Frege when he discusses Schröder and Boole, because their logic was sophisticated when the Aristotelian logic Kant had in mind, but still, and this is one other paper I also wrote about Frege and Schröder. In Schröder, you also always have one level, one order, so you can reinterpret things in a different order and arity, but you never can combine different order and arity. And Frege very much highlights also in the Schröder-Boole context that his logic is made for concept formation, and the Schröder-Boolean one is not, and I think he's right about this. And the Venn diagram, so this is not my own rhetoric, this is also Frege's rhetoric, not in the foundations, but in the discussion of Boolean logic, so Rechnenlogik, meine Begriffsstoff there. He has this Venn diagram for a time, and he criticizes Schröder here.
Okay, and the last question about Bruno, and then you close the session.
No, actually just as a follow-up. I wanted to ask the question at first, but so I believe, I will just make it very short. I believe that for Frege, analytic judgments can extend the knowledge because of the Sinnbedeutung distinction. So so identity statements can be informative, even though they are both things are extensionally equivalent, but they don't have the same meaning. And here you can rephrase what has been said in terms of prime numbers. You can rephrase it in other words, and of course this would be extensionally equivalent. But you will have gained knowledge because it isn't going to say meaning.
Yes, of course.
And so mathematics can be rephrased into second-order predicate logic, and you will show that these are just theorems of second-order predicate logic. And of course, you can derive them, and so these are analytic judgments, but still, because they don't have the same meaning as the same Sinn as the statement to which to the extensionally equivalent statement that can be rephrased in, you gain knowledge. They are informative because you could not expect that they would be true.
Yeah, but the Sinnbedeutung distinction is just introduced in 1891, and he already claimed in 1884 that arithmetic is knowledge and extensional. And I think that you really need the story complementary to this sense reference distinction, because, for example, you can say bachelor and unmarried equals, no, not bachelor and unmarried, sorry, man and unmarried equals man, and you can say, okay, in a way, these are two different senses. But what Frege wants to say, taking up Kant, is, okay, this is kind of trivial because you just look and see the predicate there. So this is, when you embed it into this theory, it's more it's a more fine-grained story. Yes.
Okay, so let's thank Tabea again. have the lunch break, and we reconvene at 1:30.
Non, non, ah non. J'aime bien ça. Je suis habitué à ça.
que ça se frotte pas sur ta
Oui. Alors je vais mettre là peut-être. Je pense. Plutôt. Non, j'ai pas de note. Ouais, parfait. Merci.
Okay, so thank you everyone. So we are starting our last half day of the workshop, and the first talk of the afternoon is by Romain Büchi from the University of Zurich, and he's going to talk about intuitions as a practice of conjecturing. The floor is yours.
Thank you very much. Good afternoon, everyone. Thanks for having stayed. First of all, I would like to thank Bruno and Yassine for having given me the opportunity to share my ideas here in Liège at this workshop. I've already enormously profited from all the wonderful talks given so far. I've also very much enjoyed the many interesting discussions I had. So many thanks to all of you for your contributions, but also for your kindness. It was really a nice time. Today I will talk about conjecturing and the possible role of intuition within this practice. The question I would like to address is the following: how can intuition serve to rationally form fruitful conjectures, eventually leading to truth? A lot of adverbs and adjectives. They will be explained, or I will try to explain them. So on the one hand, I'm interested in the rational practice of conjecturing, as it was and maybe still is conducted in mathematics. On the other hand, I'm asking about the role intuition may play in this practice and how it can help to achieve truth in mathematical matters. My talk is structured accordingly. Section 2 offers elements of an epistemological account of conjecturing as practiced in mathematics. This includes discussions of necessary conditions for successfully making conjectures and for their having the potential of becoming fruitful. Section 3 introduces basic distinctions to clarify different uses of the term intuition. The aim here is to identify the notion of intuition relevant to our investigation. It is quite a different notion of intuition, especially different from the Kantian tradition, or the notions coming from the Kantian tradition. So I will say a little bit about that. And Section 4 then offers an answer to the question of how intuition may contribute to rationally forming conjectures by discussing one famous example from the history of number theory, that is the prime number theorem. So it's one example, it's a bit paradigmatic, maybe anecdotic, we will see, I hope not. Before trying to answer my main question, however, I should make sure that it is not misguided. And I should also explain why it's worth addressing. Let me therefore begin by answering two possible objections. According to both of them, it would be misguided to grant intuition any essential role within the rational parts of mathematics. So, first, one could object that a statement's potential to become a fruitful conjecture is incompatible with its being intuitively evident. Imagine a group of students with limited knowledge reading a textbook on number theory, and let us assume that the students, while carefully reading the first chapter, intuitively grasp the fact that there is only one even prime number, namely 2. Unable to find a proof in the textbook, the group announces their great discovery as an important conjecture. Statements of this sort will, of course, hardly motivate mathematicians to take the trouble of giving a proof, except perhaps for didactical reasons. But if a statement needs no proof, it cannot become a conjecture worth investigating. Consequently, we should deny such trivial statements the possibility of being put forward as serious conjecture. Similar considerations apply now to statements which still might require some proving, although they seem intuitively evident or at least very plausible. A case at hand is a statement that every simple polygon divides the plane into an interior and an exterior region. More precisely, let P be a simple polygon in a plane R2, then its complement R2 without P consists of exactly 2 connected components. One of these components is bounded and the other is unbounded, and the polygon P is the boundary of each component. While this statement may have been a sensible conjecture to make at a certain point in the distant past, it surely did not have the potential to become a fruitful conjecture. It is not in any way a deep result, and a proof, even a rigorous one, is too easily at hand. If contemporary textbooks contain a proof at all, then again only for didactic reasons, as an occasion to practice the art of proof. To be clear, the same remarks do not hold true for the generalized version of this statement. The generalized version of this statement became Jordan's curve theorem, famously. And the Jordan curve theorem states the same as the lemma above, but for Jordan curves in general. And I don't want to claim that this the statement of the Jordan curve theorem is that trivial or obvious that it couldn't have been meaningfully and seriously conjecturized. But maybe we can talk about this later in the discussion, because there is also the view that it is totally intuitive and even intuitively evident. I'm not so sure about that. Maybe the intuitive evidence or the appearance of intuitive evidence in the general version, the Jordan curve theorem, is due to special cases like this one. And then you extrapolate and you think, well, it's just the same. But Jordan curves can be quite strange entities in their generality. So maybe it's not that evident at all, but maybe we can discuss it later. So what do I make of this first objection against my undertaking? Well, I'd say intuitively evident or very plausible statements like the ones we just considered. 2 is the only even prime number, or every simple polygon divides the plane into an interior and an exterior region. Statements like these do not exemplify the kind of intuition I'm after here. To be established as a conjecture, a statement suggested by intuition must be worth proving or disproving, and not only for didactical reasons. Trivialities do not meet this requirement. Also, the statement should be sufficiently deep and hard enough to prove as to have the potential to spark the interest of the relevant mathematical community. Only then may it increase mathematical understanding and prompt the development of new concepts, methods, and theories. It is very unlikely that these requirements could be met by the sort of intuition about mathematics most humans share. What I'm after, therefore, is what one could call advanced intuition, or the sort of intuition typically invoked by experts in any given field. So I will call it expert intuition, lack of a better name. As such, expert intuition will more likely be fallible, thus non-factive, than the sort of trivialities mentioned in the first objection. So let us now consider a second objection to my main question. First part of the second objection is that there is a long history of separating intuition from discursive rationality. We saw this in the passages this morning from the Methodenlehre. So we have Anschauung on the one hand, what I call here discursive rationality on the other hand, which belongs to philosophy and which will not produce synthetic truths, at least certainly not in the same productive way as in with the Anschauung. So intuition is often understood as the faculty of the mind to directly apprehend truth without recourse to reasons and justifications. And intuitions as products of this faculty are considered self-sufficient and in no need of further justification. Justification in the form of proof or less rigorous argument is not necessary. Either you see the truth or you don't. Justifications, on the other hand, cannot substantially rely on such intuitions if they are to bring certainty about statements, the truth of which is not accessible to intuition. And this, one could argue, is especially true for justification in the most rational of all sciences, in mathematics. It may seem compelling, therefore, to deny intuition any essential role within mathematical contexts of justification. One might concede that intuitions are involved in contexts of discovery, in developing new concepts, forming hypotheses, and exploring possibilities of proof, for example, but in the mathematical proofs themselves, and this is important now, as well as in any other justificational work, intuitions seem inessential and, in principle, dispensable. So that's one part of the second objection. The other one is to say it could be maintained that the philosophy of mathematics can only be concerned with contexts of justification. This has been done. For example, I found really a quotation in Dummett. So if the philosophy of mathematics has an object, and certainly not context of discovery, questions pertaining to contexts of discovery would have to be relegated to other disciplines such as psychology or sociology. And by asking how intuition serves to rationally form conjectures, I'm assuming that intuition indeed has a role to play in mathematical justifications. I grant intuition a key role in conjecturing as a rational practice, a practice that typically allows for, sometimes even requires, justifications. So therefore, one could argue that my question either commits a category mistake by not clearly separating context of justification from context of discovery, or that it fails to be a philosophical question altogether, even worse. So what is my response to the second objection? Well, first I would point out again that the statement is only worth conjecturing if its truth is not evident but open to doubt. Certainly if a conjecture is made, it is because its truth is considered somehow probable, that's true, but it must be conceivable at the time when the conjecture is made that it would turn out to be false. This is why, as I already said, the notion of intuition at stake here must not be factive. Intuitions of the kind relevant to our discussion can lead astray, and sometimes they do. But to be a reliable guide in seeking mathematical truth, intuitions need not be infallible. Even an intuitive conjecture is eventually proven false. Even if it is proven false, it can still have contributed decisively to establishing truth, developing theories, etc. In any case, whether a conjecture based on intuition proves to be true or false, for this to be decided, one must convince oneself or others that it is worthwhile to investigate the truth of the statement involved. And for this, it will sometimes be necessary to corroborate the choice of the statement with arguments before it may be accepted as serious and potentially fruitful conjecture. It is in such contexts of conjecture forming, which I think are clearly contexts of justification, that intuition and discursive rationality come together. just to be clear, I will not discuss the role of intuition in proof. What I will try to show is how intuitions can be part of justifying why certain statements should be investigated rather than others, and how, under the right circumstances, intuitions can help to guide and shape mathematical research. The second part of my answer concerns the claim that the question raised here is not a philosophical one. I believe that to give an epistemically accurate account of the art of conjecturing is a task for philosophy, more precisely for the philosophy of mathematical practice. And there has been this turn to practice in the philosophy of mathematics. This is not to deny that questions belonging to other disciplines may be involved. On the contrary, one task for the philosophy of mathematical practice is to prepare the ground for non-philosophical studies. Philosophy can help, and I think the help is sometimes needed, to clarify the conceptual landscape, dissolve possible misunderstandings, and set out, from an epistemological point of view, set out well-structured accounts of different sub-practices. One of these sub-practices, the one I'm interested here, is conjecturing. Besides that, I believe there to be good reasons against a strict bipartition of mathematical activity into context of justification on the one side and context of discovery on the other. And there are even better reasons, I believe, that speak against the assertion that the philosophy of mathematics should stay out of questions pertaining to discovery. However, to give a forceful account of these reasons, that's not possible here. In this talk, I will pursue the more modest goal of elucidating some cases in which this bipartitioning, discovery and justification, turns out to be misguided or not very helpful. Good, so these are the two objections and my responses. Now let me quickly say something about the general aims of my work on the topic. My main interest is mathematical truth, what it is, how it is achieved, why it is worth achieving. Obviously, the practice of conjecturing has an important part to play in reaching for mathematical truth. And insofar intuition can play a part in forming conjectures, my work is a contribution to the larger question of how intuition may help to achieve truth in mathematics. But maybe more importantly, or what really motivates me at the moment, is that I also believe that conjecturing is intimately connected with the truth conditions of mathematical statements. So what do I mean by that? I believe that the conditions for the possibility of conjecturing a statement or its negation, that these conditions coincide with the conditions for the statements having a definite truth value. If a statement or its negation is too remote for being seriously conjectured, it has no truth value. It's a form of anti-realism. Thus, mathematical statements have their truth value neither in virtue of their correspondence to an ideal fact in a Platonic realm, nor, as in intuitionism, of the actual construction of a proof or disproof. Don't need to wait for the whole proof to be there to have truth value. So in the not too distant future, I would like to work out an account of mathematical truth along these lines. It's very sketchy. It's an intuition that needs to be refined. So my last goal is I would like to prepare the conceptual ground for assessing questions concerning the use of artificial intelligence in forming fruitful conjectures, but this is quite far away at the moment. So let us now take a closer look at the mathematical practice of conjecturing. By calling the mathematical activity of conjecturing a practice, I want to emphasize the fact that there are certain rules to which anyone who wishes to succeed in inventing a conjecture must abide. By denoting it as a rational practice, I want to refer to the possibility of demanding and giving reasons for or against investigating a certain statement as conjecture. And finally, by referring to this practice as art, fancily I would name it ars conjectandi, I want to indicate that not only one can succeed or fail in conjecture it, but one can do better or worse at conjecturing. And all these aspects should be taken into consideration here. Being essentially a social practice, the art of forming mathematical conjectures emerges from the shared activity of groups of experts. As such, it is governed by various norms, the description of which would require an empirical approach, not a purely philosophical one. Whether a proposed conjecture will be accepted and eventually become fruitful or not, this is in part a matter of contingency. To become fruitful, the conjecture must not only be accepted by a group of sufficiently influential mathematicians, it also needs to be acknowledged as worthwhile investigating and actually spark research. These are all facts that have to come about. But this, of course, does not imply that acceptance and fruitfulness are solely a matter of contingency. Not every mathematical statement will be accepted and would have the potential to spark the interest of the community. Typically, the fruitfulness of a conjecture is associated with features such as generality or simplicity, depth or inferential power, beauty or boldness, and so forth. But what is more important for the present investigation is that there seem to be necessary conditions that any statement must fulfill in order to be successfully established as a fruitful conjecture. It is these conditions of the possibility for success and fruitfulness that epistemological investigations like the present one should try to illuminate. As I already pointed out in the introduction, not every meaningful mathematical statement is suitable for conjecturing. A statement that is intuitively evident cannot seriously be made a conjecture. The same holds for any statement that is obviously false. So, if someone, for example, wanted to advance the conjecture that there is more than one even prime number, this would not count as a serious attempt. On the other hand, if someone wanted to turn a statement for which a proof is known into a conjecture, this would also not be considered an acceptable attempt. Theorems and their negations cannot be made conjectures. If someone tried to advance as conjecture either that there are infinitely many prime numbers or that the primes are only finitely many, neither attempt would be acceptable, since Euclid. From these very simple, trivial considerations, one can already discern a first principle that underpins the practice of conjecturing. A mathematical statement can only become a conjecture if it is neither known to be true nor known to be false. Therefore, whether an attempt to make a conjecture succeeds depends on what is known to be true and what is known to be false. Now, whose knowledge is meant here, one might ask? Is it the individual knowledge of the subject trying to make a conjecture, or rather the collective knowledge of the mathematical community, or competent part of that community? Well, usually the decisive factor is the community's collective knowledge. Because if an individual tried, for example, to advance a well-known theorem as a conjecture, that individual would simply be made aware of the fact that the corresponding statement has already been proven. So this is not a question I found very interesting at the moment, something that would have to be, I think, investigated with a more sociological, empirical approach also. Other questions are more important to the present investigation, I think. For instance, one would like to know what kind of knowledge is required, how much of it is necessary, and what must be yet unknown for statements to be valuable candidates for conjecture. And it will not be possible here to answer these questions conclusively. I can only give first hints, and I do this by considering a particular case. Imagine a child who has just mastered the language of arithmetic. The child knows now how to assemble numbers, letters, and other signs in order to form well-formed, meaningful formulas, for example, equations. Imagine further that this child jotted down the equation a to the n plus b to the n equals c to the n. And that this child, who's improbable, never know, was now claiming that no natural numbers a, b, and c satisfy the equation for any integer value of n greater than 2. Of course, we would not accept this as serious conjecturing, but not because the statement is Fermat's so-called last theorem, not because this statement has been proven in the meantime. We would not accept it because a superficial and merely syntactic understanding of statements is not sufficient to make conjectures. Serious conjecturing is not guesswork. It presupposes the establishment of a certain conceptual environment around the notions involved in a conjecture, and this environment should be such that its mastery allows for a serious attempt at proof.
And a serious attempt is one that would bring some progress and not immediately end in perplexity. If you ask this child to give a proof, not much would happen. Depends maybe on the child. If we'll see, making guesses out of the blue just because one has the syntactical skills to do so is not the kind of conjecturing that has proven itself in mathematics. Now, admittedly, if the child in our example had been born in 1777 and was called Carl Friedrich Gauss, we would perhaps take a second look and judge the method differently. As we shall see, Gauss made his conjecture about the prime number theorem when he was only 15 years old, but that doesn't matter. Even a conjecture advanced by a recognized expert in the field may not be accepted immediately. This could be the case, for example, if the claim seemed overly speculative and no serious attempt at proof were foreseeable. In such cases, the mathematical community would be entitled to ask for reasons why this proposed claim should be believed to be true. Perhaps Fermat's conjecture of his so-called last theorem was such an overly speculative conjecture, considering that it took 360 years of revolutionary developments in mathematics before a proof was achieved. Now, a different way to deal with this delay in the case of Fermat would be to say that his conjecture came too early to become immediately fruitful. That the conjecture, like an exceptional wine, needed time to mature. So Andrew Wiles makes, or has made, comments in this direction. At a certain time, when he gave the first version of his proof that was shown to be incorrect or not complete, he was so desperate that he wouldn't be able to fill the gap. And one of his thoughts was, maybe I'm just living in the wrong century to fill the gap. Maybe we need 100 years more to fill the gap. So there is this notion of that the statement can be too remote, too far away to seriously try to prove it. But of course, it's a very vague notion. So conjecture is also an invitation to investigate and eventually demonstrate the truth of the statement being conjectured. One could also say that by making a conjecture, a challenge is set up to produce a proof, and what is usually expected is a proof of the statement involved, not of its negation or of a different statement. Accepting a conjecture implies therefore accepting the challenge to come up with a proof of it. It would be strange, maybe even irrational, to pose or accept this challenge if one had better reasons to believe that the statement being conjectured is false. Typically, to make or accept a conjecture implies the belief that the statement involved is probably true. Again, simple considerations suffice to identify a second principle underpinning the practice of conjecturing. A mathematical statement will only be accepted as conjecture if it is not believed to be more likely false than true. Therefore, whether a conjecture is accepted depends on what is believed to be true and what is believed to be false. Although the absence of belief in the falsity of the statement is necessary for accepting it as a conjecture, it is clearly not sufficient. What if someone advanced a conjecture that goes against common intuition or some other kind of evidence? Think, for example, of the Banach-Tarski paradox, a theorem in set-theoretic geometry proved by Tarski and Banach in 1924. Now imagine that Tarski had told you a year earlier about his conjecture. It is possible he had claimed to decompose a ball into a finite number of pieces such that they can be reassembled into two balls, each of equal size to the first. Clearly, you would have been entitled to ask for reasons why the conjecture statement is true rather than false. After all, the conjecture should be plausible enough as to convince others to put efforts into proving it. If Tarski had been unable to provide any reason as to why the statement should be hold true, you would have been free to reject the conjecture as insufficiently justified. And it is on occasions like these that justifications will be asked for and will have to be provided, I think. As a result of the justificatory dialectics following from this, the initial statement of the conjecture may be adjusted as to more convincingly approximate truth. However, the role intuition may play in rational exchanges of reasons and counter reasons is not restricted to the one just mentioned. As shown, common intuition can lead to demand a justification for accepting counterintuitive conjectures. That's one rule. But expert intuition can be given as a reason why the conjecture should be accepted. And this, whether it goes against common intuition or not, doesn't matter. And to be honest, if Tarski had told me about his conjecture and that it was based on some advanced intuition he had and I wasn't capable of having it, I would probably have taken his word for it and accepted the conjecture as sufficiently justified. Expert intuition will often trump common intuition, where there is conflict, I believe. But of course, even the intuition of an expert genius may turn out to be false, and perhaps Tarski indeed had to bolster his intuition with additional support in order to convince colleagues that he had not lost his mind, but that his conjecture was probably true and certainly worth investigating. So expert intuition can be a sufficient reason for accepting a conjecture, but it need not be. Now, what about statements on which our intuition stays silent? And more generally, what about statements that one neither believes to be true nor believes to be false? Is it not possible to conjecture such statements? Well, I'd say rather than advance a conjecture, one would simply formulate an open problem. This, of course, exists also in mathematical practice a lot. Is it the case that P or that not P? Sometimes the difference between conjectures and open problems is blurred by the fact that some people hold the relevant statement to be true, while others prefer to stay agnostic. However, this should not conceal the fact that the strategies for proving a specific claim will typically differ from the strategies for disproving that claim. Take any statement affirming that all natural numbers have a certain property. To prove it, we could try the method of mathematical induction, but to disprove the same statement, we must resort to very different methods. We might want to give a counterexample or an indirect proof, and therefore what I would like to maintain is the following. To conjecture is not simply to say, take a look at this statement, it is interesting, and it could be fruitful to investigate it further. I would like to maintain that conjecturing essentially contains a truth claim. And like every science, mathematics strives for truth, but due to the intimate connection between truth and falsity in mathematics, the truth claim involved in a conjecture can in certain cases become negligible. As we shall see in the next section, this has to do with the fact that whether a statement has the potential to become a fruitful conjecture does not depend in general on its truth value. False conjectures may become as fruitful as true ones. So, when doing mathematics, mathematicians are not always only interested in getting certainty about the truth value of statements. Often, what is sought after is more than just knowing that something is true or that something is false. Understanding why it is true or even why it is false can be at least as important and worthwhile an investigation. Accordingly, one might not only want to conjecture a true statement, but a statement, the investigation of which will prove particularly fruitful. A fruitful conjecture, then, is one that improves mathematical understanding, a conjecture that helps to deepen or broaden our understanding of the statement's conceptual environment by triggering the development of new concepts, methods, or theories. And for this, of course, the statement conjecture needs a certain potential of becoming fruitful. But what exactly is meant here by fruitfulness? What does it need for a conjecture to become fruitful? And what does it mean to say that a conjecture statement has the potential of becoming fruitful? How does one even know whether a given statement has or lacks that potential? So admittedly, I make a rather technical use of the term fruitful here. It's also not the same use as in Frege. I try to cover a vast multitude of aspects that one would have to disentangle later in more elaborate discussions of the topic. So this is like a first draft, so to speak, and this is my first concept or term that I want to use for that. Maybe later I will split it into much finer conceptual distinctions. And for the moment I can say just so much. For a conjecture to actually become fruitful, it needs to be investigated to actually spark the interest of mathematicians. So that's clear. It will not become fruitful just by having the potential of being fruitful. So therefore, again, whether conjecture becomes fruitful depends, at least in part, on contingencies, like the preferences of dominant groups within the mathematical community, or the authority of the individual advancing the conjecture, etc., etc. So a conjecture by Gauss has more weight than a conjecture by me, for example. But clearly, not every mathematical statement has the potential of becoming fruitful. There are some that really don't have the potential. To show that a statement lacks that potential, one could give, for example, a trivial or nearly trivial proof of it. And to show that a statement has that potential of becoming fruitful, I think there is no way around investigating the statement and coming up eventually with an ingenious proof or disproof. So I don't think that having the potential of being fruitful is like something you would recognize on certain criteria. You really would have to investigate the statement and see whether it has that it eventually will become fruitful and spark interest and research or not. So this is what I can say for the moment about fruitfulness. And from these considerations, we can see a third principle at work in the practice of conjecturing. And this is that sometimes the aim of advancing a conjecture is to help improve mathematical understanding in significant ways rather than just attaining truth. And for this to be possible, the conjecture statement must possess the potential of becoming fruitful. Therefore, whether a conjecture might actually spark the interest of the competent community can depend on whether it appears potentially fruitful or not. So it must look interesting. And obviously, the third principle is not as constraining as the first two. It is certainly possible to make a conjecture that clearly could not become fruitful, and dull conjectures will be accepted, but they will probably not be investigated much. In a certain way, conjectures are better off when they are held to be false rather than unfruitful. Better be wrong than boring, one could say. And why is this so? To doubt the truth of a conjecture is very different from deeming it unfruitful. One could believe the conjecture to be false and yet be highly interested in settling the question of its truth value once and for all, even if this means proving the conjecture to be false. In such a case, one could be said to investigate the negation of the statement first advanced as conjecture, but this is not to dismiss the initial conjecture totally. It is trying to decide the question of its truth in the negative, so to speak. False conjecture then can become fruitful in two different ways, either by disproving the statement initially conjectured. One has proved the truth of an equally interesting statement, namely its negation, or the negation of the initial statement is in itself uninteresting, but the reasons why the statement is false are worth investigating. So let me first give an example for a false conjecture, the negation of which turned out to be equally interesting. The example is the decidability of first-order logic. Clearly, Hilbert and members of his school conjectured, believed, and hoped in the 1920s, and some still in the 1930s, that the decision procedure for first-order logic not only existed, but could perhaps be given one day. After Gödel had presented his incompleteness theorems, this conjecture became very improbable. Accordingly, the question of decidability did not turn into an open problem, but instead the negation of the initial statement became the conjecture sought after. Neither Church nor Turing hoped to come up with a proof for the existence of a decision procedure, let alone with the formulation of such explicit formulation of such a procedure. Instead, what they tried to do, Church and Turing, and eventually succeeded in doing, was to show that, and to some extent why, no decision procedure could exist. And I think this is as interesting as a result as when the opposite, the decidability would have been shown. It's interesting, well, maybe it would have been even more spectacular to show that first-order logic is decidable in the sense that all the consequences that would have flown from this would have been quite interesting too. But I think the undesirability result is certainly an interesting result, although it was not the initial conjecture. The second case, just mentioned before, is when the negation of the conjecture statement is not interesting in itself, but the reason for the statement's falsehood are. Imagine that a counterexample to Goldbach's conjecture was found. Although the specific instance for which the conjectured statement was proven false could be uninteresting, one might still want to better understand why the statement holds for many pairs of natural numbers but not for others. For example, one might want to know whether it holds for infinitely many pairs or whether it is false of all but finitely many, etc., etc. So to sum up this last section on conjecturing, one can say that in mathematics, false conjectures can become as fruitful as true ones. If a conjectured statement is false for interesting reasons, the situation can be quite similar to cases where the conjecture proves to be true. Therefore, even when intuition fails us, it can still be a valuable source for forming fruitful conjectures. Now let me make some brief remarks about the notion of intuition relevant to my investigation of conjecturing. The notion I'm after here stands in sharp contrast to the Kantian tradition, as I already alluded to. An intuition in the Kantian sense is the direct representation of a particular object. Kantian intuitions are always intuitions of an object, never that something is or is not the case. It makes no sense, therefore, to ask whether an intuition, taken in a Kantian sense, is true or not. Only judgments are capable of being true or false, and when an assertive judgment contains an intuition, it says something true or false about the object directly given in the intuition. For example, I could judge that the thing in front of my eyes is a table, and this would be a judgment joining an empirical intuition with the concept of a table, which as a concept is a general representation. According to Kant, the judgments of pure mathematics are special in that they contain only pure intuitions. That is, no intuitions of particular empirical objects. Contrary to empirical objects, which are given through sensation, the objects of pure intuition are constructed by the imagination, as we saw this morning. In constructing the object of mathematics, the imagination conforms with space and time, which are the general forms of intuition. This is why mathematical judgments essentially contain an intuitive element. And this is why Kant classifies them as synthetic a priori. In this, they contrast with philosophical or logical judgments, which are the result of discursive rationality. It becomes clear from these short considerations that, from a Kantian point of view, the question raised at the beginning of this talk may seem misleading. Being synthetic truths, mathematical propositions are based per definitionem on intuition. Any conjecture which has the potential of becoming a theorem presupposes, therefore, intuition. On the other hand, if fruitful conjectures are mainly the result of discursive rationality, unhelped by intuition, one will not be doing mathematics, but rather logic, philosophy. Because by asking for reasons, the immediacy and facticity of intuition get lost. From this, I conclude that the notion of intuition I'm after here must be at some distance from the Kantian tradition. So what are the main differences? First and most importantly, intuition in the sense intended here is not objectual but propositional. It is intuition that P. And intuition in the sense here relevant is a propositional attitude. It may be also denoted by expressions like I have the feeling that, or I tend to think that, or I believe I can see that, or I believe to have recognized that. Something like that. Secondly, this sort of intuition is based on experience, which usually means years and years of hard work as specialists in a chosen field. It is intuitions of this sort that allow for mathematical research to advance into unknown territory. They are somehow the opposite of what one might call intuitive knowledge in virtue of its basicness. Expert intuitions will struck others, especially non-experts in the field, as too difficult or too remote to venture guessing their truth value. More often than not, such intuitions may seem bold. And of course, they may fail us and turn out to be false. Expert intuitions are typically fallible, not factive. This is why, under certain circumstances, they may require some justification in order to qualify as worth proving. But usually, they appear interesting enough as to spark the community's interest. This makes them a reliable source, maybe the source, principal source for forming fruitful conjectures. And here is what Terence Tao, well-known contemporary mathematician, has to say about intuition in higher mathematics and what he calls the post-rigorous stage in which one has become an expert in a given field. I have this from his personal blog. It is, of course, vitally important that you know how to think rigorously, as this gives you the discipline to avoid many common errors. Unfortunately, this has the unintended consequence that fuzzier or intuitive thinking, such as heuristic reasoning, judicious extrapolation from examples, or analogies with other contexts, such as physics, gets depreciated as non-rigorous. All too often, one ends up discarding one's initial intuition and is only able to process mathematics at a formal level. The point of rigor is not to destroy all intuition. Instead, it should be used to destroy bad intuition while clarifying and elevating good intuition. It is only with a combination of both rigorous formalism and good intuition that one can tackle complex mathematical problems. One needs the formal to correctly deal with the fine details, and the latter to correctly deal with the big picture. Without one or the other, you will spend a lot of time blundering around in the dark, which can be instructive, but is highly inefficient. So once you're fully comfortable with rigorous mathematical thinking, you should revisit your intuitions on the subject and use your new thinking skills to test and refine these intuitions rather than discard them. So something like that I have in mind when I speak of expert intuition here. So, I still have some time?
How much time do you?
I don't know.
We started 10 minutes late, and so you've been talking for 45 minutes.
Already?
You
Okay.
can take 10 minutes.
Yeah, maybe I need 10 minutes. Okay. Good. Let me come now to the final section dealing with the origin of the prime number theorem. The origin is in a conjecture based partly, at least, in intuition, and this is my own conjecture, so to speak. So the property of being prime, common among natural numbers, is as elementary as it gets. So I have the definition: a natural number greater than 1 is prime if and only if it is not the product of two smaller natural numbers. And this is what this non-compositionality with respect to multiplication is what characterizes prime numbers, and this characteristic can be grasped intuitively. Take the task of arranging n square tiles into a rectangle. N is a prime number if and only if the only way to form a rectangle is to align the tiles in a row. Correspondingly, it is a trivial task, at least in principle, to decide whether any given number has the property of primality or not. Just check for each smaller number whether it divides this number or not. If no divisor other than 1 can be found, the given number is prime, otherwise composite. So in other words, there is a simple decision procedure for prime numbers that can be derived in an obvious way from the concept of primality itself. In this sense, there is nothing mysterious about the extension of the concept of primality. Quite the contrary, however, is true when one considers the distribution of the primes among the natural numbers. Of course, we have Euclid's theorem affirming that there must be an infinite number of primes, and perhaps one would even admit that the truth of this theorem follows intuitively from the notion of primality. The classical proof is so simple and elegant, one could say, well, that's also intuitively flowing from the concept of primality. And in addition to Euclid's theorem, we have a few corollaries that allow us to draw first conclusions about the distribution of the primes. From their infinity, we can immediately infer that starting from any given natural number and ascending the number sequence, we must at some point reach a new prime number. And thanks to an argument not so different from the one Euclid uses, we can also see that the gap between two consecutive primes can become arbitrarily large. However, we cannot foresee, when starting from any natural number, how far we'll have to search to find the next bigger one, the next bigger prime. This is not a question we can easily settle by the same sort of argument involving not much more than a concept of primality itself. And even worse, if one looks at long lists of consecutive primes and where they occur within the natural number sequence, it seems as if their occurrence followed no rule. They seem to pop up randomly here and there at large or small intervals without it being explainable why. By studying large lists of consecutive primes at a number up to a certain point, two mathematicians succeeded nevertheless and independently from each other in making remarkable conjectures about the distribution of primes. These two extraordinary mathematicians were Legendre and Gauss, and the conjecture they advanced famously became the prime number theorem. And let us turn now first to Legendre, for his essay sur la théorie des nombres seems to be the earliest publication to contain the conjecture. In the first edition of Legendre's essay, published in 1798, one finds at the beginning of the book, somewhat hidden in a footnote, the following remark. I'm sorry I don't have translation. There probably is one. I'm not sure of the first edition. So I will not read it in details. I will just give you a summary. So, as a first step, Legendre gives a very rough approximation of the number of primes up to a given number A. The number of primes up to this number A is denoted by B. And his approximation is the first formula you can see, it, or the first equation, B equals A over 2 times the logarithm of A. And if one looks at the numbers above, I think here it's the decimal logarithm that is meant. But he says that this first approximation works only up to 1 million. It's not clear how he came up with this first approximation. He certainly used tables for the logarithm as well as lists of prime numbers, but the calculations involved seem to be rather basic, and the margin of error is quite large. In the second step, it's the second paragraph that begins with au reste, il est vraisemblable que la formule rigoureuse da da da. In this second step, Legendre ventures a general conjecture for very large numbers. And this conjecture is that B equals A over capital A times log A plus B. And here the logarithm is the natural logarithm, hyperbolique, as he called it. We have here a proto-version of the prime number theorem, but interestingly here he qualifies the truth of his statement as merely probable. So one question one might ask is there really intuition involved? And for answering, I mean, especially in the first step, is there intuition involved for this first approximation? And I think it's helpful to have a quick look at one of these tables. That's from Vega's logarithmische, trigonometrische und andere zum Gebrauche der Mathematik eingerichtete Tafeln und Formeln. If you look at this, even if you start to study it, I don't think it's an exaggeration to say that you need a good sense of numbers to be able to see even a rough approximation of the distribution of the primes from a list like this. And I can see no reason why such a feeling for numbers, as I call it now, should not be classified as a form of expert intuition. The assumption that Legendre's first approximation was only the result of pure chance offers a less plausible explanation, I think. As Tao rightly points out, without intuition, you will spend a lot of time blundering around in the dark. So maybe Legendre blundered around, I wasn't there, I don't know. But it's clear that blundering around in the dark and making random guesses is too ineffective to explain mathematical progress in general. Let's get back. And as for the second step of Legendre, where he conjectures the general formula, it is clear that here it's not just intuition coming in, but it's really his expertise, his skills in approximating functions that comes into play, both using the natural logarithm and introducing two undefined parameters, capital A and capital B, proved to be a skillful move, as the further history then showed, actually. So, anyway, Legendre took up the curious challenge he had set himself with his first conjecture, and in the second edition of his essay, that was published 10 years later, he was able to give a refined version of the conjecture. And here, he calls it une loi très remarquable observée dans l'énumération des nombres premiers. So what has changed? I won't read all of it. Legendre now feels much more confident in his conjecture. He calls the conjecture statement a very remarkable law, and he seems to have no doubts about its truth anymore. Indeed, his increased confidence is well justified. Legendre made further calculations that have verified his initial intuition, and through this verification, he was also able to refine the conjecture itself by specifying the two parameters, capital A and capital B. Capital A now equals 1, and capital B equals minus 1.08366. So to sum up, I believe that we have here a paradigmatic example for conjecturing based on expert intuition, which is then refined and corroborated by extensive calculations. So very quickly, it's an interesting fact that Legendre's conjecture had a twin. It was born in the mind of another ingenious number theorist, in Gauss' mind, and contrary to Legendre, Gauss never published his investigations on the distribution of primes. So it was a private conjecture, so to speak, something he did quite often. And more than half a century later, he communicated his conjecture for the first time, and this was in a letter to Franz Johann Encke. Here's, you have a snippet view from this letter from Gauss' Werkausgabe. And I will not analyze it now because it's a bit, I'm running out of time. I just want to say here, or maybe to stress this one sentence that he makes, or he describes the way he came up with the key idea in the following words. He writes about the decreasing frequency of primes. And he says, ich erkannte bald, dass unter allen Schwankungen diese Frequenz durchschnittlich nahe dem Logarithmenverkehr proportional sei, sodass die Anzahl aller Primzahlen unter einer gegebenen Grenze n nahe durch das Integral, also jetzt die Integral there, ausgedrückt werde, wenn der hyperbolische Logarithmus verstanden wird. Also ich erkannte bald, he seems to have had an erkenntnis very quickly by looking at tables and looking at these decreasing frequency and making calculations. And I think that this form of erkennen, in this sense, I would just see this as an instance of expert intuition. So again, we can see also in Gauss a fruitful interplay between numerical experimentation and intuitive foresight on the other hand. This is it. Thank you very much for your attention.
Thank you, Romain, for the stimulating talk. So we have a bit of time for questions. I'll start with Valeria.
Thank you very much. It's very interesting. But I have one question, and that goes with two reading suggestions. So the question is that it seems to me, but maybe I misunderstood you, that you're a bit ambiguous when you talk about conjectures. Because you're a bit ambiguous.
Ambiguous,
then
yes.
I had the example at the end, so maybe you responded with the example. But sometimes it seems to me that you were talking, your interest was in the act, let's say, of conjecturing, and on the other side on conjectures. And I think these are two different things to some extent. In the example, it seems to me that you're interested in the process and not in the product. I mean, both are interesting objects of research, but I would ask you to clarify, because it seems to me again that you go, you're sometimes there, some other times.
Yes.
But
Yes, this
just
is true.
in relation to that, because if you're interested in conjecturing, and this is one suggestion that I'm thinking about, you have all these texts in your example, but there is, for example, something that you could look at in the use of experimental mathematics today to look into conjectures. And I'm thinking of a paper of Jean-Paul Van Bendegem on experiments in mathematics, where, for example, he talks about the fact that by looking at the graph of the Goldbach conjecture and the values that it takes using a computer, you can have some hints or some possible. So there is something that has to do with intuition.
Yes.
On the other hand, if you're interested in conjectures, there's a recent paper that has been published by Tim Gowers that it's on the reasons why mathematicians believe statements of which they don't know if they're true or not. And he framed it referring to Paulia's suggestions, and he framed it in terms of probabilistic judgments and this idea that then you update it in a kind of Bayesian way. But then you see the difference. I mean, in these two suggestions, I think that there are two different objects of research, and so I would like to ask you what you're more interested in.
Yeah, well,
thank you. Sorry for the
No, you absolutely. Thank you very much for all these good suggestions, because it's true. I mean, I just started to think about it this summer, and I have not read the relevant literature. I know it. Maybe it's not a huge literature, but there is literature, and one that I read was James Franklin, and it's interesting because he also suggests a Bayesian approach to this. So this is certainly something I will try to go in, because I'm interested in the practice of conjecturing, and of course the act of conjecturing and all the propositional attitudes or cognitive states that are somehow involved are interesting. But as I tried a bit to say at the beginning, I'm trying to find like really the philosophical question that I can try to analyze philosophically before needing or before going into something which would be more sociological or psychological. And here I found that this connection between the practice and the statements themselves, so the conjectures as mathematical statements, what the conditions or the constraints were on these statements. That was the thing that I wanted to investigate first. And I did this with a certain disregard for the subtleties that are linked to conjecturing as an act. And this is why sometimes it's blurred. So I totally see that. I think in the end what I try to do is something epistemological, in the sense that I would like to have a clearer view of what kind of knowledge is necessary, what kind of ignorance or lack of knowledge is also necessary for a particular statement to be conjectured. So it's not so much what people believe and why they believe it, and that's only maybe the framework, and I certainly need to read much more about this. But in the end, what I'm interested is what I call this conceptual environment and some sort of mastery of this conceptual environment around notions like primality or other more complex notions that allow you to make the next step, and that it's not possible to do like huge steps at a time. That's usually the next close conceptual step that you can make, and to have a bit a better idea of this. But it's really vague, so thanks. Yeah.
No, just to be sure, I'm not saying that on the one hand you have psychology, on the other hand you have epistemology. I think that you can have epistemology on both sides. It's not that the first, maybe I misspelled it by saying the act of conjecturing, but what I meant is the process of finding a conjecture on the one hand, and the idea of reasoning on a conjecture that is already there and it's been there for a while.
Yeah, no, it's absolutely right. I think, for example, I have this what I call a principle that you need to somehow believe the statement to be true to conjecture it. I mean, what notion of belief do I have here? That's really controversial, so I could really do much more work on that. And maybe I will do it, but that was really more on them. So thank you very much.
So I think so we have many questions, so we can take everyone, but short questions,
Yes.
short answer.
Yes, sorry.
If you, no, it's not your fault. It's just that so that you keep on schedule. Andy.
Thank you. I'll try to be quick. Yes. So I wanted to. I think it would clarify the project if you would distinguish between what you were in the notion of conjecturing, between what you were calling, or what you could see in the passages, vraisemblablement,
Vraisemblable, yes.
and erkenne bald. Yeah. So this is one notion here. It's something like close to truth or like true but not true, seeming true. And the notion of being interesting. And these are two different notions, and I think you are conflating them in a variety of ways and in using one to say things about the other. So I think it would be both, on the one hand, good to distinguish between those two aspects, the somehow true seeming on the one hand and interesting on the other hand, and then also to think about the ways in which those two interact with each other. And there's much more to say about that, but that will do for now.
Thank you. Yeah, well, I tried a little bit to do it by using this term fruitfulness, but this was more like, a first try. So I tried to say on the one hand that, you're looking for truth, but you also, and this is another aspect, you're also looking for an interesting or fruitful conjecture. And the two are not linked in the sense that you can have false conjecture becoming very interesting, fruitful. This is, at the moment, what I was trying to say. But it's clear that, I should distinguish it much more, and especially say more about this notion of being interesting or fruitful, because I don't have very interesting things to say at the moment, I think. Yeah. Thanks.
Okay, Monsieur.
Yeah, thank you. I really enjoyed that.
Thanks.
It occurred to me when you were speaking that a lot of what you were saying resonated with experiences I've had when I've been involved in scientific debates with people who have made other hypotheses about non-mathematical scientific things. You know, it turns out when some people in the community I work in make hypotheses, I trust them more than other people who make hypotheses. They seem to be better at doing it. The hypotheses are more interesting. And a lot of what you said, it seemed to me, could be said exactly the same way about scientific hypothesizing. So I guess my question is, to what extent do you think any of this is actually mathematical, or is this just about progress in science per se?
Yeah, well, two parts maybe of my answer. The first is, I think it's interesting to look at mathematics as a science that is not totally different from the other sciences. So, and I think that in this process of conjecturing, there are, of course, a lot of similarities. And that would be interesting to highlight them even stronger. But I think that there are differences. And in an earlier version, I had a stronger account of what difference may be. And one difference that's really important is, I think that the falsity of a statement can be, and regularly is, as interesting as its truth. I think there is a connection of truth and falsity in mathematics that you maybe don't have exactly in the same way in the sciences. So if you have a hypothesis that just doesn't verify itself, or doesn't just bring what you hoped, maybe you could ask, why didn't it work? And then you have a similar situation. But very often you just look for another hypothesis and just lay it down. But maybe, that's not really a difference. So what would you say? yeah, something along that line. But I was not convinced myself, so I took it out again. And that's certainly something I would like to investigate further. If there is like a specificity of mathematical conjecturing. Yes?
Okay, Dirk.
Thanks a lot for this talk. From the title, I was expecting that you talk a lot about Polya and Lakatos and all these people. So I must say I'm a bit disappointed.
Sorry.
But it's okay. Yes. One conceptual question or remark that I have, to me it's not clear what you mean by conjecture, because for me, like, every theorem starts with being a conjecture, right? You have a conjecture and then you prove it and then you make it a theorem. But you seem to pick out some that are kind of more famous, right? Like you had Fermat mentioned, these ones. So it's not clear to me exactly what you mean by conjecture. And personally, I think anything goes. You can come up with any idea, and that can be a conjecture. But I want to kind of press you on something that you actually concretely said about conjectures. One of your conditions was that, I think, if I understood you correctly, no negation of a theorem can be a conjecture. No negation of a theorem can be a conjecture. But in the history of mathematics, it has been shown that theorems, or statements that were thought to be theorems, turned out to be refuted.
Yeah.
So that seemed to be clear counterexamples to your claim.
Well, maybe to second question first. No, I mean theorems in the sense that have been correctly proved to be true. But that doesn't mean that something that was thought to be a theorem and turned out to be incorrect, that in that case you could conjecturize the negation. That's surely a possibility. So, okay, but maybe I'd say like this. I mean, before you conjecture the negation of a well-known theorem, you would have to doubt its theoremhood. You would say, well, it's not a theorem. Otherwise, you wouldn't do that. Or maybe you could do it for an exercise or something and try to find indirect proof. But that would not be the same sort of conjecturing that I had in mind here, where you have some belief of that a statement is probably true, and then you eventually look for the proof to confirm it. In that case, when you're sure that the statement you will be trying to prove is false, I mean, your goal must be a different one. And I would call this something else than conjecturing. But it's, there's similarities, and it's not, I don't want to impose like a normative way of talking about conjectures. It's just trying to describe, I think, a practice that might be there, maybe not.
I'm not sure what your conception of that brings me back to my first comment, that I'm not sure exactly what your conception of conjecture then is.
So you'd say like every lemma, every theorem that has been proved was first conjecturized and then proved.
That's what I say.
Yeah, but I mean, I'm not sure if this is true. Very often you'd come up with a lemma just by trying to prove something else, so I'm not sure. I had more in mind these cases where you had a very prominent statement that was also published and then discussed through maybe generations of mathematicians. That's what I had in mind. Not so much like, but then you're right. I mean, in every we'll find what I called at the moment like private conjectures or smaller conjectures that were part of a, So you'd say, maybe I have to think about that, how I would make this a bit more clear.
Nicolas has a quick follow-up.
Yeah, thank you. So just on your discussion, so first of all, I think that in the historical dynamics, there's not just people conjecturing things to be true, assigning temporarily truth values to statements, but there's also dynamics within the theorems and within the way, the way concepts are delineated and put in relation to another. So one historical way in which a refutation or the negation of a theorem may arise is not that people doubt the theorem to be true, but that the concepts underlying a field or a theory are redefined, are reorganized, and in this way, a theorem becomes rephrased, reformulated, or new limit cases come into view. If you look at the history of analysis, it's not that people suddenly decided, oh, the theorems of Cauchy are wrong. And it's that they rethought what continuity was, what a function was, how you denote them, how you prove things about them, and so on. I mean, it's such a tectonic change in the way that we do analysis, and then theorems become disproved or modified. It's not so much that someday some mathematician wakes up and thinks, oh, well, that theorem I read the other day is actually false, so I'm going to prove that it's false. It's that, I think these are changes on a much more continuous and large-scale level that just placing the historical dynamics at the level of truth values of statements isn't enough to capture it, is what I would say as a historian.
Yes, I think, you're totally right, and this is certainly one of the aspects that I haven't worked at all on is the conceptual innovation. And I mean, I was talking about intuition, propositional intuition, but that was more like a move to keep the topic a bit smaller. But of course, you would have to look into what happens when new concepts are formed, or when old concepts are refined and changed. Is there also intuition involved? What kind of intuition is this? You also have this sort of expert intuition, or is it more than intuition in Kantian sense? So I haven't said anything about that, and it's clear that this would have to be taken into account. It's what I did is like a very rough model that I will try to use now to look at certain developments, and I'm really sure that I will change a lot of parameters according to what I will find. Now, maybe I should have done it differently. Look first much more into the history of mathematics, look at many different cases. But the thing is, without this model, I wouldn't have known exactly what I'm looking for. And maybe I'm still not very clear about what I'm looking for. I have a few paradigmatic examples, like these famous conjectures. Maybe they're just special cases of a larger phenomena. Maybe it's a bit anecdotic. So this is not totally clear yet to me. But yeah, thanks.
So there was Gemma and Gemma.
Thank you for your talk.
Thank you.
Something that maybe we've been talking around for the past few days, but you made more explicit, is in your notion of expert intuition, is the elitism of intuition, and how among those who are mathematicians, only some subset are allowed to have intuitions. And I wondered if you could speak to that.
Yes, well, I'm not a mathematician, so I know it only from the outside. I know that coming from the outside, you could not just like come and say something. And maybe in mathematics, this sort of elitism is particularly pronounced, and more than in other sciences. I'm not sure about that. This, I think, would be a sociological question that I have no answer to. What is clear is that also, if you look at this particular example from Legendre and Gauss, most people talk about Gauss and say Gauss conjectured the prime number theorem. It's true that it's a bit earlier, but it was not published. So it's clear that Gauss' prominence and genius is what influences the way the story will be told afterwards. It's Gauss' conjecture. Legendre maybe is mentioned sometimes, but it's clear that the more the more prominent you are, the more interest you will draw, and the more people will work on that. So I think this is dynamics that I have just like a very rough idea of, and I'm sure that many of you have a clear idea. So maybe to ask you back, you think that this is right? There is this sort of elitism, or?
Of course.
Yeah, of course, yes.
I mean, yes, all over the place.
All over the place, yes.
Okay, Bruno.
Yeah, thank you very much. So I was much interested in your talk. I would love to state a remark and then ask a question. The remark is about what you said on slide 5, saying that the conditions for the possibility of conjuring a statement coincide with the conditions for the statement to be true.
Yes.
So you surely want to be the same kind as. So because what you wanted to state is you're looking for epistemological reasons for conjecturing a statement, and these epistemological reasons can also intervene in making the statement true. But coincide is not probably not what you want, because you could have good reasons to make a conjecture, and then miss some reason that will make it true, or miss a reason that make it false. So they can't not coincide. Perhaps they're part of.
Yes.
And the same kind as, but coincide probably is not.
No, that's yeah, you're right.
That was my remark. And my question is about something else. You said on slide 7 that even if a child has the syntactic tools to state conjectures, he or she cannot make conjectures as long as he or she does not master the conceptual environment allowing for attempting a proof. And what would you say about computers? As François Charton said yesterday. François Charton claimed that computers will probably make conjectures and help us make conjectures, because they can spot that some theorems are likely, are probable. And so, but he was not sure that they master the conceptual environment. So, what about computers?
Yeah, that's a good point. I mean, that's one of the things I want to try to investigate, but I'm really far away. I know that now literature is coming up, the use of artificial intelligence in conjecturing, and I mean, yeah, if it's about finding true statements or false ones, I think that yes, why not? Of course, it could be very helpful to have a computer assistance. Of formulate conjecturing, yes.
Possible theorems.
Possible, yes. I think this will probably happen. I mean, I don't know, but I don't see any reason why not. Where I'm a bit more critical is about the aspect of fruitfulness, because or interest. This is a very human thing. What we find interesting. Now, of course, there are algorithms that try to suggest to us what we should be interested in everywhere in social media, and so maybe we could have something comparable in mathematics. But I think fruitfulness will be more hard to simulate, and yeah.
Finding possible true conjectures is not the same as interesting.
Maybe not, but also our criteria of what is interesting might change. And also this aspect of elitism. I mean, we seem to be very willing to accept algorithm taking decisions for us and telling us what we should do. I don't see why in mathematics this could not happen with a later generation, that you say, well, why should I take the trouble of conjecturing? I can just let my program spit out some conjectures, and then I'll just try to prove them or disprove them. So this is something that might happen. It would be a change in the culture, I think. Yeah.
So very quick.
To follow up, because it's true. Another thing that you mentioned, but that you didn't go into that much, is that at the beginning you mentioned a relevant mathematical community, and then you never spell it out very clearly. So it's true that all this could be, it's relative to some particular community, maybe, or not. I mean,
yes, no, it is, certainly. So, and if computers or AI tools become part of this community, they would find a way to be used meaningfully.
Okay, thank you very much. So let's thank Romain again. We're going for a short break, and then we have Jessi's talk.
J'avais calculé 45 minutes.
C'est pas grave. Non, t'inquiète pas, il y avait 10 minutes.
Okay.
At some moment.
Don't worry, your
Q&A.
teaching calls.
Yeah.
Yeah.
So you're just 3 minutes away from
Oh,
here,
okay.
so I can just leave at the end, but still.
Yeah, don't worry.
I got 2 hours teaching.
Oh gosh, really? You must be that must be tiring. 2 hours at the end of a long conference.
It won't be a problem. Just it's a bit frustrating because I would rather be here.
Yeah.
But at the same time, I really want to give all my teaching, so and when I can do it. Of course, if I'm at a conference abroad,
Can't be done. Yeah.
I can't do it. But if I'm here, I try to be with my students. And actually, I do not accept many conferences during the first term because most of my teaching is in the first term.
Right. Okay.
And this is what I wanted, so that I can accept.
Can do lots in the second term. Yeah, that makes sense. No, come over from England.
From England?
Yeah. It's super easy these days on the train.
Yeah. All the times we've been to Europe, we've never been to England.
Oh, really? Okay.
I mean, went through the England airport.
Sure. Yeah.
There, but yeah, definitely next time Jessi and her sister have more time, we definitely want to do it because I mean, England is, well,
What
I don't have to argue with you. It's
well,
the best country in Europe. Right?
Oh, I don't know about that.
England's very fascinating with the history and culture.
Yeah, I suppose that's.
And they drive on the left side of the road.
Yeah, it's confusing for people, isn't it? Yeah.
Is the weather, is it rainy like they say, or?
I think it's pretty similar to here, to be honest. I mean, yeah, I don't know. I mean, it has been pretty bad.
you have to unmute it. Let's check it, please. Right, it's good. Okay, so now we have the second talk of this afternoon by Matthew Inglis, and he's going to talk about method for eliciting mathematicians in institutions. The floor is yours.
Thank you, Yassine, and thank you, Bruno, for the invitation to speak. So yeah, I'm going to talk about a body of work that I've been doing for some time now, which, at least in some sense, could be seen as trying to use different empirical methods for eliciting intuitions about mathematics. Some of this is going to be old, so I apologize if you're familiar with the first bit of work I'm going to talk about in particular, but I wanted to talk about that so I can contrast the results with more recent work, because the argument I'm going to be making is that when you use different methods to elicit empirical intuitions, and in particular I'm going to be talking about intuitions about mathematical aesthetics, you seem to often get conflicting results. And the thing I want to propose in this talk is we should take seriously this hypothesis that mathematicians don't have stable intuitions, at least sometimes in some domains. They don't have stable intuitions at all. And if that's right, that has quite important implications for the study of this matter. And I should say this is joint work with lots of different people, some of whom I'm sure you will recognize. Okay, so I'm going to talk about three different methods, classes of methods that I've used to investigate this issue. Some from the personality psychology literature, a fairly standard method that people in that literature have used for many, many years. A novelish method from the educational assessment literature, which some colleagues and I have been using in that world, and I've tried to use to study these issues. And also, very recently, adapting some work from the experimental philosophy literature. I want to focus on two particular questions only, and I'm going to contrast the answers you get to these two questions when you use different methods. So firstly, I'm interested in, do mathematicians agree with each other about mathematical aesthetics? So is there a shared intuition about aesthetics? And then is, as lots of people claim, mathematical beauty related to the thing being intuited, well, the thing that is being intuited about being simple or being economical? So they're the two questions I'm going to focus on. And essentially, the result will be, depending on which methods you use, you get different answers. Okay, so just some background. I'm sure you're all familiar with this. Lots of mathematicians say that beauty is very, very central to their work. There's some quotes. As the conference has gone on, it's clear that this needs to be justified, why I think this is an intuitive feeling, why this is an intuition at all. And so really, when someone says intuition to me, I think about it in the psychological sense, so in the sense of what Stanovich and West or Kahneman and Tversky call system one. And what they mean by that is it's a quick feeling, so it's an automatic feeling. The key definition that they would use for such a type of cognition is that it doesn't require working memory. So it's this automatic feeling you get that comes from somewhere, doesn't require reasoning about. And that's how a psychologist would think about intuition. And it's not totally clear that's the same, well, it's certainly not the same as every type of intuition that we've been talking about at this conference. But that's how I think about these things. And in that context, it's pretty clear that this sort of aesthetic feeling is an intuition. Okay, so hopefully you're content with that. And I'm sure you're also familiar with this kind of claim. Lots of people have made the claim throughout the history of people writing about this subject that one key feature of whether a bit of mathematics is beautiful is that it's simple in some way. So there's McAllister talking about the degree to which a bit of mathematics lends itself to being grasped in a single act of mental apprehension. So it's this simplicity. So let's go on to the first example of methods, how you can study this. And this is some work I did with Andrew Aberdeen some years ago, which I'll go through quite quickly because it's a bit old now. So the basic analogy here is like personality psychologists are interested in the dimensions on which humans vary. And the way this literature started was noticing that there's lots of adjectives that you can use to describe humans. And that is also true of mathematical proofs and other bits of mathematics, of course. So an interesting question you can ask is how many basic ways are there of characterizing a person's characteristics? And perhaps surprisingly, if you're not familiar with the literature, the answer is 5. There's 5 different dimensions on which people vary, in some sense, but their personalities vary. So the methods people use to do this is a sort of a meaning through use approach. So basically what you do to discover this is you say, think of this person, think of a person, and then say to what extent a whole long list of adjectives describe them. So, you know, we can think about Bruno and we can say, is he bashful? You know, some kind of Likert scale, yes or no. And you do that for loads and loads of adjectives. And then, in some sense, if the adjectives that always go together, if there are adjectives that always go together, they in some sense mean the same thing. So, for example, if I think Bruno is creative, I will also think he's imaginative and vice versa. If you don't think he is, you will also not think he's imaginative. These two words almost always go together, and in some sense that means they're the same thing. So this is a sort of standard, what people call the Big 5 personality scale, and you can go through and, you know, score yourself on these kind of adjectives, and then some of these all fall onto the same factor in a factor analysis, and that's the Big 5. There's 5 different dimensions on which people vary in that sense. So basically, Andrew and I wanted to do the same thing with proofs. So we created this big long list of adjectives that people use to describe proofs. And we essentially used exactly the same methods. And one of which, of course, for the relevance of this talk, was beautiful. And we got a load of mathematicians to do this, think of a proof that they'd recently read, didn't know what it was, and then go through these adjectives and state the extent to which they described it. Turns out mathematical proofs vary on 4 dimensions. So here's the interesting one, the aesthetics dimension. So it turns out all of these words co-vary. So if you think a proof is striking, you're also going to think it's ingenious, inspired, profound, creative, and so on. One of which of those words is beautiful. So we call that the aesthetics dimension. And there are 3 other dimensions too, the intricacy dimension, the utility dimension, and the precision dimension. Now, what's kind of interesting is, for these purposes, is that the word simple appeared negatively on the intricacy dimension. So if you think a proof is dense, you also think it's not simple. So it didn't appear on the aesthetics dimension. So several things you can conclude from that type of empirical finding. Well, the first question is, what does this mean in terms of mathematical beauty? But also, how can we then use that factor structure to answer the first question I posed about agreement or disagreement? So firstly, it's really hard to sustain a simplicity account based on those data. Simple, as I say, loads onto the intricacy factor. And you can also look at the 0th order correlation between the two. So if you just calculate the correlation between the people's ratings of this particular proof that they were thinking of as being beautiful and as being simple, the correlation was essentially 0. So whatever these words mean, they don't mean the same thing. That's a conclusion we can draw, or at least the way mathematicians use them doesn't mean the same thing. Of course, we can assert that the mathematicians are wrong and that they're using simple in an incorrect way, which is a possible defense of the McAllister type account. Okay, so first, using personality type methods, the conclusion is that beauty is not simplicity. But we can go further and push the method a bit more. So the personality people have used this factor structure to create these short personality scales that you can apply to particular individuals. And in exactly the same way, we can do the same thing to create a short version to construct a scale which allows us to assess the mathematical personality of a particular proof. So you can end up with a little scale like this, which is simply, essentially what you do is you just pick the words that are particularly characteristic of the 4 different factors, and you ask people to rate a particular proof with a certain number from each factor, and then you can just add up the scores, and you end up with a point in 4-dimensional space, which which gives you some measure of the personality in inverted commas of that proof. So let's ask this question. To what extent do mathematicians agree on their proof appraisals, or to use the language of intuition, to what extent is there a shared intuition of mathematical aesthetics in the mathematical community? So second study, Andrew and I did a while back, is we picked this proof about how you can split up points in the plane. You don't need to know the details of this proof, but it's a sort of shortish proof. It comes from the Eigner and Ziegler book, Proofs from the Book. Apparently this was Erdosch's favourite proof, so it has quite a good pedigree. And we were interested in how people would think about where people would put that proof in this four-dimensional space that we've constructed with our personality psychology type methods. So we got, again, a load of mathematicians, just got them to do our personality scale, particularly about that proof. And it turns out if you do this, you get horrendous disagreement on all four dimensions. So this is very, very beautiful over here. Well, on this, if you're up here in the top right-hand corner, you think the proof is really, really beautiful. If you're over here, you think it's really not beautiful. And as you can see, there's just, people are all over the place on this. This is a horrendous distribution. It's not even that it clusters around anything. People just radically disagree. And we did replicate that. So it's not a sort of rogue sample. And it's particularly problematic, as I say, given this was selected for proofs from the book and allegedly was Erdosch's favourite proof. So it's a bit weird. So, very little consensus about the properties of this particular proof. So at least it's an existence proof of the fact that there's not necessarily shared intuitions about the properties of proofs, in particular about aesthetics. So, in terms of the two questions I want to ask about using all these different methods, the answers are mathematical beauty is not about simplicity. These two things are completely independent. And there's big disagreements about mathematical beauty, at least some of the time. Okay. So, let's forget about that for a bit and move on to a second set of methods taken from the educational assessment literature. So, this comes down to the observation that there are some things we want to assess in education that we care a lot about, but are not very easy to assess. So this is Labato saying, particularly in sort of things where there's both procedural notions and conceptual notions, it can be really easy to assess procedural knowledge because it's super easy to measure at the cost of not assessing conceptual knowledge. So for example, it's really easy to see whether people can multiply fractions together, but it's much harder to assess with the same degree of reliability whether they understand why the standard algorithm gives the correct answer. And this is something that's a real problem in education, because if you are evaluating educational interventions, say, using only procedural measures, you may end up with interventions that underplay the importance of conceptual understanding. So if we want to rigorously evaluate educational interventions, you really do need some way of assessing conceptual understanding with a high degree of reliability. So that's an active research area. Some colleagues and I have been spending a lot of time thinking about comparative judgment as a way of doing this, which I'll explain now. So this is the essentially a method adapted from the psychophysics literature. So this is an American guy from, well, was working in the 1900s, who said that all judgments are inherently comparative. So there's no such thing as an absolute judgment. And you can kind of demonstrate this quite easily by giving some examples. So if I said to you, what's the area of that circle? That's a really hard question, right? It's very, very difficult to do that unless you got out your ruler and started measuring. But that, unless you're at the angle I'm at, is really, really easy, right? So which of those two circles is bigger is immediately obvious to you, or at least it should be if you are a normal person. And this is true on all sorts of dimensions. Psychophysics people care about things like area and brightness and sound and density and things like that. But you can do it on all sorts of dimensions. So, I mean, this is another simple psychophysics example. That's really difficult. That's really easy. But you can do it on other things as well. So that's a hard question. I think no one will get that right, even if you're an expert on women's shoes. But that's a really easy question, right? And this is true. Essentially, you can demonstrate this on essentially all kinds of one-dimensional constructs. So shoe pricing turns out to behave very similarly to the darkness of circles. So Thurston has this law. Across a whole range of stimuli, comparisons are much easier than absolute judgments. And indeed, we have a whole range of methods for how to model this. So the Weber-Fechner law gives us a computational way of assessing. You know, we know how people make these judgments, essentially. So, in particular, there's this thing called the Bradley-Terry model that you can fit a load of paired comparison judgments to. So if you've got a load of comparisons of this sort, you just show people lots of shoe comparisons, then you fit all of those judgments to the Bradley-Terry model. That model will give you estimates for the price of those shoes on some arbitrary scale, but a useful, you know, so you get a number which assigns a price to each of those shoes, based simply on comparative judgments. Okay, so this, I was working on this because I dabble in educational assessment in a different part of my work. And I thought, oh, maybe what's going on here is that with this, maybe the reason we got massive disagreement in the personality psychology case about the beauty of proofs is that we were asking people to do these really hard, absolute judgments. And the reason that they disagreed about this Erdos proof is that they've got no anchor. It's just impossible to you know, maybe my very high judgment is the same as your very low judgment, but it looks different when you force people to put it onto a Likert scale or something of that sort. So the idea was, well, maybe what we can do is we can use this comparative judgment method to get people to compare lots of proofs, say which one is the most beautiful, and then work backwards from those very many comparisons to assign parameter values which measure the beauty of the proofs. So essentially just using this Bradley-Terry model. So that's what we did. So this is some of my PhD student 2 years' work. This is a paper that came out this year, I think. So we started off by looking at equations. So some of you may be familiar with the Zecchi paper from 2014, where they, which was a collaboration with Attia, I think, where they did some neuroimaging of equations and perceptions of beauty in equations and tried to argue that they activated the same brain area as looking at paintings. We used some of their stimuli. We were also, because experimental philosophers, you may know there's this big argument at the moment about whether philosophical intuitions are shared across cultures. And there used to be this evidence that there weren't, and more recently people now think they probably are. But for that reason, we were interested in a cross-cultural comparison. So we had two British groups, some mathematicians and some undergraduates, and a Chinese group of mathematicians as well. So we took 20 of the Zecchi's list of equations and translated them into Chinese so we could do this cross-cultural comparison. So this is the kind of thing that we had. Here's the triangle inequality, and here's the same thing in Mandarin. So the task for you, the participant, is something like this. Here's two equations. Which one is the more beautiful? And you've just got to select left or right. And if you don't know, you've just got to guess. Okay, so we get lots of people to do lots of judgments of that sort. And then we can fit those judgments to the Bradley-Terry model. And we can ask these two questions. So firstly, do they agree within groups? And secondly, do they agree across groups? So within groups, the method for doing this is you just randomly split the group in two. You fit the model separately for each group, and then you correlate the parameter estimates you get for the equations. And then you just repeat that with a new random split. And after you've done that 1,000 times, you just take the average correlation. So if there's perfect agreement, you end up with a correlation between these two random groups of 1. And if they just completely disagree, you have 0. So that gives us a measure of within group agreement. And it turns out that when you do this method, you get pretty good within group agreement. So the standard way of thinking about these numbers would be anything above 0.7 is okay, it's pretty good. And all of our groups were above 0.7. So if you get 2 British mathematicians and you get them to do this, they have a pretty good shared understanding of which of these equations is the most beautiful and which is the least beautiful, and their scale, they sort of line up with each other. And that's true of the Chinese mathematicians and the undergraduates too. So that is already a contradiction to the first method, okay? Based on the personality psychology stuff, I was expecting that to be much closer to 0. What about between group agreement? So here is the parameter estimates for the British mathematicians. So over here are the beautiful equations, and over here are the ugly ones. And here's the parameter estimates for the Chinese mathematicians. And you can see that's a really quite a strong correlation there, 0.85. So Chinese mathematicians and British mathematicians apparently have shared intuitions about aesthetics, as do British undergraduates. So they are also pretty high correlation. So I was a bit worried about this, and I thought, oh, well, maybe what's going on here is we were using equations, not proofs, and maybe that's why we have the disagreement with the first study. So what we did is we reran the study with some proofs. So simply this, which proof do you think is the more beautiful? Here's a proof, here's a proof, select one or the other, and then you just keep getting more pairs after each other until you've done 20 judgments. And it turns out that makes no difference. So the inter-judge reliability coefficient drops a little bit, but not much, right? So it's still pretty good. I was expecting that to be much, much lower based on the personality stuff. So to summarize about that, we seem to have evidence using this method seems to tell us that mathematicians agree with each other about aesthetics, both with each other, but also across cultures, also across expertise levels. So the undergraduates and the mathematicians, the research mathematicians, they seem to agree. And this is true for both equations and proofs. Okay, so what can we say about the simplicity question with this method? So this is where the method of comparative judgment becomes kind of interesting, I think, because again, this is some 2 years' work. Is you can use exactly the same method to ask about intuitions of anything at all, right? So you can present people with pairs of proofs and ask them which proof is the most whatever. So I think actually, Jessi, you asked this yesterday. You asked about whether people would agree on which proofs are more intuitive than other proofs, which wasn't an adjective we used, but you could easily use this method to ask and answer that question. But more interestingly, is you can also see how these perceived properties relate to each other. So what Tuya did is she used the same 8 proofs as from the previous study, recruited a large number of people, but rather than asking them all about beauty, she randomly split them into 7 groups, 8 groups, sorry, and asked them about different things. So this was based on Hardy's claim that there are 6 criteria for what makes a mathematical proof beautiful. So Hardy says that a beautiful mathematical proof should have all or most of these properties. So it should be serious, it should be general, it should be deep, it should be unexpected, it should be inevitable, and it should be economical, which in a slight sneaky move, I'm going to say means the same as simple for the purposes of this talk. And we maybe come back to whether it does mean the same or not later. Certainly related anyway. So we also threw in explanatoryness for other reasons. So we were interested in if you ask people about these 6 criteria, 7, and beauty, what correlations, patterns of correlations do you find between the parameter values? So you can easily do this. So you can just say, here's 2 proofs, which is the most deep, or here's 2 proofs, which is the most inevitable. And of course, what you want to do is you want to get a sense of what the participants think those words mean by studying which of the proofs float to the top of these comparative judgment exercises and which float to the bottom. If the notion of inevitability amongst mathematicians is related to the notion of beauty, you should find some correlations between those 2 sets of parameter values. And so on for all the other things as well. You can also, of course, see to the extent, by looking at the judge-rejudge reliability coefficients, the extent to which your community of mathematicians agrees about whether proofs are inevitable or not. So exactly the same method, we recruited quite a lot of mathematicians, I forget exactly how many, and randomly allocated them to look at each of these Hardy's 6, fitted their judgments to the Bradley-Terry model. All of them had pretty high internal reliability, so there was a shared understanding of what these characteristics meant amongst our participants. But what we cared about was these relationships between these parameter values. So I hope that's big enough. But up on the y-axis here, I've got the beauty parameter values, and then here I've got these the 6 that Hardy mentioned plus explanatoryness. And the interesting one for the purposes of this talk is that graph there. So there's a really strong relationship between the extent to which a proof is perceived to be beautiful and the extent it's perceived to show economicalness. And if you're interested, there's also really very high correlations amongst other properties too. So beauty and explanatoryness look really high. I was really surprised that that was that high. And beauty and depth also extremely high. But it's not the case that people are just rating everything on using the same scale. So it's not the generality, unexpectedness, and seriousness are not correlated with beauty. So it's not a sort of general, how much do I like this proof judgment that's being made here. You can find disassociations as well as strong relationships. And I think that's important because a worry of this method is that they ignore your instructions and just assess something that they want to assess. That's not what they're doing, because if that was the case, as I say, we would find relationships on all of these, and we don't. Okay. So if we use methods from the educational assessment literature, we would want to claim that intuitions of mathematical beauty are strongly related to simplicity, or at least economicalness. Not sure what the right word to use there is, so I'll use that one. And we would say that mathematicians have a strong shared understanding of mathematical beauty. There's strong levels of agreement using this comparative judgment method, which again, quite different to the first set of studies I showed you. I should say, yeah, actually, I think comparative judgment is a really interesting method for experimental philosophers, because this flexibility that you can use, you can ask people about anything at all and just present examples of them to them, and then elicit intuitions, I think is a really powerful method in across lots of areas of philosophy, actually. And here's Fenner, my colleague, my former colleague Fenner, trying to make this case about park cases and what vehicles are. And he sort of tries to demonstrate that just by presenting different examples of vehicles, you can get people to say the extent to which this vehicle is a better example of a vehicle than that vehicle, and you get a nice dimension. You get a nice Bradley-Terry kind of model fit. So I think it's potentially quite useful for experimental philosophers in general. Okay, so let's move on to experimental philosophy. In particular, I'm interested in this paper by Cover and Payne, which is a nice paper, I think. And they're interested in folk understanding of aesthetics. And in particular, whether people perceive aesthetic judgments to be normative or not. So the base question they're interested in is something like this. So they have this vignette. Agatha and Ulrich are on holidays in the country. While having a walk in the fields, they hear a nightingale singing. Agatha says, "What beautiful singing," but Ulrich answers, "No, it's definitely not beautiful." And you have to say which of these four options is correct, or is your understanding of the situation. So one of them is right and the other is not right. Both are right, both are wrong, or neither is right or wrong. It makes no sense to speak of correctness in this situation. Everyone is entitled to his own opinion. And if you say option one, then according to Cover and Payne, you perceive beautiful singing to be normative in some kind of Kantian sense. If you say four, you take aesthetics to be some expression of pleasure. So it's just like saying, "Oh, that's great," or "Ugh." So it's not making a truth-valued statement. It's just expressing how you're feeling. And if you say two or three, you're some kind of relativist, was their argument. Okay, so again, this is part of 2 years' work, and she said, well, look, if it's the case, as the comparative judgment suggests, that economy or simplicity is really strongly characterizing beauty, then if we ask about beauty and we ask about economicalness on a Cover-Payne type task, we ought to get similar normativity ratings. So if these are the same thing, then they're either going to be both normative or both non-normative, was the basic idea. So again, we got a load of mathematicians to do Cover-Payne type tasks in a mathematical context. So we started off by having the same vignette, just to see if we got the same results. As if it turns out mathematicians all disagree about nightingales, then the general population, then we're in trouble. But they don't, so we're okay. And then we turned it into these same people were in a mathematical research seminar listening to a visiting academic present their research. At one point, the academic presents a proof of a theorem. Agatha whispers to Ulrich, "What a beautiful proof." But Ulrich answers, "No, it's definitely not beautiful." And again, with the same options. And then, of course, as with the comparative judgment context, you can manipulate the adjective you're asking about. So again, deep correlated really highly with beauty in our comparative judgment study. So we would expect it to give the same, be perceived as normative in the same way, or not normative, depending on, but you should get the same responses for deep and beautiful. And economical as well. And then we had a big argument about this. We ended up wanting something that was clearly normative, just to show that people were willing to use all of these options. So we also had a question about who wrote Saturday Night and Sunday Morning, and whether or not it was Alan Sillitoe or not, which hopefully you will all agree that is a clearly normative question. But I don't mind if you don't agree, but the mathematicians all agreed about that, so that was nice. So here's our results. So this is a simple proportion of the participants who said that this situation was normative. So we've got these two. I didn't present the taste of a sandwich one, but that was our opposite of the book author one, where we thought, this is clearly a matter of subjective opinion. And happily, the mathematicians agreed about that. So very few mathematicians think that whether a sandwich is tasty or not, or whether a birdsong is beautiful or not, is normative. But they all agree who wrote a book is normative. Now, the interesting thing about this is that almost no mathematicians think that mathematical beauty is normative. Very, very few people think that's something that you're right or wrong about. And particularly curious, lots of them think that whether a proof is economical or not is normative, so about 40% of them. So the conclusion I want to try and argue for here is that this difference tells us is not consistent with beauty and economy being the same thing. Because if mathematicians were just judging whether something's beautiful or not on the extent to which it's simple or economical, you would expect these judgments to be very, very similar. The same is true of depth. So although judgments of proofs on their depth and their beauty correlate at almost 1, so like 0.95 or so, the perceived properties of those two characteristics amongst mathematicians differ quite a lot. So, where have we got to? Using these kind of Covey-Payne methods suggests that mathematical beauty is really quite different, at least in terms of normativity, to economicalness. And mathematicians think that beauty is not a normative property. So, to summarize the answers to the two questions, do mathematicians agree with each other about beauty? If you rely on personality psychology methods, the answer is no. If you rely on educational assessment methods, the answer is yes. And if you rely on experimental philosophy methods, the answer is yes. There's a slightly different question there. Do they agree about the properties of mathematical beauty? Yes, they do, if you rely on experimental philosophy methods. So this is a bit weird. Using standard methods taken from different literatures, we get different answers. What about, is mathematical beauty related to simplicity? If we use personality psychology methods, the answer is no. If we use educational assessment methods, the answer is yes. And if we use experimental philosophy methods, the answer is no. So again, we've got this methodological problem. So, what is going on here? So I think there's two ways you can try and deal with this. One is to try and concoct an account of aesthetics that changes its predictions depending on the methods by which you elicit these aesthetic intuitions. And I don't think that's impossible, actually. I don't think that's, that's a legitimate thing to try and do. But I think it's none of the existing accounts will suffice for that, or at least not in a straightforward way without doing some work. But I think the other way of dealing with this possibility is to say that actually aesthetic intuitions in mathematics are completely unstable. And therefore, it's not surprising that the very subtle differences in the way you ask people about them lead to quite different answers. And there's good reasons to think this might be true. So I want to talk a bit about this guy, Nick Chater, who wrote this book a few years ago and has been saying this for quite some time. He's got this idea that mental depth is an illusion. And really, the mind is a very, very simple thing. And any idea that you have that you're some sophisticated person with all of these thoughts and beliefs and views is just an illusion. And there's good reasons not to think that's the case, says Nick Chater. So the way he tries to explain this, the analogy he gives, I think, is a helpful one to think about. So he says, well, let's imagine you want to know where a missile is taking off from. So I suppose, I don't know, we're at war with Australia, and you want to find out where their missiles are being launched from. What you do is you take some bearings from different places, you watch the missile, and you triangulate. Okay, so from over here, the missile looks like it's coming from that direction. From over here, and you sort of triangulate, and you end up, it's probably about there. And triangulation, of course, is a standard term in research methods, in social science research methods. If you try and understand a concept using different methods, different measurement techniques, hopefully it gives you the same answer, and you should increase your level of confidence in it. So the more measurements you take of different sorts, the more accurate your conclusions is going to be. So that's what we would hope would be happening when we do research. But sometimes it doesn't happen. And this is true in the real world too. So the example Nick Chater gives is, where does a rainbow meet the ground? You just can't do this triangulation anymore, because if you're standing here, it's from that direction. If you're standing there, it's pointing to a different place, and it moves around with you. So more measurements isn't going to help you. They're all going to give different answers. And there's lots of research in psychology that you can point to that sort of hint at this direction. Let me give you my favorite example of this, which is this paper, which was published in Science in 2005. Petter Johansson and colleagues wrote this fantastic paper, Failure to Detect Mismatches Between Intention and Outcome in a Simple Decision Task. So the task they give participants is a sort of face perception, face attractiveness task. So you get given two faces, and you say to the participant, which face do you find the most attractive? And the setup looks like this. So the participant is sitting opposite the desk, and you show them two faces, and the participant says, that one. And then, literally using a card trick, you show them the other face. So you'll notice this person is pointing to this face, but some kind of card trick gives them the other face. So what have we done there? We've done a comparative judgment. Well, what's Petter Johansson done? He's done a comparative judgment, and then he says, well, I'm going to ask you, using a different method, some kind of retrospective interview, to explain your judgments. So in the space of about 3 seconds, he's using two different methods to try and understand his participants' face preferences. And the fascinating finding is, when you do these switches using your card trick, very few people notice. So only 13% of people notice they've been given the other face. So that's already a bit weird, but it gets weirder, because you then say to them, can you explain your decision, please? And it turns out people just do. They just do explain. They say, oh, she looks like an aunt of mine, and she seems nicer than the other one. Or, she had more personality, she was more appealing, or whatever. So people confabulate. And there's tons of studies of this sort. So this isn't some weird, it's just a nice, the sheer temporal location of these two conflicting responses is kind of striking, I think. So the Johansson summary, people don't notice these mismatches, but they offer these introspective reasons for why they chose the way they did. They call this effect choice blindness. And the Nick Chater interpretation of this is that people just do not have stable beliefs and desires and intuitions. They make them up as they go along in some kind of improvised acting way. So you go through the world concocting reasons and trying to understand your behavior as an observer, and then retrospectively justifying them if required. So if this is right, you can measure these sorts of intuitions in multiple different ways, using methods from all sorts of different literatures, but you're just going to get incoherence, because there's just nothing there to measure. There's no coherent intuitions which can be measured, would be the Nick Chater argument here. And he does, interestingly, draw philosophical implications from this in other areas. I don't know if you haven't been to London recently, there's a very controversial movement. Bentham's been moved into this big glass box, which has upset lots of people. It's worth exploring that if you haven't been there recently. But so the Chater argument is, look, utilitarianism is going to fail, not because of any of the standard reasons, but just because people don't have stable utilities. So you cannot maximize utility if it's not a stable property. And there's no reason to think it is. So if this view is right, it really does have very serious implications across a whole range of domains. So the Chater hypothesis would be something like this. Mathematicians don't have any stable notion of mathematical aesthetics. They literally make up their minds as they go along, based on an attempt to stay in character. So all behaviour of this sort would be some kind of improvisational acting. And I think we do even have some evidence already that this might be true. So Andrew and I did a paper some while ago now where we tried to manipulate people's aesthetic judgments with irrelevant things. So let me just say, if it's true that staying in character and improvising is what's going on here, then you ought to be able to push people's judgments around with irrelevant factors. And we did that a while ago, where we looked at whether telling people the author of a proof changed perceptions of its aesthetics. And it turns out it does, or at least it does if you're a pure mathematician. Our account for that was the applied mathematicians didn't know who the author was. But there's at least some evidence that this ought not to be possible if people were making a genuine aesthetic judgment of the text. So at least some aspects of aesthetics are not purely aesthetic. Okay, so I'm not saying I think this is right. I just think we really ought to take this seriously in the context of mathematical aesthetics, possibly in other contexts where we make strong claims about the existence of mathematical intuition without really particularly compelling evidence that what we're talking about exists in a stable way. And if this Chater type account is right, I think it would have a kind of interesting implications for lots of things we've talked about at this conference, I guess. So I will stop there. Thank you.
Thank you very much, Matthew. Valeria?
Okay, thank you very much. I have lots of questions, but I'll make it short. I'll ask more than one, but short. So 2 are qualificatory questions about your experiments. The first is about what is the psychophysics of your comparison when it comes to equations and proofs, because to some extent you have some distance effect. You might have some distance effect. Did you check for that? I mean, something that it's really, really beautiful against something that it's really, really not beautiful. That's the first qualification. The second qualification is about the experiment when you asked to make comparisons later on with, the one inspired by Kova and Paines. And my question is, why didn't you put the discipline, like a theorem in number theory or a theorem in, because it could be that some disciplines are more visual than others, or I don't know. It's a question. And then third question, because as I said, I have to keep it short, but I have more. There is some work that I found out about recently that I think it's UCL on the neural correlates of mathematical beauty, and I really want to know what you think about it.
Yeah, okay, thanks. So question number 1 is, do you get distance effects? And yes, you do. And in some sense, the Bradley-Terry model allows you to so basically how it works is the Bradley-Terry model assumes that there's some underlying true score you can attach to the dimension that's being perceived. So in this case, it would be darkness. You know, the one on the right has a higher darkness score than the one on the left. On this one, it's shoe goodness. I don't know what it is, but it's some property. The one on the left has a higher shoe goodness than the one on the right. And essentially, the Bradley-Terry model says, well, look, if that's right, you should get bigger agreement when the distances are bigger, you know? So what you do is you do many comparisons of these. Imagine a sort of matrix of comparison, you know, object 1 and object 2. Then you try and populate that matrix with lots of responses. And where the distances are bigger, you would expect more agreement about which one's right. Where the distances are very close together, you would expect 50-50. The slightly surprising and counterintuitive result is it turns out you can fit the model with a really sparse matrix. So you don't need to populate that matrix very much at all, and you can still reliably fit that model. So that's the slightly weird thing about the Bradley-Terry model. But yeah, absolutely. So if it wasn't the case that there were no distance effects, you wouldn't be able to fit the model.
So how could you check for that in the case of equations and proofs?
Yeah, absolutely. So you just end up. No, we just picked it randomly. But the fact that we get a nice range there tells us that we do have, you know, a range of. And your second question was yeah, that's interesting. So to be honest with you, it wouldn't have occurred to me that I'd expect a difference there, but the fact that you think you might is interesting. Why?
I'm wondering, I mean, I'm not sure, because maybe some, and also, it's a problem though, because then, you know, you would have to check, it's a problem with testing mathematicians, because then you would have to check who are they, I mean, in which disciplines they are.
Yeah.
But I was wondering whether that could be more informative.
So I guess, I mean, that can't be the case for beauty because there's no disagreement. It might be the case here, I suppose. So maybe.
No, but maybe there this is something that's more abstract to some extent, so they would agree. But about being beautiful or not beautiful, maybe it's connected to the discipline they know more, or the visual features of one discipline compared to another. I don't know.
Yeah. I mean, you know, easy extension. Yeah, okay. And sorry, your third. Oh, yeah. So I'm not a neuroscientist, and I'm generally somewhat skeptical of the insights one can obtain from neuroscience. I don't know enough about that particular paper. I have heard people very skeptical that you can draw straightforward comparisons between neuroactivation while looking at paintings and while looking at equations, and there's all sorts of other reasons you might get the same activation. You know, you're also looking, you're also trying to draw some. You know, so there's all sorts of reasons why, but I'm not competent to pronounce on that. But
That's exactly what I wanted to hear.
Okay, Louis. Nice. I had a small question on this. I just don't understand why you say normativity score, because it seems to me it's more like along the line of subjectiveness. Like, you know, how subjective it is or how objective it is. And yeah, maybe mathematical beauty is more subjective than mathematical novelty or whatever.
Yeah.
So maybe you can, and this is one small question, but should I ask another one now? Maybe I'll have another question afterwards, but you can answer this.
So so the straightforward, what's on this axis is simply the proportion of people who answered this answer. And the reason it's called a normativity score, well, essentially it's because that's what Kober and Payne called it, but that's what they describe as their normative response. So it's the proportion of people who are saying, no, there is a true answer to this. We don't know which it is necessarily, but one of them is right and one of them is wrong. So I agree, it's pretty similar. The reverse is, I guess you could call all of these subjective, I suppose, if you wanted to. Although maybe not, the two in the middle might not be. But yeah, I suppose that's the reason, right? Those two are not really subjective answers. Well, maybe they are. I don't know.
I mean, that's fair enough. That's terminological, but I understood it that way. No, and another point, I really like your point about the flatness of mind, but I was wondering how much you investigated the idea that taste is socially constructed, as opposed to, like, you know, being something in your mind which is deep in your mind, or being something you just confabulate on the fly.
Yeah.
But it might very well be, and there's a lot of studies in sociology that tells you that aesthetic judgments are socially constructed, and some things are beautiful because you're born and raised in an environment where you ought to think that this is beautiful. And what about mathematicians, right? I mean, what do you think that mathematical beauty is something that we learn through social practice?
So I think So I think that is definitely something we should take really seriously. So, and I think there's a lot of reasons to think that there's good reasons to think what you've just said is true, I think. So partly is this study I did with Andrew, which, telling people the author of this proof, telling people the author of the proof shouldn't make a difference, but it does. Okay, so that's one bit of evidence. I think there's other, historical account, people who know more about history than me will be able to pronounce more on this, but, Cantor got a lot of criticism when he first did his diagonalization proof. Everyone said this is terrible, awful. Now it's held up as a
very weird. If that was genuine aesthetic judgment, what's going on there? There must be some social factors. So also, the equation that came at the top of our list by some distance was the e to the I pi, which everyone said, oh, it's beautiful. So yeah, I think if you are a mathematician, you have a really good understanding of what it means to be a mathematician, because you observe mathematicians, you observe yourself, you see the social, you know how to play that role really well. So if there are certain aspects of that role that require you to say e to the I pi blah blah is beautiful, you can do that. And if you know Cantor is now widely regarded as a great person who did a very clever thing, you can say that's beautiful. So yeah, I think that would be really consistent with the Chaytor way of thinking, because the social context gives you the cues with which you use to improvise. So an interesting question is how much that could apply to more genuinely mathematical intuitions, which I don't have an answer to. But I think it's something perhaps is worth thinking about.
Okay, Dirk?
Thanks, Matthew, for this presentation. When I teach philosophy of mathematics, I present Inglis in Aberdeen 2015 as one of the top 3 papers written this century in philosophy of mathematics.
Gosh, wow.
But I have a question.
You need to be replaced, Dirk, as a teacher.
Yes, I was very scared about your second paper that you mentioned that seemed to question that. And I have a question about that because, the first question is, you had the equations in Mandarin and in what we write.
Yeah.
One question is, why are they so different? Is it that that just every symbol is translated into a longer expression, or are they also structurally different, these two?
Yeah.
And maybe related to that is, did you kind of, or have a sense or check whether there's evaluations that were given, whether one of these equations is more beautiful, correlate with something like symmetry or shortness or simplicity?
Yeah.
Because if you would say yes, then that might explain the consensus that it's actually not the equation, but kind of these other more general aspects of the expressions that are being evaluated.
Yeah. So on the translation, so I don't speak Mandarin, but the way this normally works is you get someone to translate it from English to Mandarin, and then you get someone independent to just translate it back, and someone completely different, and then you get the extent to which you get, you can evaluate the extent to which the translation seems robust. So that's what we did, and so the idea was literally just get someone. In fact, one of the people who did the translation wasn't very mathematical at all, so there was no real, it was just translation. There was no sort of thought behind the translation in some deep way, but the back translation worked, so it did seem to get what we were hoping for in terms of the translation. You seem like poised to say something.
No, I completely misunderstood what was going on. I thought that the translation would be a translation of the equation, but it's actually...
Oh, I see.
Okay, so
No,
forget
just
my
of
question.
the,
Yes,
just of the
so
text.
the equation is actually exactly the same.
Correct.
Okay, I misunderstood.
Your second question was, what was your...
Whether that correlates to symmetry or...
So yeah, we did do some exploratory stuff on that. Now, I don't want to mislead you. So take what I'm about to say with some caution, but look at the paper if you want to make sure I'm right. So it was the case, as I recall, that the number of symbols correlated with beauty judgments. The trouble is how you operationalize that is a bit tricky, right? It's not straightforward how to do that. And also it was pretty exploratory. We also looked at whether, so like this one talked about like a famous person, and we thought, oh, maybe that might play a role. As I recall, that didn't play a role. So I think there were 3 things we looked at of that sort, but it was kind of pretty exploratory, and it had no strong predictions, so I wouldn't really want to make strong claims about it. But yeah, we did do that, and the simplicity one was one of the ones that came out, yeah.
Thanks.
Although I should say, again, it's really not straightforward to know how many symbols that has. So
Jima?
Thank you. This is really interesting, and I haven't read The Mind is Flat, so I probably shouldn't try to critique it. But there's something about assessing beauty that seems, assessing beauty seems to have a temporal factor in that getting to know something, you may find it more beautiful with time. And all of these experiments are necessarily, for different kind of economical reason, quite short. And I wondered how to reconcile that.
Yeah, that's interesting. So, so I think if you want to take that argument seriously, you have to posit two different types of aesthetics, actually, because people are very willing to make these. Sorry, I don't quite know what's happening here. People are quite willing to take these. Oh, I see what's happening. People are very willing to make these judgments. So it's not the case that someone says, I refuse to tell you which of these two equations I think is the most beautiful. You know, people are, the question makes sense, they do it. So I guess your point would be, well, maybe if you allow them to study it in detail, they would come to a different judgment. Now, that might be true. I think, in my terms, that would no longer be an intuition, because it would require some kind of reasoned process. It would require some working memory capacity, blah, blah, blah. So I guess that's why I'm not so interested in that. But yeah, it's interesting. I don't know. Yeah, I don't have strong views on whether you're right or not. But it could be studied. But I think it would be studying something else.
Yeah, I mean, one of the first things you said about intuition was it was quick. So I know that wouldn't fall under that category anymore. Thank you.
Romain?
Yes, thank you. It's my question goes a bit to the same direction, I think. So I don't know. In my ideal setting would be to observe these judgments in their natural environment, so to speak, without triggering them, and especially not triggering them in short time, and maybe also on items where usually people would just not give any make any aesthetic judgments. So I was thinking about another attribute, triviality. You call something trivial in mathematics, and this has a lot of different functions, and you will use it really. I mean, depends what kind of human you are, personality, but you will be careful using it. Yeah. So you might call a theorem trivial in front of your peers. Maybe with first semester students, I mean, they do it, but maybe you shouldn't do it because you will just demoralize them. So what about this kind of perspective, if you want to do a triangulation, looking more at what's actually the function of aesthetic judgment in mathematics or in texts about mathematics? At the time, very often it's not about expressing an intuition, but more praising something, for example, or saying that's the kind of stuff I would like to have for myself and for my students, etc.
Yeah, no, that's a good point. So several things to say about that. So one thing some colleagues and I have been doing over the last few years is doing large-scale corpus linguistic analyses of various mathematical texts. So one thing I thought, maybe, how do mathematicians use this word in published texts? And it turns out they don't. Aesthetic judgments don't turn up in writing very much. It's kind of interesting. So I think it's non-trivial to find a context where that happens. So the other place we tried to look for it is in prize citations, and then they use it. So like mathematical prize citations. Winning the Abel Prize or whatever. There, they use it all the time, but do so in a completely there's just so much of it. You don't know what's going. Don't know what anyone who wins that is deemed intuitive and deep, and so it's really hard to interpret. So what you really would love to do is be in the discussions about those in the debate, the committee discussions about who should win the Fields Medal or whatever. So that's one thing to say. I would love to do that. I don't know how to achieve that. The other thing is you can also do referees' reports is another place for looking at that. And in fact, coincidentally today, Christian Greiffenhagen from University of Hong Kong, I'm not sure, somewhere in Hong Kong anyway. Just emailed me today actually saying that his latest 2 papers on mathematical peer review have just come out. So he actually did do quite a detailed study of the process by which people make judgments of importance in a peer review context, which you could say is getting a bit aesthetic maybe. Not quite clear what that means. So yeah, I think that's another way of trying to do it. And it'd be interesting to work out how to do that at scale, which I think there are ways to do that actually, but yeah. No, that's a good idea.
Thank you.
Okay, so I think we can thank Mathieu again.
Thank you.
So we have a short break and then we continue with Jessi. No. Does it work when you talk?
Talking, yep.
Okay.
Yeah,
Maybe you
it's
can
projecting.
a little bit,
Higher, okay. I get loud once I start talking.
Sorry?
I get louder once I
okay,
start.
so you can stay here. Yeah.
Maybe I'll.
Okay, everyone. Okay, see you, Tabea. See you next time. Okay. So we'll start with the. So we are a bit late on the program, but that's okay. So last but not least, we have Jessi's talk. So I'll just take 1 minute for people come in. Just let them come back slowly.
Yeah, you're good. Long day.
Okay. Okay, we're ready. So we have Jessi from Utah State University, if I remember correctly. Yeah, Utah State University, and she's going to talk about conceptualization of intuition construct in the mathematics education literature or mathematics education research. The floor is yours.
Thank you. Just gonna set a timer here. Okay, got it. So first, I just want to thank you all for the opportunity. It's been probably one of the best experiences being in a space where there's a focus on intuition and the focus is explicit. And so today, I'm going to discuss some research that I began in my doctoral studies with my dissertation at the University of Oklahoma, and continued this exploration into my postdoc at Colorado State. And I'm still thinking about these ideas as a professor at Utah State. So some of the big questions, I really can think that I can condense them down. One, I think about what is mathematical intuition and how do we define it coherently? Is there a way? Two, what does it really mean to develop students' mathematical intuition? And three, what are instructional methods or novel innovations in instruction that might develop student intuition? And four, is there any way that we could study the efficacy of these innovative instructional methods? Is there any possibility there from an empirical standpoint? So here's my overview. I'm not going to answer all those big questions today because they're too big. But I'm going to talk about an introduction into math ed research and challenges surrounding the intuition construct in the field. Then I'm going to discuss an integrative literature review. There are three foundational cores in our literature: Fishman et al.'s corpus dual process theory and concept image concept definition. So many of the researchers who are studying intuition in an education context are pulling from these cores when they study it. Next, I'll discuss boundary properties of the intuition construct based off of a particular literature sample. And I'll talk about classifications for different types of intuitions based off the same literature sample. This work has been published in the Journal of Mathematical Behavior, and I emailed the paper so that you guys can see the references. It's quite a long list. And so next, I'll be presenting an in-progress methodology. This is very preliminary. The goal of this methodology was to improve researcher and educators' visibility of students' intuitions, specifically the qualities of student intuitions. And then I'll discuss some future directions for specific to math education research. Okay, so what are some early beginnings and challenges in the field? Early beginnings in 1959, the role of intuition in learning and thinking was a working group topic at the Woods Hole Conference. And at this conference, they stated, "It is certainly clear that procedures or instruments are needed to characterize and measure intuitive thinking, and the development of such instruments should be pursued vigorously, and that precise definitions in terms of observable behaviors is not readily within our reach at this time." In 1978, the second international group for PME met. This is a conference, and again, intuition was of explicit focus. Intuitive and reflective processes in mathematics was a working group led by Fishman and Skimp. In 1999, we see that explicit focus begin to fade. Burton interviews 70 mathematicians and asks, why is intuition so important to mathematicians, but missing from mathematics education research? With the notable exception of Fishman's work, accounts of deliberate nurturing of intuition and insight is absent from mathematics education literature, even from process-based research, and despite the claim of the centrality to mathematical work, it is absent from practices with our students. In 2008, there's been evidence that researchers are actually working on this topic still, but they're having a lot of difficulty. So many researchers are saying that it is a loaded and slippery concept. In general, the field needs to work towards an updated compression to prove coherency of the construct and to avoid disorienting theoretical inflation. Okay? And I'll kind of show you that theoretical inflation in a little bit. Finally, in 2014, we have a push to develop standard working definitions. And Keene makes a very good point. A person's intuition regarding a subject is difficult to measure given the myriad of factors. Furthermore, researchers have difficulty even defining intuition. We have a difficulty to illustrate intuition altogether, even though we know we have some sense that we have them. And so we can see that the challenges really are both theoretical and methodological. So current state of research on intuition in undergrad math education is active, but has disappeared from collaborative platforms of working groups or specific special issues in journals or collective disseminations. The last compression, I think, was probably Fishbin 1987. This predates the first special session on Room, or the formation of the field, really, in 1991, and later, more formally, in 2001, and a surge of contributions by these researchers. Educational studies on intuition at the collegiate levels builds from these cores, which I'll now describe. So just to give you a feel for dual process theory, here's a famous prompt. A bat and a ball cost $1.10 in total. The bat costs $1 more than the ball. How much does the ball cost? Let your mind just give you a quick response. So without doing any calculation, what is your mind telling you? Don't calculate. Okay. brave soul saying it out loud. Yeah. Okay. So let's see what's going on here. So let me just keep that in mind, and let me just talk about dual process theory, and we'll come back to that, what they found when in several studies running that prompt. So dual process theory says that system one is intuitive. It's automatic, effortless, associative, rapid, and skilled action. This is contrasted between system two, which is reflective or analytic. It requires computational control. It's deductive, it's slow, it's serial, it's rule-based. And that there's this sort of idea that when we're making decisions, system one will give us an immediate response. And this is highly desirable because there's very little computational load. Intuition is nice, doesn't suck up much working memory resources. And then system two comes in and is supposed to check that intuitive response. Does it feel, is it correct? Is it incorrect? Should we go ahead and check our work with proof or computation? So system two should kick in and reevaluate system one. That's how it should work. So what they found in the psychology study where they applied the bat and ball prompt is that 17% at the University of Toledo got the prompt correct. 66% got it correct at MIT, but the rest erred. And the common error response was $1. The correct response would be $1.05. So what's going on here? The source of error would be considered attribute substitution. So our non-conscious processes make implicit substitutions, or there's implicit mechanisms going on that are basically making a complex problem simpler, and then you err. So let me describe that. So substituting a harder problem for an easier one. So maybe you just read the following, maybe your implicit mind read the following prompt. A bat and ball cost $1.10 in total. The bat costs $1. How much does the ball cost? And then you might say 10 cents. Okay, so there's been an attribute substitution. Instead of more than the ball, you've created a period costs $1. And that's the non-conscious process trying to give you a rapid response. However, the system too should kick in and tell you actually the answer should be to this question $1.05. Okay. In research and undergrad math education studies, they've applied dual process theory to study learners' errors. One big study was by Hazan and Laurent in an abstract algebra setting. And they asked the following prompt to 113 abstract algebra students. Z mod 3 is a subgroup of Z mod 6. In your opinion, is the statement true, partially true, or false? What they found is that 73 students erred on this statement, and they misapplied Lagrange's theorem in a way that was not logical at all. They said it's true because 3 divides 6, which is actually the converse of Lagrange's theorem, and the converse does not always hold. So they misapplied the theorem. They made a logical fallacy. This is a failure of system 1 for hastily reacting to surface representation cues. So if I'm looking at this as a learner and I see the numbers 3 subgroup and a group 6, I'm immediately thinking, ooh, Lagrange's theorem, because if the order of H divides the order of G is part of that statement of the theorem. So your mind instantiates that theorem, pulls it quickly, and you apply it because it's accessible. But S2 has failed to monitor or override or reject that very quick reactive S1 response. Moving on to Fishman's corpus, which is quite large. Fishman had a huge career. He studied intuitive cognitions, which he stated appear directly acceptable as self-evident without proof in hand. These are also called proof, which contrast with proof-based cognitions, where there's a basis, they're considered true on the basis of a logical proof. Properties of intuitive cognitions, he defined self-evidence as the main attribute. So confidence in truth without need for proof. So your intuitions feel so true, you don't feel a need to prove them. And immediacy. Immediacy was another main attribute. And then there are several other attributes: intrinsic certainty, perseverance, coerciveness that he defined. So for example, coerciveness is this idea that once you have an intuition, it's very difficult to change. It's often hard to see other routes once you have it in your mind. And he also went on to classify various types, a lot of types of intuitions. So the primary one being used is the classification between primary versus secondary intuition. Primary is that's based on everyday experience versus secondary intuition, which is acquired via some educational intervention. And along with Fishman's corpus, I would also put intuitive rules theory in there, because Stavi and Tirosh built from Fishman to identify sources of learners' errors that are common across a variety of student populations. Misapplication of everyday rules. And it also draws from Kahneman and Tversky's research program on heuristics and biases employing dual process theory. And so what the literature has shown is that university learners invoke intuitive rules, same A, same B, more A, more B, adding makes bigger and division makes smaller, which leads to error. So there's a huge focus early on intuitive errors and their sources. So here's an example of the intuitive rule more A, more B being applied in a conservation task. So this is with a child in Piaget. So a lot of the field builds from psychology and a lot of the psychology literature. There's not much on advanced learners, so some of it's more on children starting off. So here we have a conservation task where you can see that the 2 cups have the same amount of water, and then the water is poured in a taller beaker, and the child says, oh, that taller beaker has more water in it because it's taller. So more height, more water. And clearly that's an intuitive error. And what the literature shows is that this is called, if the child were to say, oh, they're still the same, they would have been said to have conservation acquire conservation. That usually occurs in later developmental stages of learning. So here's one that they gave to teachers, so adults. Intuitive rule, or later on in rerun, but I'll do another one. So intuitive rules identifying sources of error, same A, same B. So they gave this rectangle and they turned it sideways and they asked several different populations, is the area the same? And then the second question they asked is, okay, well, if I take that rectangle and I create a cylinder by gluing the edges, and I take that rectangle and I make a cylinder by gluing the edges, which one has more volume? Okay, so same area, should they have the same volume? Okay, so they're trying to get at this same A, same B rule, intuitive rule. Okay, so what did they find? They found that, so the correct answer is that the volume of the cylinders is going to be different. However, 85% of upper grade levels said that they would be the same. In fact, the volume of the wider cylinder to the left is larger. 15% of the upper grade levels actually got this correct, so not as many. This is just on the graph here. So the solid line shows that to the first question, do they have the same area even though they're turned? We see that as ages go on, so this is first through second grade up through 8th through 9th grade, that they become more accurate in conservation and answering the question of same area. But as we get older, it looks like they're erroring more on the second question. So in summary, basically, Stavi, they've run a ton of studies, and they actually have found that even adults and educated collegiate students will apply these intuitive rules and error across, and this is true across many populations. The other theory is concept image, concept definition, and I'm just gonna, I should probably kind of hurry up through this. So the idea is that the concept image is just the total cognitive structure, including all mental pictures, properties, and processes. That's very general. It can include metaphors, images, examples, intuitions, whereas the concept definition is just the plain formal textbook style definition. And so what they said in a lot of early studies is they said too often it's the concept image that drives students' decisions, and then it causes them to err. They're not checking against the formal definition or even calling the formal definition to mind. Too often the concept image is overriding. So it's this very negative thing. But Kendron, they also study this idea of treasured intuitions, this idea that part of the concept image for a limit definition of a function would be that gradual changes have gradual effects. And so that might be a concept image that students will pull and use, and that actually will cause error and is at odds with the concept definition. In my dissertation, I started looking at semiotics and this idea that you can fix a concept and have different ways of representing it, and those different representations are part of the concept image that a student might have. So here I actually found a case where a student did apply the formal definition. So the first thing he pulled was, he said, and this was in the context of creating quotient groups, sorry. So abstract algebra, they're creating a quotient group from a dihedral group, and they're claiming that there is one to Z4. Turns out there's not. But this particular student pulled the formal definition of a quotient group or to construct a quotient map. So he pulled the definition of a homomorphism, essentially. He could state the formal textbook definition beautifully. But then when he went to actually construct that homomorphism object, he made an error, and he ended up erasing vertices and tearing edges, which is not what a homomorphism does. A homomorphism preserves structure, and this student's concept image was totally, even though he had the formal definition, he had aspects of his concept image that weren't in alignment and again erred. And so what might the student be doing here when he says, okay, I can go from this graph on the left to this graph on the right? I think what he's doing is he's just trying, and I have evidence to suggest that he's trying to reduce visual complexity. So the intuitive mind, these intuitive mechanisms are trying to reduce visual complexity, trying to make a complicated problem simpler, and then the error occurs. So let me go into the literature currently on what's happening in depth. So what is an updated conceptualism intuition construct? In other words, how might we define it? So the attempt to find a common definition for a great variety of meanings, features, and connotations seems to represent an impossible task. Intuitive knowledge seems to cover the whole domain of cognitions. And I think throughout this workshop, I realized that there are many types of intuitions, and I think we're all describing different constructs, really. So these are the 4 phases I went through during this literature review: exploratory, systematic, ongoing, and I'll talk a little bit about my methods. So during the exploratory phase, I was like 2018, 2019. I was kind of just getting started, and so I was going to room conferences a lot, research in undergraduate math education, and these are some of the things that were going on. So there's talk about mathematicians' methods for developing student intuition via examples and real analysis, and expectations of mathematicians on the presence or absence of their students' intuitions. They were also describing mathematical intuition as an indicator of maturity. We're also seeing that there's a variability in mathematicians' formal definitions for differentials, and they also describe that much of the intuition of these mathematicians is not expressible in words. There's also a talk on the geometer's creation of student handouts to facilitate student intuition in an algebraic topology course. So that's kind of what the landscape looked like at the conferences. But here's what the landscape looks like more broadly. And so it's huge, and it's all over. So maybe let me just point to like the theoretical frameworks and the key constructs table on the far right. What you're going to notice is that these researchers are throwing a ton of different theories and frameworks at intuition to try and understand it and study it. And I think that's the big idea, is that this is really difficult. So limit definition in calculus is a topic, Euclidean geometry, statistics in physics and Euclidean geometry. Function concepts are a big topic, and optimization of area and discrete algorithms. Here they were trying to validate or invalidate the existence of something called optimizing intuition on the last line. So there's quite a variety of studies that are going on. We also see the studies mixing cores. So it's not just that they're applying concept-image definition, but they're applying concept-image definition with dual process theory. They're mixing it with Fishman's corpus. And there's just these mixing of, or networking of theories to try to tackle this construct. So what did I do in terms of sampling? I gathered 816 papers. I pulled from 4 big journals in the field that published at this level: Jeremy, ESM, JMB, ZDM. From 1987, the last compression, to 2020. Later on, I added IJROOM, International Journal for Research in Undergraduate Mathematics Education, i.e. ROOM. This sample was added later on. At the time I started the review, IJROOM was very new. IJROOM published first volume in 2015. So I didn't add that sample until later, but it's there now. And so here, though, these graphs are not with IJROOM in it, because I constructed these graphs before I added the IJROOM sample. But the idea is the following. You see in blue, these are our papers, and this is basically how many papers in that or in this case, it was like 700 something. How many of those papers referred to intuition in the paper, or intuit, I-N-T-U-E-I, intuitive or intuition. And we see that a lot of these, we have a good number of papers referring to the construct intuition, but if I look at how many people are focusing on the intuition construct explicitly in the abstracts, you see those numbers drop dramatically. So these brownish bars are how many people are referring to it actually in the abstract. So a lot of people are saying the word, but nobody's really being explicit, or not as many people are being explicit about it. And this is just separating by journal, and the same trends hold. So ESM seems to be the one where there's a lot of, the term intuition is being used a lot, but similarly, there's not much going on in the way of intuition being in the abstract, but maybe there's something there at that spike on the end. I should investigate this a little bit further. So maybe there's, yeah, I guess there's not really a spike. What is this? Oh yeah, ZDM, I guess, had a spike here. So maybe I should see if something went on with, maybe there was a special issues, but. Next I did a systematic phase. So what I do, I took all these papers and I had them ordered. I was using in vivo from papers that were using the word intuition most frequently, to those or not, and 411 articles were using it less than 3 times, which means that half of my sample probably wasn't explicitly focusing on the construct, but was just saying the term kind of as a here and there kind of thing. So I read the top 150 articles in full, and this figure to the right shows the top 50 articles in the field. I isolated chunks surrounding intuition, and then I coded them, and I'll show you how to code them in a little bit. First, I used some sort of automatic coding. So there's auto-coding of themes in a lot of these softwares I was using in vivo. And so here are some of the auto-coded themes for intuitive and intuition. Intuitive subthemes include rules, probably intuitive rules from intuitive rule theory. Sources, sense, cognitions, beliefs, interpretations, meaning, description, conceptions, bear on the formal, theory, structures, non-examples, nature, processing, judgment, solution, argument, representations, estimations, thought, clear, insight, feel. And we see a bunch of types of intuition showing up here on the right. So these were, I separated intuitive and intuition because I don't think they're the same exact meaning of a word. But types of intuitions are secondary, primary, geometric, deep, probabilistic, optimizing. And if you have a question about maybe a definition of one of these types, I can refer you later to the correct paper. There's treasured intuitions, he's same, relevant intuitions, naive, everyday, Kantian. So there's some philosophy coming in. So how did I also checked the representatives of 3 cores in the sample. So in terms of who's using what cores, the most dominant core was Fishman's corpus, followed by intuitive, followed by concept image, followed by dual process. At least 324 used at least one of those 3 cores. Each of the top 50 referenced at least one, if not more than one. So method of manual coding. So to remain open to a variety of characterizations of intuition, I adopted the view that mathematics education researchers have not been studying the same cognitive affective phenomenon under the label of intuition, but rather a vast class of phenomena that share a family resemblance, much like a class concept. So I decided I needed to build some sort of, or construct some sort of class concept for intuition, the intuition construct. So I used Piaget and Skemp's ideas of how to build the class concept, so coming from structuralism and psychology. So first step is to define invariant boundary features, identify belongingness to existing classes, grouping. So maybe we have a bunch of instances of intuitions. What are attributes among those intuitions? Can we abstract them? Can we form a classification of intuitions for a particular type? Then we have formation of the conceptual structure for the construct and continual maintenance via assimilation and accommodation. So the idea here is that we're trying to form this big conceptual structure of what intuition is, and we can add things so we can assimilate. So maybe we have a structure, but the yoke isn't there. So the inner frame is missing, but the surface frame is there, but we're missing the yoke. So we would depend on the environment. There are contexts being developed or instructional environments being developed, such as inquiry-oriented environments and guided reinvention, where students' intuitions are given societal support within the classroom and are deemed at the level or value of experts' intuition. So they're very much valued. So that's environmental. So these boundaries, I think they're context dependent. They're dependent on the environment. Some of our boundaries are talking about certain types of intuitions rather than collectively the construct as a whole. So what did I do next? So I tried to understand the component view. This comes from psychology. So the component view of intuition states that it's a process outcome object. So
So there's an intuiting process, there's attributes associated with that process, and then we have the intuition outcome. And so I found that despite some parallels, there's a major component of mathematical intuition that was not emphasized by this process outcome component that psychology sample makes. In mathematics culture, the intuiting process that comes to us and the realized outcome is not always strictly non-conscious or without awareness. So they talk about the process as being non-conscious. But in mathematics, we often refer to intuitive thinking or activity as drawing sketches, which is very intentional, using manipulatives, constructing visual models, and informal rephrasing of formal objects or theorems. The de-emphasis of a conscious intuiting processing component in psychology sample may boil down to a difference in decision-making environments under investigation. When psychologists investigate the intuition of chess players, firefighters, military personnel, they're studying subjects who are surrounded by a natural scene of visual or perceptual cues. And the intuiting process can immediately act on those cues to produce an outcome. However, in mathematics, we often have to paint our own scene. The cues are not just readily available in front of us, and so we have to invoke what I would term conscious intuiting methods, such as developing models and developing these figures, or even working really hard to try and come up with some metaphors. Okay, so what are some methods that I find? Constructing tactile models, geometric and informal paraphrasing of formal definitions of theorems via diagrams, developing metaphors using computational tools, translating axioms, objects, and theorems across mathematical systems, and effective regulation strategies. So this idea that when we're sitting there and we're given something, some sort of problem to play with, what do we do to gain ideas? What does the intuiting process like to eat? And these are the things that the intuiting non-conscious process likes to eat. They like to eat metaphors and visual stimuli. We could also think of methods as effective regulation strategies. So while intuitive methods described above, they provide sustenance for the intuiting process to operate. According to Noddings and Shore, there's a stage that may precede the first clear intuition. During this stage, the intuition is looking but as though in a darkened room or at a great distance. The feeling that accompanies the stage is discomfort. We are impatient, uncertain that anything will be accomplished, doubting our own capacities. This is the stage of mental torture. Thus, intuiting methods to support the intuiting process could also extend to effective regulation strategies, especially those that help learners drop into a relaxed state of mind, in which the objective is to follow curiosities that come from within, rather to produce formal products or to please an authority. So here's the classification scheme. I'm not going to go too much into this, but here's one classification scheme I found. But anytime you're trying to build a class concept, what you realize is the classifications depend on the attributes that you're paying attention to. So there's tons of attributes flying around, and depending on which ones I choose to focus on, the classes, things are going to get shuffled around into different classes, depending on what attributes I'm focusing on. But let me just show you the course's classification scheme that I came across. Non-creative versus creative forms. Let me check the time really quick. Okay. So two different classes of intuition, non-creative forms. The intuiting process is reproductive, much like in Kahneman's study with the bat and the ball task, that quick reactive type intuition, little reflection. It also is lining up with intuitive rules like more A, more B. Matching associative forms that we could just think of as basic pattern recognition. And recovery of already consolidated instantations. What I mean by that is, so an instantation, so if I give you a formal concept like isomorphism, Weber and Alcock stated mathematicians would pull this instantation. Two groups are isomorphic if they have the same Cayley tables up to reordering. Okay? So they had that in their concept image, they pulled it, that's the instantation. It's not quite formal, but it captures the isomorphism concept in some way. They actually found that students didn't have instantations for that concept, but they found the mathematicians did. So a recovery of those, already learned things that have been consolidated in the mathematician's mind, and they can readily access them quickly. Creative forms, though, They seem to operate as a form of tacit pattern generation entailing the organization of novel structure. They involve lengthy incubation periods and tend to be generative rather than reactive processes or reproductive processes. To give you an idea of the distinction between non-creative and creative forms more explicitly, here are some attributes that pull non-creative forms apart from creative forms. So personal novelty is the degree to which a learner feels that a particular intuition feels new to them and involves an internal comparison between their current state and past experiences. So the more novel the intuition is to the intuitor, so their intuition is to themselves, we would say the more creative the intuition is. So personal novelty. If it's something that feels like old familiar knowledge, like an instantation, that's not very personally novel, we would say that's non-creative. Incubation period and length and intention. So the length of incubation period, so the longer the incubation, the more creative. If there's no incubation period, we would consider that non-creative, so the reproductive kind. So incubation just means a period of rest. You often hear in like Hadamard and some of these other texts that mathematicians will say that they went on a walk or they were taking a shower and they got this hit. So that period of conscious rest where everything is relaxed, that would be considered incubation period. Emotional valence and intensity. So creative intuitions, intuition is often accompanied either with a non-emotional response or a highly emotionally charged response. So when you have positive emotions and high intensity, these occur with more creative forms, whereas more neutral or non-emotional responses, like kind of like you're recovering old knowledge, it's a fact to you, you're going to have more of a non-emotional response. So the intensity won't be as strong for non-creative forms. Ease of externalization. Something that's new to you, something that's novel, that's creative, can be difficult to externalize. So the more difficult it is to externalize, the more creative. The easier it is to externalize in words or formal language, the more non-creative. That's an indication of consolidation. Use of sanctioned, non-sanctioned representations. So now I'm getting into semiotics and things, but the use of sanctioned representations, these are commonly taught signs that feed the intuiting process. Those would be considered non-creative. So if a student is drawing something and it's something, a representation I drew up on the board, or it's in their textbooks all over the place, that would be considered a sanctioned representation. If they're using that to feed their intuiting process, I would consider that more non-creative. If they're actually making and generating their own non-sanctioned representations that I haven't found in textbooks that are really unique to that individual, I would consider that more creative, as if they're creating their own figures or representations or they're creating their own stimuli, and that stimuli doesn't look like what's in the textbooks, basically. Same thing with the outcome, we can think about that, but the next one here is network thinking and analogic reasoning. So network and analogic reasoning, I would say, tends to occur with more creative forms. So if you have an intuition, is it an intuition in which you arrived at it by drawing a connection across disparate fields? I would say that's more creative. Whereas if you're just in a particular pocket or a particular field, but you're not making networking kind of connections, that's considered more non-creative. So there are the attributes highlighted that we just discussed. And I asked the geometer about this framework to see what his sense was on it. And he related to it. So in fact, he was describing the creative form when he talked about his intuition. He said, you can spend a long time developing an intuition, and now you need to come up with a language. In particular, if it's very geometric, you need to come up with a language that's got enough metaphors in it that gets people on your side way of thinking. But it also has to be precise. You need to formally give, rigorous definitions and then prove things using them and so on. And that can take a lot of work, and some people are terrible at it, and some people are very natural at it. He also describes network and analogic thinking when he describes his intuitions. It could also be that this new environment is actually, a feature of something we already know, or even making a weird connection between two very well-known fields, but that are very far away from each other. That's very much, I don't know where it comes from, but that's very much intuition. So sometimes intuitions can take a decade even to coherently externalize. These would be on the extreme end of creative forms. Here's some additional attributes that I found that didn't fall into that classification scheme. So unique individualistic versus common collective intuitions. And maybe I can argue that we can talk about that later if you want. But then there's non-arid versus arid. Confidence and obviousness was another attribute. Temporal formation of the intuition either prior to or after systematic formal instruction, alignment or paradoxical conflict with the formal mathematics. So intuition may be in alignment or in some sort of paradoxical conflict like Banach-Tarski. So let me just discuss the significance of what I think that this is, this distinction is. So it's hard for me to hold all of this, so sometimes I have to look at the notes. So in summary, non-creative and creative forms of intuition are fundamental aspects of learning and evolving knowledge. The activation of non-creative forms provides directions on where to start and reserves cognitive energy to explore more complex problems. During the exploration, the learner invokes intuitive methods. This provides additional inputs for non-conscious intuiting process to work on and generate a creative intuition outcome. These may be difficult to externalize, but over time they can be recovered and repeatedly used. What were once creative intuitions can transition into more non-creative states with more non-creative attribute makeups. It is not necessarily that one, non-creative or creative, is superior to the other, but rather that there is not an imbalance characterized by an overabundance of non-creative forms and a lack of creative forms. And here I've just placed these, but so like the same A, same B rule, hypothesis, I would say that that would be tending more towards the non-creative and instantations, recovery of old knowledge, things that are repeatable ways that mathematicians think about a particular concept. Those seem to be more non-creative because they're just pulling the same thing they've done 100 times before. Whereas a correlational hypothesis, this is basically an intuition that's a big boom across fields. These are like the big theorems that come up. I would say that would be an extreme form of creative intuition. And then we have all these other additional attributes flying around, and we could ask questions about what happens if we cross the non-creative to creative distinction with something like arid or non-arid, or common and not common. So maybe I'll try to give you some data to explain why those crossings might be meaningful for the field to pursue. Okay, so this is very preliminary. The idea of this methodology is to make the necessary leap from an updated conceptualization of the intuition construct to a methodology that aligns with it, particularly the non-creative one that aligns with non-creative to creative forms in the attribute frameworks. And so I'm really just trying to capture the makeup or qualities of students' intuitions. Are they more non-creative? Are they creative? What is their makeup or attribute? What are the qualities of students' intuitions? Again, yeah, very preliminary. I don't have a ton of data on it, but here's what I have. So I had 2 graduate level learners from the same Central US University, Jenny as a first-year graduate, Alex, second-year graduate student, and they were in an environment where they were studying in this intuition type environment task I threw them in. They were exploring orbit stabilizer relationships. Okay, so I picked this on purpose because it's a rich setting. And they were given a bunch of examples of group actions. They were given the same set, but they were also allowed to build their own example spaces. So I'm sure they have their own examples of these different objects. But I wanted to make sure that they at least had some initial set, especially that first-year graduate student. From playing around with a bunch of examples of group actions of different kinds, so here's kind of 4 different kinds of generality, you can arrive at a lot of different results in theorems. So Cayley's theorem is probably the least advanced, and then orbit stabilizer theorem is a little bit more advanced, but maybe that's also subjective. What's more advanced, what's not, is subjective. So orbit stabilizer theorem, though, states that if you have a group, the order of G divided by the order of the orbit is equal to the orbit of the stabilizer. So that's kind of important for the data I was looking at. For data collection, in order to look at the qualities or makeup of students' intuitions, I was viewing each intuition they had, I was viewing it as like an object, a method, process, outcome object, and there's attributes attached to this object, and I was trying to get at what those attributes were. Maybe this is the best thing to focus on. I had them journal about their intuitions. I had them to give me succinct descriptions of their intuitions with the logs. I left it up to them. I gave them some basic definitions of intuition from the literature, but these were also graduate students that had been enculturated into the mathematical culture, and so I also allowed them to determine what they felt was their intuition or not. And then I created this self-report survey instrument, the NCCFIS, to get at these non-creative to creative attributes, like personal novelty. So for example, the item says, I have never experienced this intuition before. If they strongly agree with a 6, it's highly personally novel to them. Emotional intensity. The moment the intuition came to mind, I had an intense and positive emotional reaction, like feelings of euphoria, elation, exhilaration. If they strongly agree, that would be more on the creative end. Ease of externalization. I found it very difficult to externalize the intuition held in my mind in any way. Felt like I didn't have a coherent language to express it. If they strongly agree, that would tend to be more on the creative end. And then I also asked them about their confidence in the truth value. And I also looked at error and non-error type values. Why am I looking at a new instrument? So the instrument I'm proposing is local, a local instrument. It measures each individual intuition object the moment it occurs in the student's mind. So as the student has the intuition hit, they immediately fill out that survey and tell me what are the attributes attached to that particular cognitive affective object. This is very different than the global measures that exist in psychology, like the REIM, which are general preferences and overall beliefs. Using logic usually works well for me in figuring out problems in my life. These are very general. My feelings play an important role in my decisions. Again, very general. I'm an intuitive versus analytic person, so this is getting into personality theory. And these global estimations ignore the fact that intuition is fractionated. So you might have really good intuition in one area, but not another. I disagree that it's a personality style. My view of intuition is that it's a particular cognitive affective object rather than a stable personality, but I think you could go both ways depending on how you look at it, but the way I look at it in this particular work is that it's an individual cognitive object. Okay, so I'll just go quickly through a couple of results here. Okay, so what did I do? So they fill out these surveys, and I captured the qualities of their intuition, and I fed this data into the fuzzy C-means algorithm. This is just a clustering algorithm. It provides me with a makeup of prototypes, which are the cluster centers, and then membership functions. So the membership functions assigns some sort of cognitive affective objects to the intuition object, and membership value to certain clusters, and then I can get a feel for what is the makeup of that object. I ran some descriptive results first. So Jenny is on the left. She reported 11 intuitions. Alex on the right reported 6 intuitions. So this number n is this is Jenny's intuition sample, and that's Alex's intuition sample separately. Something to notice is incubation. Alex never had an incubation period that was very long. So he wasn't experiencing like, oh, I went on a walk for an hour and had a hit. I woke up in the morning and had a hit. But Jenny actually was experiencing some of those moments. So that's just isolating the attribute univariate. Okay, let's look at what things look like overall, though. So and these are 2, 3, and 4 cluster models on the left. I used validity indices, but I actually looked across all the cluster models to determine my results. So the prototype means, so 0 would be classified as more non-creative cluster, 1 would be classified as more creative cluster. And so for the cluster 1, so let's just do the 2 cluster model maybe. So here's the 2 cluster model. The prototype mean for cluster 1 is 0.2. That would tend more toward the non-creative end, and 0.6, which is a little bit in the middle somewhere. I'm not seeing any extreme creative type prototypes in my data, but I am seeing some sort of moderate amount of some more moderate creative intuition kind of occurring, but not that really extreme level that would be characterized as maybe a value of a 1. What we can notice is that the younger student, the first-year student, has a mix of non-creative and moderately creative intuitions, or mildly creative intuitions. Whereas Alex, you see his membership value 0.9, 0.9. so it's probabilistic. 0 means it's highly non-related. 1 means it's definitely, it's got high membership to that particular cluster. So we see that Alex 0.9 across the boards, a 0.8 I guess there. High membership values to the more non-creative cluster. So the older student, the second year, had more non-creative forms of intuition, whereas the younger student was having a mix in the data. Overall, common intuition outcomes reported in the Intuition Journal and logs were rare and unique. Not common intuitions were more prevalent. So I'll focus on a small intersection of common intuitions where the content from their journals overlapped, but the actual attributes were very different. So the intuitions with the content overlap were related to the orbit stabilizer theorem, and Jenny logged that she was seeing the pattern orbit x stabilizer x equals order of g. And similarly, Alex journaled that the cardinality of a group can put restraint on the orbit size. So they're both getting at orbit stabilizer theorem here. While both arrived at these intuition outcomes with overlapping orbit stabilizer theorem content, the examples they were exploring in the duration of the task were very different, and the attribute makeup of their intuitions along the way were very different. Okay, so here's just some examples of their intuitions, and I'll just kind of leave that up there for you guys to read. Just kind of pause. We see Jenny try to make a leap to generalize a previously intuition, which was just trivial, saying that the orbit is the whole group and the stabilizer is just the identity. And this actually is is incorrect, but she'll correct later on. Jenny also explored other examples besides quaternions. So she's exploring D2N to GL2R here, and she's drawing a lot of sketches. And these are some of her processes. I'm able to capture some of her processes in the journals that are leading up to the conjecture that are along the lines of the orbit stabilizer theorem. All of these intuitions leading up to the orbit stabilizer theorem for her, number 7, 8, 11, and 10, that I was looking at, based off of the FCM data, they were tending towards the more creative cluster in the sample, that one that was like a 0.6. Alex makes the following, though. He says in his journal, so many of the examples that Alex explored had trivial stabilizers containing only the identity element. He was aware that these examples were not the most informative. He followed these with his preferred Dex transformation example and journaled, now I have to actually calculate something, which in my experience is often harder than understanding the underlying concepts, but in actual fact, I managed to pick something fairly well behaved. So that part wasn't as difficult as I anticipated, especially since the hard example was sufficiently general to not allow for exact calculation. So Alex liked to live in a realm of abstraction, and he was feeling computational overload with those examples, so he went to a more abstract space to think about things. He logged the following intuition, which is the orbit stabilizer, number 17 intuition for him. And according to the FCM data, that was had high membership value to the non-creative cluster. In fact, all of his intuitions leading up to this theorem belong to the more non-creative cluster. They weren't particularly novel to Alex. And so maybe I'll just say a few words about that. I did cross error and confidence, but I can talk about that if you're interested later. Or maybe I can just open up to the audience to see what they want to talk about. I did identify something called fragile creative intuitions in the data. So the idea of this is just that there was an intuition that had high membership value to the creative cluster. However, it also had, it was correct. So in terms of error to non-error type, it was a correct intuition. It was more creative, but Jenny had very low confidence in it, and she ends up rejecting it, the conjectural intuition. She ends up rejecting it altogether and moving on. And I term these fragile creative intuitions And I think it's intuitions like these that need to be tended to by care with educators. However, such intuitions may not be observable or withheld by the learner in certain environments and difficult to respond to on the spot. Moreover, figuring out to incorporate and build from the learner's creative intuitions during instruction presents a challenge with regard to visibility of creative intuitions, communication, and adaptability of the instructor. So there is statistical evidence of these fragile creative intuitions. I want to mention something about affect, though, too. So here's a quote from Alex. He says, if you read writers talking about writing, a lot of times they talk about having a writer and having an editor inside their head and sit down and write. They have to put the editor somewhere else so they can make all the mistakes, spell words incorrectly, and have terrible grammar. Then once they're done with that, they can bring the editor in and clean it up. And I think analogously, anxiety kicks in, and it's like the editor part is the one in control, and it's the only thing that's happening. And so the part of me that wants to just explore and see how things work, as soon as anxiety kicks in, it's just like, you don't have time for that. You got to figure this thing out right now. And that's sort of like, you're just focused on the solution and the end goal. It cuts all paths off to get to the end goal, it feels like. So this idea that affect or emotion can impact our intuition in a way that cuts it short. So some future directions. I think we need more research that evaluates trends in the field, both theoretically and methodologically. We want to catalog data-driven categories of primary intuitions that learners express for a given concept. We need to develop and explicate methodologies along with their limitations for investigating mathematical intuitions. We need to unpack relationships between intuition and the affective domain. We need to continue to catalog attributes associated with the intuition constructs. What attributes are meaningful for mathematics education research? We need to clarify what it means to develop learners' intuitions. What do researchers that emphasize cognitive dimensions look for, affective or sociopolitical? And we need to eventually try to pursue studies that examine the impact of novel forms of instruction or grading systems on the development or qualities of learners' intuitions. Thank you.
Okay, thank you very much, Jessi, for a lot of interesting materials. Questions? Gemma or Romain?
Thank you for this talk. You've provided such a rich vocabulary. I feel like I need to meditate on it for a while. But and I think it's really useful to think about these different measures or axes. Something you mentioned towards the end was this idea of fostering intuitions, and perhaps I'm reading too much into it, but it seems because you're in math education, maybe that's part of the goal of studying intuition is studying how to foster them. And I wondered specifically, was the choice to do journaling in order to foster intuitions, because having that reflexive process seems like it might be actually generative as well.
Yeah, I totally agree. I think journaling can be a great thing to bring into the classroom for helping facilitate or foster intuition. In this particular setting, though, I was just doing a case study, and this was before I started teaching abstract algebra. So I was just a doctoral student, and I was doing a case study, and I was having them journal just to gain an angle of qualitative data to pair with the quantitative statistical data to kind of give me a richer view of what students' intuitions look like. So it was really just exploring the qualities of their objects. And at that point in time, I wasn't really thinking about it from teaching it. But now I am, as I teach abstract algebra. I've done it a couple times now. And now that's I noticed my shift changing towards, like more how do we facilitate it.
Thank you.
Yeah.
Okay, Romain.
Thank you. It's a clarificatory question. It concerns a slide, I think was border properties or bordering properties.
Oh, yeah, boundaries.
Or boundaries, yes.
Yeah, they're fuzzy.
I don't remember exactly.
Yeah.
Yeah, exactly. The boundary properties, this one. Well, first, my question was, what about intuition without self-evidence? But then you brought some examples. You also said that very often with mathematicians, they were not so confident, actually. So self-evidence would probably imply confidence, I guess.
Yeah.
So that's my first question. And related to this, on the same slide before on the boundaries, there was, I think it was the second bullet, intuitive was in opposition to plausible, and this I found really strange. In what sense? Plausible in the sense, I mean, intuitive is opposite of rigorous, visual, plausible, or convincing. So I didn't really understand what that was about.
Okay, so the idea of plausible is just saying that whenever we have an intuition or an intuitive conception, it needs to feel at least somewhat plausible or convincing to have the motivation to pursue it. And otherwise, we wouldn't use our intuitions to really pursue anything. So plausibility can be thought of as a kind of a weaker condition than self-evidence. So instead of saying that the intuition needs to feel true without need for proof, you could say that intuition just needs to feel plausible to the intuitor, plausible enough that they try to pursue it.
Yeah, absolutely. But here it says opposite. That's the thing. What I didn't understand.
Oh, did I? Oh, I'm sorry. I think I might have. Sorry.
Oh,
yeah,
okay.
I think this is sorry. Yeah, this is typo. That was when I was making slides. Yeah, sorry. Intuitive is the opposite of rigorous.
Yes,
Intuition or intuitive means visual. Intuitive means plausible or convincing. Intuitive means. Sorry, yeah.
No, okay,
I can see how that's really confusing. Yeah, so I meant to just say intuitive is visual, intuitive is plausible or convincing, intuitive is incomplete, intuitive is. Okay.
Thanks.
Sorry.
Valeria?
I'm happy because it's on this slide, my question. I'm really intrigued by this idea that intuition is something that can't be replicated or fully recovered in contrast to proof, because I think that precisely in this idea that you want to foster it, we should think of intuition of something that can't be replicated, maybe across individuals, like something that can be communicated and replicated. Maybe it's the kind of thing that we want to foster. I mean, something that we will find more than once. And so I wanted you to comment on this, because of course it's not replicable in the same way in which proof is replicable or should be replicable. But there's something about intuition that you want to advance into expert intuition that you want to be there more than once.
Yeah, so some of the texts suggest that, especially like expert intuition, that it's transient. So they'll have some sort of intuition or happy idea, and they'll kind of have an idea of how to push something, but it's not really expressible in words, and then they forget about it and wake up the next morning. Have no idea what it is. They can't replicate or recover that intuition that they had, a week ago or 5 days ago. And so I think intuition is not stable. I think it's constantly changing. And so to replicate it, I'm not sure that it's possible to replicate the cognition as it was originally. So that intuition as a cognitive affective object, once it passes, maybe learning occurs, there's different framing, there's different cues, there's different environment that occur, that object is no longer, it's gone, it's no longer the same object. Maybe we recover it partially, but it's not the exact same object it was before, and we build from that sort of partial idea of what it was. But I don't think you can just recover it fully in its initial form.
But couldn't you think in terms of, having strategies for replicating or to have new intuitions, no? So to some extent.
It would be nice to replicate expert intuition if you could. One thing, though, I would caution, though, is that oftentimes as a learner, my professors would try to give their intuitions to the class. So they would write on the board these beautiful diagrams and pictures, and it was hard for us to access what that mathematician's intuition was. Even though they were trying to show us their intuition or give it to us, we could not take it in. And so I think really what instruction should try to do is to get the students to maybe develop their own metaphors or intuitions, create environments where they can develop those things for themselves, that are personal, that are internal and connected to them, rather than trying to access some expert's intuition, which I don't think that they can. It may be very difficult for them to access what an expert knows, because those intuitions took an expert maybe decades to develop. Who knows how long it took the expert to develop those intuitions? And just to think that you can just hand them to the student and that it'll help them, I'm not so sure.
Okay, then we can talk about it, but I don't know, maybe I have an idea what would be interesting to foster as something that has more collective dimension, so there is less a picture that is less solipsistic, maybe because I think in terms of the kind of instruments that you use and something as some kind of thing that you're sharing and that you can use to intuit similar things, but that's an open question. Thank you.
Maybe I can help. So we do some of my research now tries to design tasks with embodied cognition in mind, which goes on to this like active form of intuition, like this. So trying to get students to act out the mathematics to develop or facilitate their intuition and develop their own intuition for things. And so that's something that we've been working on lately, but aside.
I mean, just before Matthew, just a quick follow-up. So we know that like for the problem of like transmitting intuition, in the philosophy literature, one thing that is hard to transmit is understanding as well. And I think like intuition may be similar. And there may be a reason why is that if you go back to this kind of more computational aspect of learning, you see that for the systems to, like in the kind of AI thing we see yesterday with François Charton, you need a lot of examples to acquire this intuition. And so there may be like something fundamental about a difficulty to really like transmit it directly from one to the other. It would be like a system who have learned wanted to teach, wanted just to tell a system who hasn't learned what the right intuition is. But the thing is that for the system that hasn't learned, he has to learn. He has to go through the process of seeing a lot of examples, of trying out, of doing exercises, of being very active, right? So there may be something in the nature of what this intuition are. There may be something fundamentally hard to transmit right away that you have to think about the path. Or what do you think about that? Could that make sense? Or
kind of. I'm just not as familiar with like the AI stuff as much, but I mean, transmitting intuition from one person to another person, I think, I just feel like it would be really hard. I'm not even sure. I'm not sure if it's,
the only thing, probably if so, maybe the only thing you can do is train the other one the same way as you've been trying to acquire this intuition. So it's like you have to like uncover what you've learned, and put them into the same path of examples, maybe trial and errors, and like some kind of learning mechanism with a lot of input data, like the language model with all the solutions and problems.
Yeah, I see what you're saying. And so maybe like a parallel would be like in education, we put students in these environments called guided reinvention, where they use, like they're kind of in play environments like this, where they're just playing around. And the activities are constructed very carefully to get students to arrive at some sort of formal definition or theorem on their own, right, that they can have ownership of. And maybe if you could figure out what those environments are, then you can use those environments to try and help students facilitate the intuition, or I guess indirectly transmit the intuition that you're hoping that they'll develop. So for example, here, we were hoping to help them develop this idea that a subgroup is a symmetry within inside of a symmetry. This kind of geometrical intuition for a subgroup and maybe a normal subgroup when they're working on quotients. And so we put them in this environment to try to help them facilitate that intuition, because as a learner, and there was another mathematician, they said that they played around with these objects a lot to try to develop their intuition. So maybe figuring out what the environment was and then putting the thing you're training into that environment and seeing if they develop some sort of intuition, yeah.
Right. Okay.
Maybe an indirect way of transmitting, yeah.
Mathieu?
Thank you. Yeah, I think that's super helpful. Let me ask a couple of questions I had. Firstly, I wanted to push you on why the distinction you want to draw is between non-creative and creative. That felt I don't know, it felt sort of not an intuitive, I suppose, way of characterizing why is it non-creative?
So non-creative in the sense, like thinking about, how do you say this? So non-creative in the sense that it's a recovery of old knowledge. So let me go back to the base definition. It's reproductive. It aligns with system 1 reactions that come to mind quickly and without reflection. So things like same A, same B rule, more A, more B, some of these things that are common with errors, these are non-creative forms. They are things that are basically just recovering old consolidated knowledge. And I feel like that type of intuition feels very different than the type of intuition that mathematicians were describing to me when they basically find some sort of connection across 2 different fields and have some sort of boom hit, and now they have this major new result. That type of intuition felt very different from these non-creative forms, and I feel like the psychology literature, especially like dual process theory and these intuitive rules theories, were hitting more on this type of non-creative form and weren't really capturing these creative forms that are novel to the intuitor. Maybe I can explain okay, so here's an example. I was in a creativity researcher's office, and he gave me this task or this problem to solve. And I went up to the board to solve the problem, and I wrote down some sketches and some diagrams and told him the solution. And I gave him the solution within like 10 minutes, pretty quickly. And he said, "You're being creative." And I said, "Why?" He said, "Because you drew diagrams and pictures and representations, and you're flexing between representations, and you're being creative." And I said, "I'm not being creative at all. I've done that 100 times before, over and over. I'm just pulling all of my old sketches that I've done 100 times. I'm just pulling all of my ideas that I thought about 100 times before. I'm just recovering old knowledge that's very familiar to me. I'm not being creative at all. I'm not being novel at all, personally." And so I think it was the distinction, maybe it's rooted in this idea that intuition is very personal to the intuitor, and that what is defined as non-creative or creative is really dependent on the person internally. It's not dependent on some sort of outside observer. So as an outside observer, I can't say that your intuition is creative or non-creative. I would have to get at some sort of internal attributes. Does that make sense? I don't know if that makes sense or.
Yeah, no, sorry, I'm going to have to think about it. No, that's very helpful. I mean, I guess what I was thinking about is that it's possible to use that kind of recycling old knowledge in creative ways. You know, so if you think about like a grandmaster chess player playing blitz chess, you know, like moving every second or something, then they're not making the same moves they've made before. They're making very creative moves, but instinctively in some kind of intuitive way. And I guess you'd want to be calling that non-creative because they're using the knowledge that they're recycling knowledge, even though they're recycling it in a creative way. Is that the right distinction? So even though the expression of that intuition is creative, it's in your terms it's non-creative because it's just recycling previously learnt patterns, I suppose.
Yeah, I guess in the simplistic one it does seem like that. I don't know if the attributes, if this helps to clarify the distinction a little more. I don't know if I can even blow this up. But like, let's see, so, I mean, maybe they would say I've never experienced this move before. They strongly agreed that personality more creative. Ease of externalization, it's probably pretty quick for them to just make the move. I don't know, did they reflect on the move before they made it? Or did they just externalize it quickly without problem? Yeah, that's something that needs to be looked at for sure.
My other question was about your study, which seems really promising and interesting. But my question is whether or not by that method you're going to inevitably be missing lots of what some people would call intuitions. You know, like a Kahneman and Tversky type approach would be saying you're activating system 1 processing just all the time. You know, the fact I'm attending to you and not Yassine is a system 1 process that is my intuition in some sense. It's an intuitive process that's directing my attention to you rather than to something else. So, and I think you can think about that. If you think about like classic Kahneman tasks, you know, like a sort of anchoring task, say, you know, spin the thing and then guess how many countries there are in the world. the fact that people are affected by the spinner, they don't know they're affected. But that's kind of what makes it an interesting intuitive process. So I guess the fact that you're asking them to reflect on their intuitions as they occur, like inevitably there will be a lot of intuitions they can't do that because they don't know they've got it. So I guess my worry, and I would be interested in your response, would be, well, how do you know that that method doesn't bias the type of intuitions you're studying quite dramatically to one type and misses out quite a lot of other ones that might be actually quite important to the exploration method?
Yeah, definitely. Yeah, so it isn't clear that maybe this method isn't biasing one type or not. I think one problem is, let me go to the, okay. So the method did allow me to pick up different types here, but certainly there are compounds here. For example, if somebody has a highly creative intuition, maybe they don't journal about it or record it because they can't even express it at all. I did think about that compound beforehand, and beforehand I did instruct participants. I said, even if you're not able to express the intuition in words, at least mark that you had an intuition and fill out the survey items on the attributes, the qualities. Like, could you at least fill out the survey attribute items? So hopefully I was still able to pick up some creative intuitions. So the ones that are hard, or intuitions that are not maybe easy to express by prefacing them with that. But certainly it's easier to write down intuitions that are highly expressible. And so certainly I might be picking up more of those than the creative kinds. So I think that we need to think about a lot of these potential compounds and somehow try to minimize the occurrence of these compounds in the methodology by adding sort of statements or techniques like this where I'm saying, you might have an intuition that's not expressible, still record it, please, to the best of your ability. That way I at least know it occurred. I might not get journal data on it, but I know it occurred.
Yeah, I know. I think that's definitely sensible. But I guess I'm more worried about intuitions that they don't know have occurred. You know, so like if I...
Yeah, the ones that are implicit. Yeah, exactly. Yeah, I think so. Yeah, because they wouldn't even pick up on those, consciously register them. So yes, certainly this methodology is not picking up on that.
So what does that do to your... is that a problem for conclusions you can draw? Do you think that's not... I guess I'm just curious as to what the implications of that missing section of intuitions is for the conclusions you can draw. Or
yeah, just implicit cognition. I mean, certainly it would restrict the conclusions you can draw. There were some conclusions I felt comfortable drawing with the data, and maybe there are some conclusions that I wouldn't be so comfortable drawing. Certainly it will restrict what conclusions you can draw, for sure. I think one conclusion, though, I did draw from the data that I felt comfortable with, which I didn't talk as much about, was this idea of intuitive feelings of rightness or wrongness, which are guiding feelings. This is another class of intuitions, and I think that these guiding feelings can act on a previous conjectural intuition or example-based intuition. So for example, in the data, Ginny had, let's see, where is these clusters? Let me find them. Yeah, so okay, maybe 3 plus 2, 2 plus 2. So there's a couple clusters here where they're marked by low levels of confidence, and they're highly errored. So that gray bar, the higher it is, in terms of, oh wait, no, the other way around. So number 1, yeah. So 1 is errored, and then the blue bars, the higher they are, the more confident in their truth value. There was a case where, maybe I'll just stay in words because I'm having a hard time seeing that close. So there was a case where Jenny had an intuition. It was errored, and she was not confident in its truth value at all. And to me, you see somebody error, you think, oh, that's bad. But actually, her guiding feelings of rightness or wrongness were kicking in, and they were working properly to act on that previous conjectural intuition. So in that case, I think it's giving me evidence for when students' guiding feelings of rightness and wrongness are kicking in and working properly. If the methodology was revised in a way that we could eliminate more confounds, I think we could say, make more claims, for example, about regularity in the environment. So for example, if I think about creative intuition, non-creative intuition, and then I look at unique versus common within the population. So say I have a lot of density in non-creative forms that are not that are common, and I don't have very much of a density in creative intuition that are unique within a particular classroom or population. I would say maybe I have some regularity issues in that classroom because I'm getting a lot of non-creative common intuitions and I'm not getting any of these creative unique kinds. So maybe there's some sort of regularity issue in the environment. So maybe this distinction can point to some of these issues, but I think it's too early on to really tell what conclusions could be drawn. And this was just a very preliminary small sample that I'm dealing with, and there are confounds riddled in this methodology that need to be dealt with for sure. Yeah.
Great, thank you.
Okay, so I think we'll close the session if there's no more questions. So let's thank Jessi again. All right, so this is the end of our workshop. We still have one dinner tonight. I've sent an email to everyone. Yeah, I took that. And yeah, so you should have the information. Otherwise, I'll be around if you want to go for. You can go back to your hotel and so we'll meet at the hotel, the Amosa Hotel at 7:15. So me and Bruno will pick you up there. But if some of you want to stay around and go for a drink, we have to clean a bit with Louis, and then we can go with you. Okay. You leaving? Okay. Will do. For sure. You did all the work as speaker, so yeah, we were very happy to have the event there, and we were also very happy with the collaboration Nancy Liège in our area of Europe outside of Paris and all the big cities. Okay, thank you very much. See you later.
Thank you. I understand what you're saying about, yeah, because there's certain cognitions that you might not even remember. Like even whenever I write up proofs even, like I don't consciously think about the proof frame. It's just automatic. It's like I just do it implicitly, but I may not recognize